Tere hommikust, kallid kaasmaalased ja külalised, sõbrad ja vaenlased. Minu nimi on Merja Pukari, ma olen Fermi Energia üks kaasasutajatest ning ühtlasi teie tänase päeva jutujuht. Algamas on Fermi Energia järjekorranumbrilt küll teine, kuid sellegi poolest iga-aastane konverents. Meie konverents täidab täna 2 eesmärki. Ühest küljest heidame pilgu möödunud aastale ning katsume anda ülevaate nendest uuringutest, mis on läbi viidud. Need uuringud, mille eesmärk on selgitada, kas ning millistel tingimustel on võimalik rajada Eestisse tuumaelektrijaam. Teisalt katsume ka heita pilgu tulevikku ning vaadata, mida toob meile järgnev aasta, aastakümned ning võib-olla isegi pikem ajaperiood. Seega on mul väga hea meel võtta vastu nii teid, kes te olete meiega esmakordselt, kui ka teid, kes te olete korduvkülastajad. Ajastule kohaselt on meie konverents seekord digitaalne. Mina võtan teid aga vastu siit kultuurikatlast Tallinnas. Hoolimata sellest, et meil ei ole võimalik täna viibida füüsiliselt samas ruumis, julgustame teid sellegi poolest osavalt kaasa mõtlema ning esitama meie kõnelejatele küsimusi. Meie tiim omalt poolt annab endast parima, et vältida kõikvõimalikke tehnilisi viperusi, kuid tõrgete esinemisel soovitame teil siiski jääda rahulikuks. Hetkel ei võtaks ma aga mitte ühtki minutit rohkem meie tihedast ajakavast, vaid pigem annan sõna meie konverentsi esimestele kõnelejatele. Meie konverentsi juhatab sisse 3 keskkonna, energeetika ning jätkusuutlikkuse hiidu ning annangi sõna 2 esimesele neist. Esimesed avasõnad esitab Eesti keskkonnaminister Tõnis Mölder ning Rahvusvahelise Aatomienergia Agentuuri peadirektor Rafael Mariano Grossi.
See võimalik pidada ei ole. Seda enam on mul hea meel, et konverentsi korraldajad, kes vaatavad just nimelt tuumaenergeetika osas tulevikku, arutavad uute tehnoloogiate üle, on võimelised korraldama sellist interaktiivset konverentsi, kus üle maailma oma ala tippspetsialistid on kokku tulnud. Arvestades Euroopa ja maailma suundumusi, peab ka Eesti olema avatud uute väljakutsete tarbeks. Me peame lähtuma sellest, et meie kliimapoliitika ja looduspoliitika oleksid omavahel tasakaalus nii, et Eesti energiajulgeolek oleks tagatud. Seetõttu oleme ka meie avatud uuteks diskussioonideks, mis puudutavad energeetika valdkonda. Konverentsi teema uue põlvkonna tuumaenergeetika kasutuselevõtt Eestis on kindlasti oluline ja vajab laiapõhjalist käsitlust. Ühelt poolt on tuumaenergeetika oluline ning vajab teadlaste poolt hinnangut. Teine pool on ühiskonnas tekkivad emotsioonid, hirmud, kartused, mis vajavad selgeid ja konkreetseid vastuseid. Seda on võimalik teha nii, et avalik sektor ja erasektor teevad siin tihedat koostööd teadlastega. Vabariigi valitsus on andnud Keskkonnaministeeriumile ülesande moodustada tuumaenergeetika töörühm, mille üheks ülesandeks on analüüsida Eestis taolise energiaallika kasutusele võtmist. Vaatleme ja analüüsime tuumaenergeetika kasutusele võtmist Eestis. Oluline on rõhutada, et ühtegi poliitilist otsust sellise pika ja olulise sammu tegemiseks Eestis veel vastu võetud ei ole. Põhjalikud analüüsid ning sellega kaasnevad teadusuuringud on kindlasti investeeringud, aga see on investeering tulevikku, mida meil on vaja teha, et saavutada Eesti kliimaneutraalsuse eesmärgid. Vaadates tänase konverentsi esinejaid, teadlasi ja külalisi, keda siia on kaasatud, siis kahtlemata tuleb sisukas ja detailne arutelu. Soovin teile tänase konverentsi puhul tõsiseid ja tugevaid arutelusid, mis viivad Eestit ja maailma edasi ning tänases situatsioonis ka kõigile tugevat tervist.
Ladies and gentlemen, I would like to thank you for inviting me to speak at this event. I am happy to open this conference together with the Estonian Minister of Environment, Mr. Tõnis Mölder. Estonia is at an exciting moment in deciding how it will fuel the future. The decisions it makes today will have a profound effect on the country and the region for generations. Estonia is not alone in seeking a future powered by clean, reliable fuel. Countries across the European Union are busy establishing integrated national energy and climate plans. By 2030, all EU members will need to cut their greenhouse gas emissions to less than half their 1990 levels. I do not need to remind this audience that oil currently satisfies more than 2/3 of Estonia's energy demand. How is it possible to ensure a sufficient energy supply, causing the smallest possible environmental footprint? That question was posed at last year's conference. It will not surprise you that as the Director General of the International Atomic Energy Agency, I believe nuclear energy must be part of the answer. After all, we are the agency that supports atoms for peace and development. Nuclear remains the only energy source, along with hydropower, to have the demonstrated ability to decarbonize electricity production on a national scale. France and Sweden have used a mix of nuclear and hydro to bring their electricity supplies CO2 footprint to within the climate objectives of the Paris Agreement. But even countries pursuing mainly wind turbines and solar panels will need reliable backup when the wind doesn't blow and the sun doesn't shine. Nuclear power has been serving this role in many countries. And nuclear can help us to decarbonize sectors beyond electricity, industry, housing, and even transport. Nuclear power can be used for seawater desalination and hydrogen production. Small modular and high-temperature reactors could dramatically widen this potential. When nuclear power is used to produce more hydrogen for the transport sector, we have the chance to abate a lot more carbon emissions every year. Ladies and gentlemen, developing a nuclear program can be a long process that needs smart regulation and sound financing. There are many stakeholders to reassure about its safety and relative value. With a well-structured milestone approach, the IAEA is here to help. We have the expertise and the experience in all areas of nuclear, from creating legal frameworks to safely operating nuclear power reactors. We keep on learning and we keep on making breakthroughs. In November, I traveled to Onkalo in Finland and descended 0.5 kilometer into the first licensed deep disposal site for high-level nuclear waste. Onkalo is a game changer. With it, the safe final disposal of high-level nuclear waste ceases to be the unsurmountable challenge it once seemed. Whether in fighting climate change, treating cancer, boosting crops in developing countries, the IAEA has a long history of helping people benefit from nuclear science and technology. For more than half a century, we have mainly been working with governments around the world. Now, we are reaching out to new partners, including international organizations and even the private sector. Because together, we can work on exciting projects, such as fighting the next global pandemic, abating emissions, and cleaning up the plastic in our oceans. And the IAEA acts as a forum in which experts can gather. For example, just at the end of January, representatives of Estonia's Environmental Ministry and Board attended our virtual week-long regional meeting. They discussed engaging stakeholders with regards to SMRs and were joined by colleagues from Croatia, Hungary, Lithuania, Romania, Russia, Slovenia, Turkey, and North Macedonia. Ladies and gentlemen, in closing, I will say this. To meet our climate goals, the world needs more nuclear power. The Intergovernmental Panel on Climate Change has listed 4 model pathways for achieving the 1.5-degree target. All of them include increases in nuclear power generation of between 60 and 500%. That is why I'm pleased to be here with you today. I wish you all the very best in the important work you have before you. And I look forward to our ongoing dialogue and partnerships. Thank you.
Meie kolmas avakõneleja tuleb aga naaberriigist Rootsi. The Senior Executive Vice President at Vattenfall, Torbjörn Wahlborg. We are very pleased to have you with us.
Thank you very much. Dear conference participants, ladies and gentlemen, it's a great honor for me to have the opportunity to have a short speech at your great conference. And I'm going to focus today on why Vattenfall is interested in the development of SMR. I have a couple of slides with me, and could I please ask you to show the first slide? There it is. Thank you very much. So, global warming is today the main threat against human beings and a future world. I think just 10-15 years ago, global warming was very much discussed and challenged. And there was a big discussion, is this really happening? Today, I would say these discussions are not that intense anymore. I think the focus has now shifted much more from discussing and debating whether global warming exists to concrete actions. And that's probably the reason why we today see nations, regions, almost competing about who could have the most ambitious climate targets. And what we also see now is that there are more and more technical solutions for how to reach these ambitious climate targets. And this will, of course, accelerate the energy transition. What's also interesting today, I would say, is that almost everyone agrees that the solution is electrification. Electrification of the heating sector, electrification of industry. So electrification in itself will be the key to abate CO2 emissions. And this will, of course, drive demand. And the demand is for fossil-free electricity. It's for fossil-free heat, hydrogen, and of course, this will also put a lot of pressure on the grid companies to extend the grid networks. In the background of this slide, you can see the pilot project, the Swedish pilot project, which Vattenfall is also one of the proud owners and initiators of. It's the hybrid project, which is the aim is to produce fossil-free steel. And the pilot project started, this construction started 2 years ago, and today it's in operation. And just this company, SSAB, the steel company, if they were to produce all the steel using fossil-free technology, they would need roughly 15 terawatt hours of electricity to produce hydrogen enough for the company to produce fossil-free steel. And the ambition of the company is definitely to produce fossil-free steel, and not only 10% or 20% of the production, but 100% of the production. When we started this cooperation a couple of years ago, we were really first in the world. No one talked about this. People were questioning this technology. Today, all major steel companies are looking in the same direction. The main supplier of raw materials for this company, steel company SSAB, they just recently declared that they will need 55 terawatt hours of electricity in order to produce the hydrogen necessary for them to produce fossil-free raw material to the steel company SSAB. So we see that the electricity demand is increasing extremely fast nowadays. Sweden, for instance, has today an electricity consumption of roughly 150 terawatt hours, and we see that this will grow fast, and already 2040 will probably exceed 250. So we are talking about really fast growth here. Let's move over to the second slide, please. Every energy system will need to solve the energy trilemma. That's the energy triangle to the right. Energy production will have to be climate friendly. That goes without saying. It also have to be economical, so reasonable costs, and it has to fulfill the target of the security of supply. Today, we know that wind is developing very fast, climate friendly for sure, economically viable for sure, but having problems with security of supply. As Mr. Grossi also said before, when the wind is not blowing, well, wind is not delivering. The same goes for solar PV. SMRs, I believe, could be a game changer here. SMR technology will provide plannable or dispatchable fossil-free nuclear generation. So it will fulfill the climate and the security of supply. The big question, I would say, is still whether this will be competitive. So will it also be reasonable costs of building this? I believe the SMR technology is very promising in this aspect, and I think there is for sure a room and a place for SMRs to play. One of the good things and big advantages with SMR technology is the multi-purpose applications. These SMRs can produce electricity, but they can also provide heat. We tend to believe that electricity is the main challenge here, but I have to say that if you look at the heat consumption and how heat is produced in big parts of Europe, you will see that this is really the sector where we have the big challenges. Hydrogen production, hydrogen will be extremely important to electrify and to decarbonize the industry. And this can also be used for peak shift. So produce electricity to a bigger extent when electricity is needed and when the wind is not blowing and the sun is not shining. So these are the reasons why Vattenfall is looking into this technology, and we believe it's very promising. Thank you very much.
Suur tänu nende julgustavate sõnade eest, kuid ühtlasi silmaringi avardavate mõtete eest kõikidelt meie avakõnelejatelt. Samas võtmes jätkab ka meie järgmine kõneleja, kes on Fermi Energia nõukogu esimees Sandor Liive ning kes räägib teile Fermi Energia otsustest ning partnerlussuhetest.
eestimaalased ja meie rahvusvahelised partnerid. Tere tulemast Fermi Energia teisele konverentsile. Fermi Energia konverents on nüüd juba iga-aastane traditsioon ja isegi viimase sajandi suurim tervisekriis ei peata meid, vaid muudab ainult natukene selle konverentsi läbiviimise viisi. Elektrit on meil ikka vaja ja ka kõige raskemas seisus olevad koroonahaiged saavad hapnikku elektriga töötava hingamisaparaadi abiga. See on tõsine teema. Energiavarustus on tänapäeva maailmas tõesti elus püsimise küsimus. Seda mitte ainult vältimatu arstiabi kontekstis, vaid ka meie kliimavööndis lausa igapäevaselt. Meie oleme siin soojas stuudios, mis on üles pandud siia samasse kultuurikatlasse, kus me eelmine aasta paljud teiega koos olime. Teie oma mõnusates kodudes või ka siis mugavates kontorites. Aga siin samas seina taga on üle 10 kraadi külma. Ja täna öösel oli Virumaal ja mujal Eestis üle 20 kraadi külma. Veidigi pikaajalisem elektrikatkestus sellise ilmaga ei ole naljaasi. See poleks lihtsalt järjekordne õhtu küünlavalgel. See oleks sadadele tuhandetele Eestimaa inimestele tõsine ellujäämiskatsumus. Aga ärgem peatagem liiga kauaks niivõrd tõsistel teemadel. Meil on ka natukene toredamaid jututeemasid. Vaatame siis, kuidas meil kahe konverentsi vahel Eestis üldiselt ja eriti Fermi Energias läinud on. Vaatamata tervisekriisile on olnud meil väga töine aasta, milles on olnud väga palju suhtlemist nii Eestis sees kui maailma lähemates ja kaugemates riikides. Suhtlus on olnud küll peamiselt virtuaalne. Oleme saanud mitmete tehtud uuringute kaudu palju targemaks ja püüdnud varasemalt omandatud tarkusteri ka teistele jagada. Sisuliselt võib öelda, et Fermi Energia on saanud väikese hoo sisse ning seda on märgatud nii Eesti avalikkuses kui ka rahvusvahelisel energeetikamaastikul. Millega Fermi Energia silma on paistnud, seda ilmselt oskaksid paremini öelda meie tänase konverentsi esinejad ja need sajad inimesed, kes meid üle veebi vaatavad. Me ise arvame, et selle tähelepanu vundamendiks on teadmised, julgus ja ärategemistahe. Vaatame, kuidas ka Eestis on läinud. Sajandi suurim tervisekriis on jätnud oma jälje ka Eesti elektritarbimisele. 2020. aastal tarbisime Eestis 8 teravatt-tundi elektrit, mis on 3,4% vähem kui aasta varem. Eestis toodeti eelmisel aastal 4,8 teravatt-tundi elektrit, mis moodustab 55% tarbimisest. See tähendab, et 45% Eestis tarbitud elektrist importisime. Trend, et oleme nüüdseks elektrit importiv riik, süvenes. 2019. aastal suutsime toota veel 74% oma tarbimisest. 2020. aastal ei rajatud Eestis mitte ühtegi uut tuuleparki ja seda juba 8. aastat järjest. Viimane suur tuulepark avati 2013. aastal Paldiskis. Küll aga pandi püsti eelmisel aastal 200 megavatti päikeseparke. Oli viimane aasta, kui rajatavad päikesepargid said taastuvenergia toetust. 2020. aasta oli hea tuuline aasta. Tuulikud tootsid 881 gigavatt-tundi elektrit, seega 11% Eesti elektritarbimisest. Päikesepargid tootsid 128 gigavatt-tundi, mis teeb 1,6% tarbimisest. Seega tuule- ja päikesepargid tootsid kokku 1 teravatt-tunni ja 1,2 teravatt-tundi tootsid biomassi ja prügist toodetud elekter. Seega taastuvatest allikast toodetud elekter kattis 2020. aastal neljandiku ehk siis 25% Eesti tarbimisest ja poole Eesti elektritoodangust. Pool elektritoodangust taastuvenergia tundub päris suur. Kui ainult ei oleks seda toodangu drastilist langust, millest ma ennem rääkisin, sest see suhtarv, taastuvenergia suhtarv on kasvanud peamiselt tänu sellele, et toodang on langenud. Kahe konverentsi vahel on Eesti saanud ka uue valitsuse. Uue valitsuse koalitsioonileppes on tuumaenergia saanud lausa eraldi punkti. Tsiteerin. Jätkame diskussiooniga tuumaenergeetika kasutusvõimalustest Eestis. Otsime võimalusi riigi tuumaenergeetika kompetentsi tõstmiseks. Tsitaadi lõpp. Leian, et selline punkt just täpselt sellises sõnastuses on igati sobilik riigile, kes alles tutvub tuumaenergiaga kui võimaliku alternatiiviga energia tootmises. Samas 2035. aasta ei ole sugugi nii kaugel. Keerulisi otsuseid tuleb tegema hakata pigem varem kui hiljem ja selleks hetkeks peavad diskussioonide kulminatsioonid juba ületatud ja kompetentsid omandatud olema. Mainisin aastat 2035 ka sellepärast, et see aastaarv on koalitsioonileppes olulise punktina koha leidnud. Põlevkivist elektritootmine lõpeb 2035. aastaks. See on ka aasta, mil võiks Eestis esimene kaasaegne väike moodul tuumajaam juba elektrit toota. Enne elektritootmist tuleb jaamaga valmis ehitada, enne ehitust planeerida, jaamale koht ja sobiv tehnoloogia leida, enne planeerimist aga tuleb valitsuse poolt planeering ametlikult algatada ja selle otsuse saab teha ainult koos Eesti rahvaga. Seega mõeldes, arutades, kaaludes, rääkides ja hoolikalt kuulates. Eelmine valitsus moodustas enne tagasiastumist novembris keskkonnaministri alluvuses tööle hakkava riikliku tuumaenergia töörühma, mille uus keskkonnaminister Tõnis Mölder nüüd sisuga peab täitma. Nii nagu sujuvalt on tuumajaama teema ühelt valitsuselt teisele liikunud, peabki see toimuma. Tuumajaama ettevalmistuse ehitamise ja opereerimise jooksul näeme Eestis kõikvõimalikke koalitsioone ja ilmselt ka uusi parteisid Riigikogus. Energeetika ei saa olla ja ei olegi erakonnapoliitiline teema. Elektrit on kõigil vaja, sõltumata sellest, kas tuul puhub või päike paistab. Fermi Energia jaoks oli 2020. aasta kindlasti rahvusvahelistumise aasta. Esimene mitte Eesti juurtega meeskonnaliige liitus Fermi Energiaga, tunnustatud tuumaõiguse spetsialist Helen Cook. Esimene välisinvestor juunis 2020 tegi Fermi Energiasse investeeringu USA investeerimisfond Last Energy. Astusime Euroopa Tuumaenergia Liidu Foratomi liikmeks. Uutest tuumatehnoloogia arendajatest lõime koostöö Ühendkuningriigi Rolls-Royce'i ja Kanada Ultrasafe'iga. Mõlemad on koos meie varasemate tehnoloogiapartneritega ka tänasel konverentsi paneeldiskussioonis esindatud. Meie ühistest uuringutest alanud koostöö Rootsi Vattenfalli, Soome Fortumi ja Belgia Tractabeliga on liikunud kaugemale, kui isegi alguses loota julgesime ja täna võime teada anda sellest, et Tractabel teeb investeeringu ja saab õige pea Fermi Energia osanikuks. Kui Fermi Energia esimesed investorid, enamus neist olid kõik kasutajatest vanemad, siis sel aastal on trend murdunud ja Fermi Energia investoriks on saamas meist nooremad, uue põlvkonna tehnoloogia vallas edu saavutanud ettevõtjad. Fermi Energiasse saavad õige pea investeerida kõik soovijad Funderbeami kaudu. Saladuskatte all ütlen, et oma investeerimissoovist saab juba täna meile teada anda, saates sellega e-mail info@fermi.ee. Eelmisel aastal tegid Fermi Energia rahvusvahelised partnerid mitmeid uuringuid, mille tulemuste tutvustamisele konverents pühendatud ongi. Tractabel asub kohe peale minu sõnavõttu tutvustama asukoha uuringu tulemusi. Fortum koos Helen Cookiga räägivad tuumajaama litsenseerimismudelist Eestile. Staffan Quist on teinud uuringu, mis annab vastuse küsimusele, kas saame loota Rootsile ja teistele Skandinaavia riikidele, et meil tuled põleksid. Vattenfall esitleb uuringut väikereaktorite ehitamise kiirusest. Väga oluline teema, mis alati tuumaenergiast rääkides esile tõstetakse, on ohutus ja tuumajäätmete küsimus. Ka tänasel konverentsil käsitleme neid oluliseid teemasid. Nimelt KBFI on teinud uuringu väikeste moodulreaktorite passiivohutusest ja deep isolation kasutatud tuumkütuse käitlusest. Loodame, et need ettekanded annavad kindlust ka laiemale avalikkusele, et ohutu tuumaenergia on võimalik. Tänase konverentsi avasõnades Rahvusvahelise Aatomienergia Agentuuri peadirektor Rafael Grossi ütles, et täita kliimaeesmärke vajab maailm rohkem tuumaenergiat. Ta ütles ka, et kindlat, ilmast sõltumatut täiendavat energiaallikat vajavad ka riigid, kes panustavad peamiselt tuule- ja päikeseenergiale. Eesti on tuulepealne maa. Me kindlasti peame tuuleparki juurde rajama, vaatamata nendele raskustele, mis kõiki kavandatavaid parke on Eestis tabanud. Uutele päikeseparkidele on kindlasti jätkuvalt ruumi nii elumajade ja tootmishoonete katustel ning päikesepargid otse tarbimiskohtadel ei vajagi toetusskeeme. Suured elektri hinnarinevused igal tunnil annavad selge signaali, et ka Eestis on käes aeg targaks elektritarbimise juhtimiseks, et nihutada tarbimine odavamatele tundidele, kus see on võimalik. Elektriautod tulevad, nende maht kasvab ja neid ei ole vaja samal ajal laadida, kui õhtusöök ahjus küpseb. Kindlasti on meil turgu elektri salvestamiseks, olgu see siis hüdropump elektrijaama või ka lihtsalt akude abil. Salvestusseadmed ja tarbimise juhtimine võivad meid aidata ööpäevaseid elektri tootmise ja tarbimise ebaühtlusi siluda, kuid ei aita meid kuidagi suvist päikest talvekuudeks säilitada. Lisaks tuulele ja päikesele on meil vaja veel midagi. Täna on see veel midagi põlevkivielekter, mis hetkel, just nimelt täna, külmal talvepäeval, töötab täiega. Kuid mis on see miski tulevikus peale aastat 2035? Loodan, et peale tänast konverentsi on Eestis jälle rohkem inimesi, kes ütlevad, teeme oma tuumajaama. Aitäh!
Suur tänu Sandor Liivele selle suurepärase sissejuhatuse eest ja ma arvan, et tõepoolest aeg ongi edasi minna uuringute juurde, mis viimase aasta jooksul ellu on viidud. Nagu Sandor mainis, on Tractabel meie strateegiline partner ja esimene uuring, mille tulemustest meil ette kantakse, tulebki Tractabelilt ning see uuring räägib asukoha uuringutest väikese moodulreaktori rajamise kohta Eestis. Philippe Monet from Tractabel, I hope that you're with us because we would be very, very interested to hear about the results of your site screening study for SMRs in Estonia.
I'm with you. I hope you can hear me. If you can show this by your hand.
We can hear
you.
you.
Yes. And I'm now sharing my screen. Hopefully it's also getting across. Can you confirm? All right,
We
I
can
can
see
see
your
it.
screen, yes.
Thank you. All right, so it's really thank you, Maria, and good morning, everyone. It's a great privilege for me to be invited to speak to this conference, actually for the second time. Last year, we presented a down selection of small modular reactor technologies for Fermi Energia. And this year, we'll present a different kind of down selection exercise, which is screening, doing a site survey and screening the sites to identify potential locations where SMRs can be built in Estonia. So this work was performed as a desktop study, as is suggested by the illustration here, and actually due to the COVID situation, it was entirely a desktop study. We we actually missed, we were deprived of the best part of the sighting project, which is to do a lot of sightseeing. So I make it a personal objective for later this year after vaccination, hopefully to be able to conduct a comprehensive and systematic sightseeing tour of Estonia. The work was done as a collaboration between Tractebel and Estonian company Steiger. And I wish to acknowledge here contributions of Steiger, and in particular of Mrs. Anna Helena Pure, who managed most of the data collection part, and also the environmental study. Wish, of course, to acknowledge the contributions from my colleagues in Tractebel, and to express my appreciation to Henry Ormus of Fermi Energia for overseeing the work, and to Kalev Kalemets for his very useful inputs and insights, knowing also that Kalev has a very good background in geology, among many other things. So let's now move to the next slide and explain what this presentation will cover. We'll cover the scope and objectives of the work. The first three bullets actually are a description of the process that was followed, screening criteria, data management, and the following points are actually the application of the process, and we will present some of the results in terms of areas of interest, candidate sites that have been identified. We'll provide the conclusions and a few words about the follow-on work. To the picture there on this slide is a shot of this famous Clint. You need to know this word if you if you speak to Estonians. The Clint is that cliff that is the border of the Gulf of Finland, and so goes along the northern Estonian coast from east to west, or from west to east. And sometimes it's 50 meters high, so sometimes it's in this case here, it's lower elevation. What is nice about the Clint is that it displays the actual geology of Estonia, being a superposition of sedimentary rocks of different layers, all very old, prior to the appearance of the first forests on Earth. And it's overlain by a very thin layer of quaternary sediments. We'll come back to that later. And the objectives of the study were quite straightforward. It was to identify 4 to 5 candidate sites. Candidate sites is the expression used in IEA standard to designate the most suitable site locations out of a site survey. Clearly, as a matter of principle, full compliance with IEA guidance was set from the beginning, and we also used experience from past projects that was applied to this one. This site survey is a preparatory step prior to a formal application under the Estonian designated spatial planning procedure, which is managed by the Estonian administration. The sites we were looking for had to have the capacity to host multi-unit SMR plant of at least 600 megawatt electric capacity. For considering a set of pre-selected technologies for which we built an envelope of basic parameters, very basic ones, such as plant footprint and cooling water requirements or minimum soil properties. Just to show where this fits into the overall IEA siting process, well, it's the first step. It's a site survey. Then according to the milestone, IEA milestone definition, this is actually phase 1, and prior to the site evaluation. So the site survey will identify suitable candidate sites. That's the objective. and prepare all information required to go into the next phase of scoring and ranking the different candidate sites and making a selection of the preferred site. Note that site confirmation will only be reached after site characterization, which is the next box here, for which that's where the more extensive field surveys are carried out, and the plan design basis is determined, and the safety analysis report for the siting chapter is prepared. All right. Moving on to the next slide. So the nice thing about siting is also that it's absolutely multidisciplinary. It covers a range of disciplines from environment, as you can see here to the left, cultural heritage, demography, to more physical aspects of topography, bathymetry, geology, seismic activity, geotechnical, flooding, and back to more human attributes such as human-induced hazards and land use and ownership and infrastructure. There are a few other ones which will come later in the picture. So data are collected for all those disciplines, and they need to be collected in a careful way. IEA is very insistent on the need to have a data management system set up right from the beginning to review the data for accuracy, reliability of the source. Then once they are validated, to decide whether they should be entered into the project database, a database in the form of a geographical information system. And that database will be over time enriched with more data that will be acquired in the later phases. The process of screening is quite straightforward. We start from regions of interest, and in the case of Estonia, this quickly defaulted to coastal regions because the use of water inland from rivers of lakes is quite restricted. So starting from those regions, we apply a first set of screening criteria to determine areas of interest. The first set of criteria are more of a global macro scale application. Then looking deeper into each of those areas of interest, we apply the remaining set of criteria to come up with potential sites, and among them we select the best ones as candidate sites. The criteria that are applied are either purely exclusionary, meaning black or white, no-go situations, so you shall not build here type, and this applies, for instance, to Natura 2000 environmental restrictions. And we also have discretionary criteria, which are a little bit softer and judgmental, and allow us to factor in other aspects which have an impact on project cost and risk, actually. So a two-step approach was followed. This is a table showing the different attributes for each of those steps. Step one, you read it from the slide. And again, these are applied at the overall countrywide scale. And step two, for each area of interest, we go deeper and to more local objects such as cultural heritage or hazardous facilities or local geological properties, as well as grid infrastructure, land use at the local scale. So I'll now illustrate this, the step one by selecting three attributes. Of course, there are quantitative criteria that are not explained here, but for instance, for airports, there is a defined shape of exclusion area. For distance to capable faults, it's 5 kilometers to a mapped fault. So we have quantitative criteria for each of them. So to illustrate, this is the I have some echo, which should be suppressed if you can. Natura 2000 exclusion is quite extensive, as you can see. It takes out the whole of the western part of the coast, and also big blocks of the northern coast. And even when it's only a line, like the okay, I'm trying to move my arrow, but I cannot see it. Okay, I don't. If you see my arrow, this is a cliff that, and also we have rivers like salmon rivers, and the larger river here are excluded. So very impacting exclusion criteria from environment. On the population density, to the contrary, this Estonia is a low population country, low population density, except for the capital Tallinn, and so this was not quite restrictive in terms of identifying sites. Faults, geological faults. What you see on the screen is actually buffer zones along identified geological faults that affect the bedrock. And let me be clear that it's not that there is a risk, a real risk of surface rupture of such faults in Estonia. I think the risk is almost nil, but it takes time and resources to demonstrate that it is the case if you are too close to an existing fault. So we prefer to stay away from that, which it's rather a cost avoidance decision than a real hazard, I would say. In the case of Estonia, which would not be the case, of course, in seismic active areas. Just a few words on the geology. Well, you saw the picture of the Clint, and you see here a cross section from north to south, from the Gulf of Finland to Latvia, and the north being on the right side and Latvia to the left side. And you see here this superposition of very old sedimentary rocks overlaying on top of the crystalline basement, and a very thin layer of quaternary sediments. There are implications, technical implications to this, which I cannot cover in detail right now, but one of the good things is that you're almost certain to find a competent rock anywhere below at a few meters depth, which is good for foundations. So now superposing all the step 1 criteria, 1 to 6, and adding, of course, the C as an exclusion zones, we see that we have many restrictions. Some of them could be refined or lifted, but we end up with a sufficient number of distinct areas of interest where we are about sure to find potential sites within each of those. So we have 2 here to the west. Only one location in Pärnu here is not protected from Natura 2000. There's one on top here, Keibu Aliklepa, in the western part of Varju. Pakri Peninsula, I won't spend time there, but we didn't find a suitable site there because it's all locked in by environmental restrictions. There's one area here in the eastern part of Harju, which we'll talk about. Another one in western Viru, and last one in eastern Viru. So what I want now to illustrate is the application of the follow-on, the set 2, the second set of criteria to this area here in the western part of Harju. So this map shows the mapping of hazardous facilities and hazardous networks, such as this red line here from left to right, which is the gas pipeline. And okay, so collecting those data, you can see that there is an empty area here at the center of the picture, which is suitable from free of any human-induced hazard. When we look at the same area, okay, the coast is not very visible, but this is the coastline. From a bathymetry and topography point of view, we see that we can access deep water at three different sites, from three sites. That on the topography, we are above the flooding limit. We are not too high in elevation. Actually, it's a very flat area, topographically speaking. So this area is quite good for identifying a potential site. Going on with other informations, the land use in this case, where of course we don't want to define sites in built-up areas or harbors or other infrastructure, nor in places where there's already a planning procedure that is launched. And here we can see that we have the same area I was talking about is as green covers, but so it's mildly sensitive from an environmental standpoint, but it's actually a managed forestry of large area for which it would be acceptable to carve out, let's say, half a square kilometer for locating a nuclear power plant. And finally, the cadastral information is available to, we see here that we actually have state-owned, large parcels of state-owned land. This is certainly preferable to very fragmented private property. So that's an illustration for this single area where we superpose everything, and we can identify this gray rectangle here as a potential area for a site. This area is too big for it doesn't define really the site boundary, and as you can see, it can be moved around a little bit up or left. Anyway, we designate this site as the Cabernet site. Problems with my mouse, okay, in the center here. And we proceed similarly for the other areas of interest that I've shown before. We have, therefore, we have a site in Hapsi down here, another one in Keibu, Aliklipa, Cabernet, Kunda. And for Luganuse, we actually have three distinct sites with very different properties, and we felt that at this point we were entitled to choose one over the other. They have very different characteristics. So we kept all three options for now. On the contrary, we dropped the Keibu and Hapsi site because looking at the infrastructure, those sites are not well served in terms of grid, and neither in terms of transportation, road networks, and railways. All right, so this is actually the result of the project. I would now need to check time, and I have another 5 minutes to go to go through each of those sites if time allows, if I'm not overrunning. So very quickly then, we're going through each of the sites. Just a few words about each of them. So the Kunda site has this very good attribute that there is a harbor there to deliver the large items, large modules or equipment, or even bulk material that could be delivered right away at the site. And it's what you see there is municipality-owned land. It has a bit of a problem in terms of the elevation, and therefore the flooding risk or the maximum probable flood level should be assessed more carefully according to nuclear standards, for considering very extreme meteorological events and also the effect of climate change over a long period. Therefore, we'll probably move from the initially considered site, which was next to this corridor here, and move further up north to define the precise boundary for that site. The Moldova site, a little to the east. Well, this site is objectively an excellent site as a seashore power plant, allowing for direct cooling by the sea. Now, I'm saying objectively because the landowners may not see it that way. And so that illustrates the fact that site selection part has to factor in all, well, certainly to have stakeholder engagement of the different stakeholders, not only the landowners, but certainly the landowners, and to weigh the different advantages and disadvantages of a particular site, considering many different aspects. In the back of the picture, you see those mountains. Well, there are no mountains in Estonia, so these are artificial mountains of slag heap near Kohtla-Järve from the long time exploitation of oil shale. And we are actually getting nearer to these slag heaps for the following site, AA. That's the blue rectangle there, which is inland. And that causes a little bit of a disadvantage because it should be a closed loop cooling. When I talk about cooling, I mean condenser cooling, right? It's a pure conventional cooling of the condenser, not the reactor itself. And so that would be a closed loop cooling, but you do need to have makeup water from the sea to that closed loop. Which would require then to have a 4.5 kilometer distance of pipes and a pump station at the sea, and pump this water up to an elevation of 47 meters. So that's the disadvantage, and we are going to try and quantify that in terms of the plant efficiency and the cost of the cooling system. But the site has many other very positive attributes of being large, flat, well served by infrastructure, and easy to connect to the grid. And actually, it would also offer a possibility for district heating of the nearby Kohtla-Järve city. Aidu site is not so far from there, a little bit to the south. That's where oil shale was exploited for a long time. So trenches were digged. And they have now become some kind of artificial lake, which you see on the picture there, with many ramifications. And so that would be the source of cooling, again in a closed loop system. And definitely we would need to ascertain make certain that that water basin would not get depleted over a long period of time, that there's sufficient groundwater input to the lake. We are not talking about big volumes of water to be pumped for a closed loop system. The advantages is it's a brownfield site. It used to be where the oil shale was processed. It's owned by the state, and it has excellent infrastructure, even a railway into the site, and great connectivity to the nearby Püssi substation. All right, and so you understand now why we did keep those three sites, which I just talked about, which are located on the same municipality of Lüganuse. The last one, Kaberneme, is the one I illustrated before, and this is a state-owned land. As I said, it's a large managed forestry, but you know, with conifers, not very old trees. It was pointed out that there might be some public acceptance issues. So we have nearby nice cities along the coast in Neme, Kaberneme. But maybe this is an opportunity to stress again that small modular reactors are hyper safe. They emit no fume, no pollution, and actually the vendors have made a big effort on the architectural aspect of those facilities, which do not look like industrial facilities anymore. So in other words, it may be quite a good neighbor actually to have an SMR facility. All right, so I've just gone through all of those sites that are kept as the best candidate sites. We see that we have indeed identified several valuable sites in northern Estonia, actually all were east of Tallinn. Now we should conduct focus studies to answer specific questions. I mentioned the cooling aspects to differentiate between some of the sites, and maybe enhanced flooding study. So very focused studies to answer specific questions. And we'll then finalize summary files that have already been prepared to gather information on each of those sites as an input to downstream to the scoring and ranking of each of those sites per the IAEA guidance. With all of that, Fermi and Energia would be ready to prepare to formally submit the application under the National Spatial Planning Procedure of Estonia. This is the end of my presentation. I hope you found it informative, and I will be ready to take questions.
Philip, thank you very much for that extremely thorough overview. And for those of us who would like to have a nuclear power plant in our backyard, I guess we now know where to buy real estate for the future. If you don't mind, I do have a couple of questions for you. And the first one is actually related to the siting process. So is the siting process for an SMR any different from that of a conventional large nuclear power plant?
Well, the rules for siting are not defined specifically for SMR, so they are the same ones as for large nuclear power plants. Now, but there are specific features of small modular reactors that are quite advantageous. One, probably the main one, is that the fact that all vendors make the promise to demonstrate that the emergency planning zone would be restricted to the site boundary, so that in effect there would not be an emergency plan needed for the population nearby. And likewise, that would also make the site characterization work a little bit easier. We would not need a very detailed site-specific atmospheric dispersion analysis, and because we would use a generic one from the vendor that applies to the site boundary. Therefore, no big meteorological station at the site itself to measure all kinds of site-specific parameters. I'm not saying that we would be cutting corners, but it's really an opportunity to indeed simplify a little bit the site characterization phase. But also, when we select a site, we are careful to select sites which have kind of homogeneous geotechnical properties, so that we can simplify the borehole plans for obtaining that information. So, in other words, in a summary, the rules are the same. The applicable safety guideline is the same, but we can hope for simplifications by design of the SMRs and also by proper site selection.
There's another question to you from the audience, and the question is as follows. In your analysis, have you also considered the large energy consumers, industrial consumers in particular, as one of the factors?
Yes, it is an attraction factor. Now, contrary to other countries, Estonia doesn't have a lot of large industrial facilities. But in the case of the Kunda site, for instance, we know that the reactor could serve the needs for the nearby paper mill. In the overall realm of defining criteria, although it seems that like there's a lot of emphasis on negative criteria of exclusion, don't go there, don't go here, we do also have attraction criteria, and I think it's very important that they are explicitly recognized. And so proximity actually to also to small cities that can benefit from district heating, or to industries, or also to small cities that can afford the accommodation for working people. Also, not be in a very remotely and isolated place. I think it's a shift in paradigm in terms of site location for SMRs. But yes, and also in the direction that was mentioned by was mentioned before about multi-purpose SMRs, the industrial applications are certainly something that will require co-location of sites nearby industries.
We also sometimes get this fairly intriguing question of why do you want to build it on land? Couldn't you build it on one of the small islands off the coast? How would you respond to that?
That's what the Finns do, right? Loviisa is on an island just across the Gulf of Finland from Estonia. Well, that would be fine. You just have to lift all the Natura 2000 exclusions. So that's we didn't find any location including islands that was not protected by environmental restrictions in Estonia.
And then finally, what is for an SMR in Estonia? What would be the minimal distance to populated area or an industrial area?
The answer from the vendors to the question, we sent the questionnaire to them on the low population zone. First of all, low population zone is defined as a requirement in the United States, but it's not explicitly defined as a prescribed limit by IEA. IEA defines that mandates that you will have to demonstrate the feasibility of an emergency plan. But so the answer to the question is it can be a very short distance. You've seen the densely populated areas on one of the maps, and the criteria we used was 200 people per square kilometer, which means 2 people per hectare. So that's not very dense. Okay, so as long as we are outside of those areas, I think we are okay. Now it's a matter also of acceptance by nearby landowners, and so it's a matter of prudence and just kindness, I would say, to let probably a kilometer or so, or 2 kilometers from the nearby homes or populated areas.
Philip, thank you very much, and I'm looking forward to the progress.
My pleasure.
Even the progress for next year. Thank you again. Coming up, we have 2 speakers who will continue on the topic of the potential of building SMRs, but looking at it from the licensing point of view. And so I would like to welcome our next 2 speakers, Nikki Barry-Ruth from Fortum, and Helen Cook, our partner, to talk about the SMR licensing model for Estonia. I hope you are with us.
You try, Merja, can you hear me now?
Hi, Nikki, I can hear you.
Great. It's always better to have the mic unmute.
It is indeed.
So before I go into my presentation, which is a brief introduction to the licensing study that we have done in cooperation with Fermi, I want to thank my co-authors, Pekka Nuuttinen from Fortum and Helen Cook. And then okay, can you see my slides?
We can indeed.
Merja, can you see my slides? Okay, great.
Yes.
So then let's get started. So this is a brief introduction to the SMR licensing study that we have conducted, Fortum and Fermi together. And the content of my presentation, I will just give you a short introduction to the licensing study, just the purpose, the role and goals of the study, and then present the main results, the general licensing process and a possible licensing model. And in conjunction with the licensing model, we have also considered some possible examples for application of graded approach in the safety assessments. And also, I will discuss briefly about the objectives and methods regarding the different safety assessments. And then I will wrap up with key findings and conclusions. So the main goals of the licensing study was to seek an efficient licensing model for obtaining a construction license for SMR in Estonia. And a legislative and regulatory blank canvas was taken as a starting point. And the study was aiming also for a 12-month regulatory body approval time. And it could be said that the study particularly considers Estonia as a newcomer nuclear country, but also that the model could be accepted more broadly. And the general idea that was utilized and built for what the study builds upon is that the licensee is ultimately responsible for safety, and also that the national regulator must have competence and resources to independently ensure the safety of the plant. However, in this study, the idea has been taken that to use the maximum extent an existing safety assessment of a foreign regulator, so that the Estonian regulator would use the safety assessment from a foreign regulator that has licensed the SMR design in question. And that would mean that the project and the design would not be a first of a kind in Estonia. And what this would then mean, it would mean that the Estonian regulator would verify the foreign safety assessment and accept it to the extent possible, minimizing all design changes, and design changes would then be limited only to the site. And the same applies for the supplier organization and the supply chain. And for this, there would be no detraction from the independency and the sovereignty of decision-making of the national regulators. The focus is clearly on licensing from nuclear legislation and regulation point of view. The conventional permitting has not been in focus and has not been addressed, and that is something that needs to be further investigated also when it comes to licensing and permitting. The main focus is really on how to obtain a construction license in practice. We have utilized 3 licensing areas in the study, namely being the site, technology, and organization. And in the study, the focus is on the technology part, how to license the technology. We have emphasized intelligent customer and the role of the license applicant safety assessment in the study. And in general, the study was made to be technology neutral and universal so that it could be adapted into whatever the framework of the model to be utilized in. And the main results really is a general licensing process that is based on an overview of different licensing approaches and licensing phases in selected countries, and the feasibility of those have been discussed from the deployment point of view in Estonia. And in the study, we selected or addressed the countries US, Canada, UK, and Finland. And then the licensing model based on leveraging on an existing foreign safety assessment and the safety assessments of the license applicant, as well as the national regulator based on a graded approach. And we consider that the scope of the foreign safety assessment would be one dimension in the graded approach, and then the safety significance of the subjects for the safety assessment would be another one. We also briefly discuss an additional viewpoint, which would be a system engineering hierarchy. But in this context, it has been just provided as an additional example, demonstrating that it can be done in different ways. And in connection with the safety assessments, when talking about grading, also the objectives and methods of the different grades and the safety assessments have been presented. So regarding the general licensing process, it is a discrete step licensing process consisting of 4 main phases, being the decision in principle, construction license, operating license, and decommissioning license. And I will focus on the 2 first steps, which are heading or targeting the construction license in more detail in this presentation. So the first step is a decision in principle, which would be a political decision regarding a particular nuclear facility project. So this is not the IAEA milestone 1 national position, which is assumed in this study to have been taken earlier. So the decision in principle would thus be granted during the IAEA milestone approach phase 2. At this stage, the focus on technology and site should be very limited and limited only to a preliminary safety review to ensure the availability of technology and also that there are some site alternatives available. And this is actually the approach would be closer to the original intention of the decision in principle as it has been in Finland. Also, at this stage, a strategic environment assessment is considered to be sufficient, and detailed environmental impact assessment could be conducted later. The decision in principle would be granted by the government, potentially ratified by the parliament if so wanted. And in parallel, and even before and also after the decision in principle, it's included a topical pre-approval process, which would include binding regulatory approvals similar to the US NRC licensing topical reports process. And such binding pre-approvals would be provided to high-level safety issues, conceptual issues, which would be fundamental for the project and in order to reduce the licensing risks and increase the certainty for the project. The construction license would be a combined safety assessment of the site and technology, which would be carried out based on the site-specific design. And at this stage, also the detailed environmental impact assessment would be carried out. And benefits would be that it could be done only for the chosen technology as well as for the chosen site. And from the regulator point of view, of course, in addition to the technology, the supplier organizations, the supply chain, as well as the license applicants' resources and competence would need to be assessed. And the construction license would be granted by the regulator. And then this scheme provides an overview of the 2 first phases, the decision in principle and the construction license, from a little bit different angle and point of view than the previous pictures. But from this picture, I just want to highlight that in the upper left corner, where the foreign regulatory body as well as the vendor is present, that the safety assessment of the standard design or a reference plant, as well as a potential design certificate or a construction license, would be the basis for obtaining the construction license. And when it comes to obtaining the construction license in practice, I'm focusing in the next slides regarding the practical elements regarding the safety assessment of the license applicant and the regulatory body. And for the safety assessment, this slide shows or presents an example for an application of graded approach. divided into two different dimensions. That would be the safety significance of the items, as well as then the reference design and potential deviations from the reference design. And such deviations, they could be based on local requirements, lessons learned, or then the site and environmental conditions. And as mentioned earlier, in order to minimize the designs, really to limit them to site and environmental conditions, this colorful scheme could be transformed into a little bit more boring with just two colors, but really to focus on the site-independent design and the site-dependent design, and considering the safety significance of the items. And for the safety assessment, the objectives and methods, the high-level goal is, of course, both for the license applicant and the regulator to understand the safety performance and the safety features of the plant. In the previous picture, the four different grades of safety assessments, just to show a little bit some concreteness in the objectives and the methods, that the grade A would be concentrating on verifying detailed safety requirements, whereas B, C, and D grades would go from general safety requirements to high-level safety requirements, ending up in just verification of the safety principles in grade C, grade D, excuse me. And when it comes to the methods, grade A in this example would be a purely independent safety assessment with using own methods, own tools, own inputs. Whereas then in the grades B and D, the grading is regarding the methods, tools, and input data and results, and also from the regulator point of view, focus on the license applicants and the designers' processes, how this license applicant is doing their safety assessment. And based on this, then the regulator could also give some more credit on the work done by the license applicant. And then the key findings and conclusions. Really, an international and European design certification, that would be an optimal way to support an Estonian licensing process and a model. However, this is something that cannot be expected in the near future, or at least not on a timeline considered for the first SMR in Estonia. But I want to emphasize that this is definitely something that needs to be pursued. However, licensing efficiencies can be enhanced greatly through maximum utilization of existing safety case and PSAR, as well as the corresponding safety assessment done by an experienced, independent, and transparent foreign regulator. Whatever the case is, the licensee will eventually have the prime responsibility for the safety of the plant, and therefore the license applicant will need to demonstrate intelligent customer capabilities. And they need to be competent enough to undertake their own safety assessment of all the licensing documents. And in the same way, if the Estonian regulator chooses to maximize the use of a safety assessment of a foreign regulator, they still must be competent to, and also they must undertake their own independent safety assessment. And this is in order, for example, to verify the completeness and adequacy of the foreign safety assessment, to ensure that the local or site-specific features have been appropriately addressed, and finally also to assess the license applicant's specific matters. All the safety assessments should be based on graded approach, and from the Estonian regulator's depth of safety assessment when it comes to technology, that should prioritize deviations from the standard design or reference plant, and also the safety significance of the items. And this study presents one possible approach, and there are other ones existing and other possibilities, and any details can be further discussed and adapted depending on the framework where the model would be utilized. However, utilization of a standard design, PSAR, and a foreign safety assessment That is only possible if the regulatory basis and the safety standards in Estonia and the relevant foreign country are harmonized. And therefore, the Estonian legislation and regulations should set safety targets compatible with international practices, but they should avoid setting detailed prescriptive requirements. And in practice, this would mean some kind of endorsement of regulatory requirements of the foreign country. The use of graded approach could also be recommended for the codes and standards in such a way that the higher safety classes, the codes and standards of the country of origin could be used in them, whereas then the local codes and standards could be used in the lower safety classes. And this is especially considering the non-safety equipment and a long operating time, something that is seen beneficial. And what does this everything then mean? It means that there really needs to be cooperation between the Estonian and the foreign regulatory bodies, because significant human resources may be needed, and this might require government-to-government commitment. And finally, the suitability of the site envelope-based PSAR, and especially the availability of the PSAR and also other relevant licensing documentations that could be developed or would be maybe developed or owned by a foreign licensee as opposed to the reactor vendor, that must be ensured. And this is also applicable for the existing safety assessments. And with this quick run as an introduction to the safety study, I want to hand over the word to Helen.
Thank you very much, Nikki. It's now my great pleasure to introduce you to Fermi Energy's Licensing Advisory Group. This group was established in the middle of last year to oversee the work of Fermi in the areas of nuclear regulation and licensing. Our experts are drawn from and have experience working in countries and with regulatory bodies likely to have particular significance for Fermi Energy's SMR deployment plans, as well as having important affiliations with entities such as the International Atomic Energy Agency and the Nuclear Energy Agency of the OECD. So Nikki, if you could turn to the next slide. The members of our advisory group are Stephen Burns, the former chairman and commissioner and also general counsel of the United States Nuclear Regulatory Commission. And Steve is also the former head of the Legal Affairs Department at the Nuclear Energy Agency of the OECD. We also have Ian Grant, who is the former Deputy Director General of Operations and Director of Nuclear Safety of the Federal Authority for Nuclear Regulation in Abu Dhabi, UAE. And prior to his time in Abu Dhabi, Ian held various senior management positions with the Canadian Nuclear Safety Commission. We also have Juhani Hyvänen, who is the former Executive Vice President and Chief Nuclear Officer of Fennovoima in Finland. And prior to this, Juhani held specialist and management positions at the Finnish Radiation and Nuclear Safety Authority. And finally, we have Joseph Mizak, who is the former Director General of the Slovak Nuclear Regulatory Body, and also the former head of the Department of Nuclear Safety of the IAEA, and an expert regarding IAEA safety standards, WENRA safety reference levels, and the European utility requirements. Now, these few sentences certainly do not do justice to the impressive and extensive experience of this group of experts, and we've been really honoured to have them working with us. Now, the first task of the advisory group was to review and engage with us on the Fermi Fortum licensing study that Nikki has just presented. And we greatly appreciated the inputs and guidance obtained from our experts. Separately, but relatedly, I'm happy to announce that the advisory group has developed and endorsed a set of SMR licensing principles, which will be made publicly available today. These principles recognise that successful deployment of SMRs in Estonia and more widely are significantly influenced by the applicable licensing process and regulatory basis. They encourage a proactive and constructive approach to addressing licensing and regulatory challenges, which should be embraced by all stakeholders. And they broadly concur with the high-level findings of the Fermi Fortum licensing study. So you can see a copy of the SMR licensing principles here, and as I mentioned, they will be made public today. So again, we'd like to thank our advisory group for the work that they have done with us to date, and we look forward to our ongoing collaboration. And with that, Maria, back to you.
Nikki, Helen, thank you both. Thank you both very much for your contribution. Now, I would love to ask you questions, but unfortunately, I think we have to stick to the schedule of the day. So thank you again for your contribution. We're going to move on now and look perhaps further into the future and a bit broader. And the next speaker we have online is Stefan Kvist, who will talk about the security of supply to Baltics from Scandinavia and whether it is or is not in place. Stefan, I hope that you are also with us.
I hope so too. Are you able to hear me?
Yes, we can hear you and we can see you.
Wonderful. And can you see my slides as well?
Not quite yet.
Okay. Give me a moment.
There we go.
Okay. So, not sure if I'm able to change the slides, but I guess I will just give a wave. So good morning, everyone, colleagues and friends in Europe, and everyone who's listening in from around the world. I will be stepping back a little bit away from nuclear topics specifically for the next 15 minutes. I was asked by Fermi to look at the status right now and going forward for the security of supply for the Estonian and Baltic power system. So there is a report that will be made public after my presentation today that summarizes this. I will try to summarize some of the findings from that report now. Obviously, it will be quite a brief overview, but hopefully we'll have time to go through some of the interesting things. So if you could change the slide. Sure, or if I'm supposed to be doing that. Yeah, so just very briefly then for everyone who is on this conference, but maybe not so familiar with Estonia and the Estonian power system, it's historically quite unique and that it's been based almost entirely on local oil shale. And mainly the power production in the system has been from a group of power plants near the oil shale deposits around Narva. And until recently, until a few years ago, I should say, this was supported as kind of a resource for ensuring the local security of supply of electricity and energy for Estonia. So it was a system that was quite energy independent in that sense. However, oil shale is very, very unenvironmentally friendly and not so climate friendly in that it has the highest emissions intensity of any comparable electricity production method. And obviously it's not tenable to keep running a power system based on fossil fuels in general, and certainly not on one of the most emitting fossil fuels there is around. So consequently, from climate ambitions and also for the pricing of carbon emissions, the oil shale power production is shutting down. It's already been shutting down and it will continue to shut down. And what I was looking at in this little study is then what are the implications for the security of supply for Estonia and for the Baltic nations. So if we can go to the next slide. So in general, and this will be made more clear if you read the report, there are a few ways, if you summarize it, to ensure security of supply, which basically means that demand is met by production or imports. We can do that by having domestic dispatchable generation. That means power plants from which the production can be planned in the country. You can have domestic variable generation, which means production from, for instance, solar and wind farms locally. And then you can have imports. And the combined generation and supply from all of these sources should meet the adjusted demand that you have to ensure security of supply. So if we look first at domestic dispatchable generation, which is essentially these oil shale plants, one of the plants can also be fueled up to 50% by biomass. It's not only oil shale. If we look at what the situation is going forward with the domestic dispatchable capacity, this is in general throughout history how nations have secured security of supply, basically to ensure that you can meet your expected peak load more or less with plannable power in your country. In 2020, last year, there was enough available capacity assessed by the transmission grid operator to meet peak demand, even more than that. So there was no problem with energy security supply then, if everything was working fine. Now, this year, there will be decommissioning of oil shale plants, and going forward, this is going forward. So there's no published plans, at least by the study of Ellering, the transmission grid operator, of any construction of new dispatchable power generation, but the dispatchable power generation that is there is retiring. So you see from 2020 going out to 2030, even 2035 here, how the available capacity assessed by the transmission grid operator is reducing year by year. If we go to the next slide, we can compare this available dispatchable capacity with the expected peak load. So that's the expected maximum hourly consumption of electricity per year. It's quite flat if you see projections into the future, if you compare to other nations in the Nordic region. So this might be a little non-conservative if we assume that, for instance, the Estonian transport sector will transition to electricity and there will be electrification across the industry. This might actually grow more, but these are the reference numbers. And you can see there's a huge gap developing between the available dispatchable capacity and the expected peak load. So if we graph that out, the gap itself on the next slide. So in 2020, you could see that there is more dispatchable capacity available inside Estonia than the expected peak load. Already this year, that's changed. So not just on an annual basis or a weekly basis or a monthly basis, but this one looking at the peak hour. Even if you run all the plants that are dispatchable and they have the availability that you assume, Estonia cannot support its peak load by domestic dispatchable generation. In 2023, this situation gets quite a lot more dramatic. It goes down to almost 700 megawatts into the negative. And in 2030, with further retirements, it goes negative to on about a scale of 1 gigawatt, which is maybe not sounding so dramatic for people from larger countries, but that should be seen in relation to the peak load of about 1.5 gigawatts. So most of the power will need to come from something else, which is a quite unique situation, actually, and a quite, as we will see, maybe a risky one. Okay, if you go to the next slide. So what is happening in Europe and also in Estonia to some extent, and is expected to be happening, is an expansion of variable domestic generation. So mainly wind power in the case of Estonia. It's not a very sunny place. And this also can contribute to some extent to security of supply. It's, I will show to what extent, but obviously this is a production resource available in the country and needs to be assessed as such. So if we go to the next slide. So Estonian variable renewable generation is expanding. It will be, according to the ENTSO-E projections, at least able to generate about at least a third of annual demand by 2030. So demand is growing, but also the capacity of wind and solar is growing. You can see the current installed capacity in 2021 in the graph below, and what ENTSO-E is projecting might happen to 2025 and 2030. So quite a large expansion of this type of capacity might happen. The grid operator currently gives zero capacity credit to variable renewables, such as solar and wind, so they are not currently assessed in security of supply. Maybe they should be. We can look at that if we go forward. So if we take the next slide. Yeah, so if we can pull this out a bit more extreme, as is politically popular in Europe today, to look at what would it look like if we had 100% on an annual basis supply by variable renewables, and even 150%. How much, if we had capacity installed in solar and wind to be able to annually generate all the demand, or even 150% of demand, how much would that displace the need for dispatchable capacity or imports? So what kind of security supply implications does that have, that production capacity itself? So how do we look at that? Very quickly, if we go to the next slide, we looked at data, weather data, basically reanalysis of weather data for 35 years, from 1982 to 2017. And the hourly capacity factors of onshore wind, offshore wind, and solar PV, adjusted for those weather conditions, but using the latest technology. So the latest wind turbines, both onshore and offshore, but with the weather conditions that Estonia has historically experienced, and hourly load profiles adjusted for primarily the temperature profiles historically. And the question is, the relevant question here is, what is the biggest difference between the output of variable renewables and the demand over a certain time period? We looked from 1 single hour out to over 4 weeks. What we haven't done is a full probability study on this. It's purely deterministic, just looking at what the biggest gaps in supply might be. If we go to the next slide. So I would encourage everyone who's interested in this topic to go back and look at the uploaded slides from this presentation, because this graph is a bit complicated. It might not be enough time to explain it fully. So what these two lines, the 100% VRE and the 150% VRE lines are showing is how much average firm power, dispatchable power, do you need over a certain time period. So over a single hour, of course, there might not be any wind or sun at all. So you need averaged over a single hour, basically, to be able to meet the peak load without any contribution from solar or wind. If you go out to a longer time period, it's very unlikely there will be no sun and no wind over a very long time period. So the average need for dispatchable capacity obviously reduces, goes down. And if we look over a 1 or 2 week period, 2 week period is illustrated here just to give a sense of what needs to be in place, even if you do have 100% of supply annually from solar and wind. And essentially it does a little bit over a long time period, but you can have, in a small country like Estonia that's far in the north, basically very, very little wind and essentially no sun of note over even a 1 or 2 week period, during which something else needs to step in, obviously. Next slide. Yeah, so something else is excellent to combine with solar and wind is obviously large-scale energy storage. So you might not have generation that week, but you might have had it the week before and you could store it. There's a very interesting project called Energia Salv, which plans to build a pump hydro storage facility, which will alleviate this problem a little bit and increase security of supply. So next slide, if we integrate all of this and look at what a week might look like from a security supply perspective, if we do get the next slide up. So this is a challenging weather week, which is a week with high load. So it's probably in the winter, yes, it's in January. It's got high demand, and we have very little solar and wind output. We are looking at a system designed to be able to generate 9 terawatt hours per year, so all of Estonia's needs over a year. But during this week, it's neither sunny nor windy. And even in a system like that, we're still missing about 1 gigawatt of power locally, so over an hour, and we're missing up to 100 gigawatt hours of energy over the week. So that's a deficit that we need to look at. We also did the same study for the Baltic integrated power system, so including Lithuania and Latvia, and the huge Lithuanian pumped hydro storage facility. And if you run into a bad weather week also in this system, you will discharge all of the storage you have roughly in the first day, and then you run into a deficit which needs to be covered somehow. And somehow it's quite obvious we can show that domestic dispatchable generation won't do it. Dispatchable variable generation won't do it. It's imports that is supposed to do it, and we will look at that very briefly now. If you go to the next slide. So what is typically looked at and commented on, as far as I've seen and read about Estonian security of supply, is whether there's enough capacity to import to fill these needs. And the answer to that, on a very basic level, is yes, there will be enough transmission interconnecting capacity to other countries, in the case of Estonia, Latvia, and Finland, to cover the import needs. So on a purely physical infrastructure level, I would agree, this assessment would agree that there's enough capacity to be able to do it. The problem, which we have assessed in the report, is, and if you go to the next slide, is that you don't only need enough cable capacity, you also need someone available that has excess generation capacity to be able to export to you when the system is stressed. And so for what's happening that's interesting in the Baltic region, obviously that will have huge impact, is a disconnect from the Russian, Belarus, and Kaliningrad systems, and no more electricity trade by the end of 2025. And what's remaining is basically to import in two different northern routes from Norway and Sweden, or in a southern route from Germany and Poland. So essentially, security of supply in Estonia boils down to whether these two routes can be relied upon to supply Estonia in a time of stressed high load, low VRE output. And if we look at this, it is looking a bit risky, this strategy. There are many security of supply reports from the various grid operators in the northern region. What we're looking at here at the graph is one by the Swedish transmission system operator that's assessing this. And basically by 2023, in a stressed hour, they're saying basically only Norway can be relied upon to have any export capacity. So neither the northern routes nor the southern routes will have really any export capacity summed up over the route to get any power to Estonia during a stressed period. This situation is going to get worse. Norway is building large new interconnectors to other places. So their quite small excess capacity will be hard to bid for. And the demand, as Torbjörn explained, in Sweden is set to increase by up to 100 terawatt hours over the next 25 years per year. And Norway will also be increasing, and likely every country will need to increase electricity consumption to decarbonize. At the same time, the dispatchable capacity that's available is closing in neighboring countries. All of Germany's remaining nuclear plants will close. Sweden has closed 4 reactors quite recently, and obviously all coal power capacity will need to close in this region fairly soon. So if we go to the next slide. When I put together this presentation, I had a look at the data, and it was a very nicely illustrating time period, actually. I am in England right now, and we have a kind of a winter wonderland outside my window. We have snow on the ground for the first time since I've been here. It's wonderful. And it's cold everywhere. And during the time I made these slides, there was essentially no wind and no sun in Northern Europe. And so the Nordic region as a whole was importing enormous amounts of electricity, even as sometimes no individual nation in the north was a net generator of power. So this shows from the last of January to the 2nd of February when I made this, an import need regionally up to 7 gigawatts. And this was supplied primarily by Russia and Belarus, and by German coal and nuclear plants, and by Polish coal plants. Obviously, none of these sources will be available quite soon. German nuclear is shutting down. German coal and Polish coal will need to shut down for climate reasons. And the Baltic region is disconnecting from Russia and Belarus. So if it looks a bit risky today, it's not going to be better. So a summary, and I'm sorry for rushing through this. I have tried to cover a lot. Please sit down with the report if you find this interesting. The summary from this quite introductory, let's say cursory exploration of Estonian security supplies is a quite risky strategy that's being employed. The economic impacts are not just short term, which is the cost for power in a stress period and the risk of blackouts, but also long term, because if you have a power system that can't really ensure security of supply, you will hurt the willingness to invest from industry. Now, the import dependency that's developing in Estonia on all timescales, from a single hour to multi-year import dependency, makes the case for new dispatchable low carbon generation very, very attractive. And I would say, especially for combined heat and power plants, they can also do something like district heating. So from a security of supply perspective, it seems like an ideal opportunity, essentially as soon as practically possible, for something like up to 600 megawatt electric equivalents of SMR, ideally cogeneration enabled by the early 2030s, as soon as possible, basically. There's a case and there's a need for it to complement other low carbon sources like wind and solar. So thank you very much. I hope I kept roughly to time and didn't go too fast to be understandable.
Stefan, thank you very much. It is indeed interesting. If you don't mind, just one brief question. Hearing what you have to say, the question is really, well, is one SMR or is nuclear power in the capacity of 600 megawatt electric enough?
I think there will be a combination of solutions. There's a real easy case to make for something on the order of 600 megawatts, which will be able to run completely base load. I think, as you've seen, the net need, the net requirement for power that's not covered is far higher than 600 megawatts. So if you do run into a period where you've basically decommission all of the oil shale plants and you have 600 megawatts of SMR, no, you will not be able to cover security of supply. But there could be a combination of other ways to solve that problem, including more of these pumped hydro storage facilities, for instance, or even more nuclear power capacity, or more short-term solutions, such as maybe something biogas or biomass related. So 600 megawatts is probably a safe base case where you have an extremely strong economic case. There's no kind of limit there.
Stefan, thank you very much. It's a pleasure to have you with us. Teistele aga tuletaks meelde, et nii nagu on programmis ette nähtud, võtame me nüüd kiire pausi. Meil on ette nähtud pausiks 10 minutit, nii et kasutage seda aega targasti, tooge endale uus tass kohvi ja tehke võib-olla paar kükki, et vereringlus käima saaks. Ja näeme uuesti 10 minuti pärast ehk minu kella järgi kell 12.04.
I know it's been long assumed that those who champion the environment are opposed to nuclear power. But the fact is, even though we've not broken ground on a new nuclear power plant in 30 years, nuclear energy remains our largest source of fuel that produces no carbon emissions. To meet our growing energy needs and prevent the worst consequences of climate change, we'll need to increase our supply of nuclear power. It's that simple.
Énergétique et écologique passe par le nucléaire. Pourvu que l'on progresse sur la gestion des déchets, sur la sûreté, et je vous sais là aussi pleinement mobilisé, l'énergie nucléaire est une énergie décarbonée, une énergie sûre.
You know, the weather is already very uncertain. It just gets worse in a negative way.
Do you think politically nuclear power will ever be something that will be a completely viable solution? Because it solves a lot of the problems.
If people were rational, yes, which means there's like a 30% chance. Nuclear, the current reactors actually have a better safety record than any other source of electricity. They are not the best.
Except that when there is a problem, there's a problem.
Chernobyl is the only case where you have radiation release killing people. Coal kills a lot of people. Natural gas pipelines blow up and kill people. Per kilowatt hour, it's the safest. But I don't care about that. Those reactors can blow up. You can design a reactor that is not capable. That is, there's no high pressure in the reactor anywhere. These existing reactors have lots of high pressure, and they need humans sitting there pushing buttons. You can design a reactor that by multiple physics principles, that the radioactive material never leaves the reactor. You have, you know, the heat pool and the low pressure anyway. And so people at least should be open-minded that a next generation reactor can have far better economics, far better safety, you know, no proliferation, no waste problem. But we need lots of innovations to solve climate change. If we have certain other breakthroughs like in energy storage, you can actually create a zero-emission grid without nuclear. But it's way more straightforward. It's way less expensive. It's way quicker if a meaningful part of it is this breakthrough new generation reactor.
It's like half the people that were out there, you know, saying, you know, no nukes and shut down the power plants, they're now realizing that some would say, you know, nuclear is the best way to go for energy for the future. So I think it's natural to re-examine your beliefs as you age up.
Senator Booker, I wanted to ask you about nuclear energy. You are a proud proponent of nuclear energy, have argued it's necessary to wean us off the fossil fuel economy. But you have a lot of environmental activists who are scratching their heads at your support for nuclear energy, particularly around the issue of nuclear waste. Here in South Carolina, for example, there are 35 million gallons of nuclear waste being held at a nuclear reserve south of Aiken. Environmental activists have been fighting it for years. You've got Savannah River. And of course, we're talking about communities, primarily low-income communities of color, who are dealing with nuclear waste in their own backyards, from New Mexico to Yucca Mountain to right here. What is your answer to the fact that there is no solution in dealing with nuclear waste?
Well, first of all, you're a little bit mischaracterizing my views. I'm a realist that tells you right now the biggest existential threat to humanity is climate change. 50% of our non-carbon producing power right now is nuclear. And so as some of my other opponents want to do is just get rid of it, it's going to push us back to being more reliant on fossil fuels and make this, our ability to reach our climate goals, impossible. We saw what happened in Vermont when they cut down the Yankee plant there. Their carbon footprint expanded pretty significantly. So I look forward to phasing out nuclear waste and nuclear energy. But to do it right now, when we are in a race and have a 12-year race to meet our climate goals, the damage done to poor and vulnerable communities is significantly worse coming from climate change than it is the crisis of nuclear energy. If you want to weigh your poisons right now, the one that's coming towards us like a barreling freight truck of climate change, the one that my community in Newark is feeling right now because temperature rises, asthma rates that are off the charts. And let me tell you something about asthma. As a guy that knows what it's like in emergency rooms with black children dying at 10 times the rate than white children of asthma complications. So for me, nuclear energy, it's just common sense to me right now.
To build new power plants?
No, well, let's be clear. The nuclear energy of the plants we have now, designed in the 60s and the 70s and the 80s, is very different than the new modular nuclear energy plants that are being proposed. Now, those actually have a much different, they can actually take spent fuel rods and re-engage them for usage. The frontiers of nuclear science is not something we should just shut down. We should continue to investigate. Is there going to be eventually a safe way to do this? So I don't mind exploring the future. I'm one of these people that considers myself a futurist. Why? Because you have two choices in life: to let the future happen to you, or to shape the future and make sure it happens in a way that's just. So this to me is a very, very simple equation. Is I've got a 12-year problem to solve. And if anybody wants to get rid of nuclear energy, tell me how you are going to replace 50% of the non-carbon producing power that we would have right now. Because what you're going to do, you're going to send us back to coal and oil, and I refuse to go backwards in the cause of environmental justice.
The first thing we must do is to say goodbye to fossil fuels. In Finland, we will build the world's first fossil-free welfare society. Our long-term energy policy goal is to phase out the use of fossil fuels in the energy sector and move towards an emission-free energy system. In electricity production, we have already taken big steps. In 2018, nearly 80% of Finland's electricity production was based on carbon-free energy sources. 46% of energy was produced by renewables and 32% with nuclear power. However, as a country with cold winters, heating is a big issue that we have to focus on. In the same year, 2018, 53% of district heat was produced with fossil fuels and peat. This is why our government is investing significantly in policy measures to decarbonize our heat production.
Hey guys, so a lot of you have been asking about my makeup routine. The most important thing is to make sure you wash your face really well because we want those pores as clean as we want our electricity. And the best way to get that is to use this cleanser called Stop Shutting Down Nuclear Plants for Christ's Sake. It's carbon-free, emission-free, pollution-free electricity. Then I use this plant-based serum called When a Nuclear Plant is Shut Down, It is Replaced by Fossil Fuels. That's bad. And I just rub this on my face because we all need some goddamn moisture in this quarantine. Then I put some foundation and conceal, like Germany trying to conceal the fact that they still have one of the dirtiest electricities in Europe, probably because they focus on shutting down nuclear instead of coal plants. Now let's do some blush, or we can just naturally blush by thinking of all the countries who already have pretty clean electricity, including France, Sweden, and Finland. They must be doing something right, but God, what could that be? So I have a crazy idea. How about instead of shutting down perfectly fine nuclear plants, we focus on shutting down coal or gas plants, which actually cause climate change. Oh, and don't forget the mascara, because it's not a look without the mascara. Mwah!
I know it's been long assumed that those who champion the environment.
Tere tulemast tagasi. Loodan, et teie paus oli värskendav. Järjekordselt ei võta ma väga palju teie aega, vaid lasen järgmise osa sisse juhatada hoopis meie partnerile Helen Cookil. Helen, I hope you're with us. And
yes,
I would really like you, very good, and I would like you to introduce the next section.
Thank you very much, Maria. Well, we certainly have a tough set of speakers to follow after those we heard from during the break, but we will see what we can do. So it's my great pleasure to introduce an initiative that draws upon the work that Fermi has done this year on the subject of SMR licensing, but which I think really reinforces a number of important themes, both arising from that work and more generally in the context of seeing nuclear energy successfully deployed in decarbonised energy systems. Themes such as the significance of collaboration within the nuclear industry in efforts to resolve what are common challenges and to achieve common objectives. Also, the importance of forging alignment between industry and with those entities that perform the task of regulating the activities of the industry. Successful deployment of SMRs requires all stakeholders to mutually identify these issues and challenges and to combine in our efforts to solve them. To that end, representatives of the nuclear industry, many of whom may be potential future customers of SMRs, come together today in support of a set of principles set forth in a document that we have called the Tallinn Declaration on the Future of SMR Licensing. Now, recognising that we can't all be together in person in Tallinn today to sign the declaration, I'm going to read out the text, summarising it in places, and then ask a representative of each of our signatories to confirm their support for the declaration and to give some brief remarks. So first, let me put the declaration on my screen. Right, so the Tallinn Declaration on the Future of SMR Licensing states, well, gathered virtually, but wishing we could be together in Tallinn, Estonia today, noting the formation of the European SMR Alliance in January 2020, with the goal of facilitating widespread SMR deployment in Europe by the 2030s, recognising the urgent response needed to meet the EU's commitment to achieving carbon neutrality by 2050, believing that SMRs can make a significant contribution to low carbon energy mixes in the EU and globally, respectful of the role of nuclear regulatory bodies in ensuring safe, secure and peaceful uses of nuclear energy, cognizant of the impact of nuclear licensing processes and regulatory matters on the business case for SMRs, their design criteria, development of supply chains, and overall viability of SMR deployment, conscious that effective and efficient utilisation of experienced global human resources in reactor licensing is necessary, and convinced that SMR vendors and future SMR licensees must proactively engage with regulators in their own countries and in key jurisdictions around the world to promote the optimal way forward for SMR licensing. Hereby support and will promote the following principles of SMR licensing. A pragmatic approach to SMR licensing must be employed to overcome licensing and regulatory challenges and to reduce SMR project risk relating to nuclear regulation and the licensing process. SMR design standardization must be facilitated to the greatest extent possible. In developing or updating the regulatory framework applicable to SMRs, host country regulatory bodies should seek to facilitate regulatory harmonisation. Regulatory framework should be based on the IAEA safety standards and implement EU nuclear safety directives, as well as give due consideration to compatibility with relevant vendor or reference plant country of origin or other experienced nuclear countries' regulatory regimes. As the licensee will have prime responsibility for the safety of its SMR plant, the licence applicant will need to be an intelligent customer, competent to undertake an independent assessment of the safety case and prepare the licensing documentation prior to its submission to the host country regulatory body. Licence applicants should seek maximum utilisation of an existing safety case prepared for a standard SMR or a reference plant design. To the extent the host country deems it appropriate in its particular circumstances, the licensing process should enable host country nuclear regulatory body to achieve maximum utilisation of the safety assessment of the standard SMR or reference plant design conducted by an experienced, independent and transparent regulatory body originating from the vendor or reference plant country of origin or from another experienced nuclear country, thereby making effective use of experienced global human resources in licensing and continuously building upon the safety case for the relevant SMR. In all circumstances, the host country nuclear regulatory body maintains sovereign and independent decision-making authority. The host country nuclear regulatory body should conduct an independent safety assessment based on a graded approach that prioritises safety significant items, deviations from the standard SMR or reference plant design, and site-specific and licence applicant-specific matters. Close cooperation between the host country nuclear regulatory body and the nuclear regulatory body of the relevant vendor or reference plant country of origin or other experienced nuclear country is essential. Cooperation mechanisms which enable mutual recognition and acceptance of regulatory approvals of experienced, independent and transparent foreign regulatory bodies should be pursued. A mechanism for international design certification should also be pursued and made viable in the future. And finally, the signatories will consider the work being undertaken by the IAEA, the NEA, IFNEC, the WNA, and the EUR, among others. Now, with that, I am going to ask one by one for the signatories to confirm your support for the declaration and give some brief remarks. So first, could I please call upon Kalev Kalamets from Fermi Energia in Estonia.
Hello. Hi to Australia. So Tallinn calling here, and indeed Fermi Energia supports that declaration, and I can confirm that we take very seriously the challenge of developing Fermi Energia systematically over coming years into being intelligent customer, and we seek cooperation with Estonian government to implement the principles in this current declaration. So looking forward to many years of interesting work with you and our partners.
Thank you very much, Kalev. Next, Olli Kaimalainen from Fortum in Finland.
Yes. Hello. From Fortum side, so we are happy to join this declaration, and we think the licensing risk is one of the biggest challenges regarding possible deployment of SMRs, and I consider this declaration as an attempt to emphasize this importance. And the main concern here is in particular the fragmentation of the regulatory and other national requirements. And just to emphasize that, of course, the nuclear safety as such cannot be compromised. So this is not to suggest to relax the expectations of safety performance itself, but this has to be done in a smarter way. And so we simply cannot afford redesigning an SMR for each country or redoing all the paperwork for each country, which pretty much is what has been done in the recent new build project. So this would kill the idea of SMRs. And so there is work ongoing currently on harmonization and of requirements in many international organizations, both on the regulatory side and on the industry side. And this is very important to continue, and it's very important to go deeper in that. But on top of that, we need to find ways to do the licensing in a smarter way, I would say, and without having to completely redesign the SMR for each country. This is the most important thing. And so hopefully this declaration encourages that work. Thank you.
Thank you very much, Olli, and thank you also for Fortum's work on the licensing study that we did last year. Next, I'd like to call on Marcus Eriksson, the representative of Vattenfall from Sweden.
Hello, Helen, thank you. Can you hear me?
Yes, we can.
Okay, thank you. Thank you for preparing this common action. Yeah, and yes, certainly, Vattenfall supports the declaration. We think it is well written and it aligns with Vattenfall's view on this topic. We know that updating the regulatory framework takes time, and there is an urgent need to engage and communicate on this subject. The declaration itself identifies key issues that we agree are vital to deal with to overcome licensing and regulatory challenges in order to reduce the overall economic risks of an SMR project. International harmonization of licensing requirements needs to be deepened. International design certification must be pursued. Deviations from reference plant design must be avoided. And SMR cannot be afforded to be redesigned for each country. And these topics are relevant for Vattenfall since we believe that small modular reactors holds a future opportunity for achieving deep decarbonization in Europe as well as in Sweden. On the other hand, the declaration puts a finger on some of the bottlenecks that we need to overcome to enable this technology to its full extent. So for these reasons, we support the declaration, and we think it summarizes appropriate principles for common actions that we are committed to promote. Thank you, Helen.
Thank you very much, Marcus. Next, I'd like to call on Anna Sertua, representing Tractebel from Belgium.
Thanks, Helen. Can you hear me okay?
Yes, we can.
Great. Yeah, so, well, on behalf of Tractebel, I can also confirm that we are proud to be a signatory of this declaration. I think the colleague before me just summarized it perfectly. This is a document that highlights that sound licensing is successful. That's a key step to take for the industry. And I think the declaration itself correctly points out some of the necessary ingredients to make that happen. For example, I believe that simplicity and pragmatism, which somewhat is inspired from the past in replicating the successful case, the successful safety case from the country of origin, is something that really is necessary. And so I believe the declaration correctly highlights that. There are other elements that are really important in this. The graded approach, the concept of making things in a smart way, giving the importance where it matters and not necessarily trying to do everything as deep as we used to do it in nuclear, but putting the effort where it's safety significant. And I would say more than that, what I really like into this declaration is also the fact that it is a first attempt for some of the stakeholders from the nuclear industry to come together and say, well, we want to move forward with SMRs. We want to do it in a smart, simple, pragmatic way, which is, I believe, a really important step. And so I really applaud Fermi's Energia courage and Khaled Kalamet's leadership on being a trailblazer for SMRs to become a reality in Europe. I think it's really important, and it's important to also to highlight it because the 2 years that this project has really taken shape right now, we kind of seeing the necessity of that kind of leadership and that kind of trailblazing. So I'm really pleased that our joint work with Fermi Energia has resulted in such a declaration, and also resulted in the signing of a new agreement that I believe will accelerate the collaboration between Tractable and Fermi over the coming years to really make the deployment of SMRs a reality in Estonia and beyond. And I believe it also confirms Tractable desire to be at the side of Fermi Energia and the other players in Europe with skin in the game to make that happen, because I do believe that Europe needs that if we want to make the zero carbon transition a reality and a success. Thanks.
Thank you very much, Anase. And I also personally concur with your comments in applauding the leadership of Khaled Kalamet and all the founders of Fermi Energia in not only this area, but so many areas which we are discussing today that will be so important to the future of SMRs. So thank you, Anase. And could we move now to Rafał Kaspro, who is representing Syntos Green Energy from Poland.
Thank you, Helen. Good morning, everybody. As a Syntos Green Energy, we strongly support declaration, and thank you very much, Helen and Kalev, for preparing this. I think it's great work. We all agree here that country of origin idea is a great path towards which can solve a lot of problems we already consider. But I would like to say that we all agree here what should be done, and we have a similar point of view. And I hope that with this declaration, we reach people who not fully agree with us, and decision makers and politicians on both European and national level. And we desperately need to communicate these to this group of decision makers. Thank you.
Thank you very much, Rafał. And next we have Peter Zawodski from ČEZ of the Czech Republic.
Good morning. Dear colleagues, it was mentioned here several times that the whole Europe has a common and I have to say quite difficult or not easy task to be carbon neutral in 2050. Some countries with optimal environmental conditions will rely mostly on renewables like wind farms offshore and big hydro in Alps and so on and so on. But approximately half of the EU will have to develop nuclear to extend the design life of the existing power plants, build a new one, including SMRs. Of course, there will be strong opposition from anti-nuclear countries, and Rafał mentioned it. We are on the same page, and we understand each other, but there are still anti-nuclear countries. There will be opposition from them, and we have to really work together as, let's say, nuclear countries. And we have to face most way for construction of the new nuclear, which means a common approach to the politicians, to the European Commission, not only for licensing, which is key of the Tallinn Declaration, but also financing. You know about the discussion in the EU or European Commission about the taxonomy and how difficult it is to reach agreement that the nuclear should be part of the solution. We have to discuss supply chain and use, let's say, industrial standards for building power plants, not to make it, let's say, too complicated. And definitely, as we are here on the conference, we are not competitors. We really have to work together to really reach new construction of SMRs in Europe to replace fossil power plants. For example, in our country, the Czech Republic, we have 10,000 megawatts, which is half of the installed capacity in coal, and we will have to replace it. We will have to replace consuming gas and other things in transportation by electricity. So we have to increase installed capacity, and it's a huge task. So let's work together. Let's find a way how to do it on time, on budget, and prove that the nuclear is really the part of the solution. So finally, we as a chess group fully support the Tallinn Declaration. Thank you very much.
Thank you very much, Peter. And next, could I please call upon Alan Tatu, representing Nuclear Electrica in Romania.
Greetings to everyone. Nuclear Electrica is fully supporting this declaration. For us, it's very important to lower the risks of the licensing process and the cost of the electricity that would become from a possible SMR in the future. Because in European Union, as you all know, we are working in very competitive markets. So it's very important that we plan in advance to lower any risk we can foresee. I think levelizing the licensing processes among surrounding countries or region countries can work to the benefit of all, because the fundamentals that stay behind the SMR development is to deploy fleets and not just the singular units in each country. That won't work financially. Nuclear energy is still expensive. It's an expensive proposition. So for countries that have small grids like or relatively small grids like Romania or Estonia or Bulgaria and so on, it's hard to make a business case for a large fleet. So we have to cooperate regionally, not just in this area of the licensing, but also in the areas as were mentioned before, supply chain, financing, and so on. So again, we fully support this initiative and like to support any other initiative in the future.
Thank you very much, Alan. And next, could I please call upon Matthijs Bekkers from the Elise Foundation in the Netherlands?
Yes, thank you very much, Helen and Kalev, for putting this together, this brilliant declaration, which we wholeheartedly support. The major reason for doing this is speed. Climate change is a pressing matter. We need to stay below 1.5 degrees, at least that's what we all agreed upon in Europe. And that's simply not going to happen if we don't manage to deploy nuclear power plants in a quick and effective and cheap fashion. And I think that this declaration is a good step forward in this regard. Thank you.
Thank you very much, Matthijs. And last but certainly not least, could I call upon Sarah Cullen, representing 18 for Zero from Ireland?
Hi, can you hear me?
Yes, we can.
Cool. So thanks very much for having us. 18 for Zero is a small group of professionals, and we're working on a voluntary basis to remove the legislative bans on nuclear power development in Ireland. So we're at the beginning of a journey, and we're fortunate to benefit from a very strong collaborative network in Europe, which has shown us fantastic support.
We greatly value our cooperation with Fermi Energia and the European SMR Alliance, and we believe that this declaration on SMR licensing is a fantastic initiative and resource which we fully support. For us, this is a concrete step in the planning for nuclear development in Ireland, and it forms an excellent template for future work in the area of licensing. But more than this, it's something tangible to prove that we're not alone in our thinking and that there's a wave of new nuclear development across Europe, and this is something that all countries can benefit from. So we look forward to our continued work with Fermi Energia and the European SMR Alliance into the future, and we fully support this declaration.
Thank you very much, Sarah. As I mentioned, the declaration will be made public today and available from today. Sarah, could you stay on the unmuted button side here? Because I have a question for you. How important do you believe regulatory and licensing matters are in your conversations around lifting the nuclear prohibitions in Ireland?
Yeah, so Ireland's interesting because we're a few steps behind everyone in that regard. For us, it's really important to have these sorts of initiatives. There's something kind of concrete we can use now to begin to address nuclear power development in Ireland and to reduce risk. Having a kind of good licensing framework now gives confidence that we could use SMRs in the future in a timely and cost-effective manner. And yeah, this sort of initiative creates more certainty around timescales and the requirements we'd need for licensing. And that's really crucial for us to make our case to support nuclear.
Great. Thank you, Sarah. I now have a question to our representatives from the established nuclear countries. Perhaps Alan Tatu from Nuclear Electrica would like to take this one. Do you see the optimal licensing process for SMRs being different in established versus newcomer nuclear countries? Or do you think that all can benefit from enhanced efficiencies in reactor licensing?
Thank you for the question. I see here a challenge and an opportunity at the same time. So for countries with established nuclear industry, the regulatory body already have been, let's say, I'm repeating myself, established based on what technology was adopted a while ago. For example, CANDU technology. So the licensing framework for us is pretty much tailored for CANDU technology. So for us, it's a challenge to adjust to new technologies. So sometimes changing something is, it takes more time than developing something new. But at the same time, I see an opportunity here to work with countries that will embark in the nuclear industry, building nuclear power plants, because they start from fresh ground, and they can develop more flexible licensing processes from which we could learn and collaborate to also adopt such, let's say, amendments to our already established license framework. It's more to talk about here, but I was in the just.
Of course, thank you very much. And maybe one final question then to a newcomer nuclear country. And Rafael, maybe I'll put you on the spot if you're available to answer this question. What would you like to see the experienced regulatory bodies, for example, the US or Canada, do to support SMR licensing in a newcomer country? What practical mechanisms do you think would be helpful?
Thank you for this surprising question. Yes, definitely NRC and Canadian regulator are leading the role in SMRs right now. We all know that OPG decision to deploy SMRs soon will be important, let's say crucial. US NRC has most important experience. So I think that the, let's say, policy towards country of origin and bilateral agreements with the European countries could help a lot. I mean, country of origin recognition, bilateral agreement between individual countries, because it would be probably hard to achieve this on European level. But this is what is possible to do. For example, agreement between Estonia, let's take this brave country, and the best SMR developer in Europe, Fermi Energia. Let's say that it would be possible, especially I hope with the current administration in US, to achieve bilateral agreements supporting recognition of the SMR's licensing provided by Canadian and US regulator. It would be extremely important to achieve this.
Thanks, Rafael. So in conclusion, may I thank on behalf of Fermi Energia all of the other signatories and their representatives today, not only for your contributions to the declaration, but of course for your support of it. We certainly look forward to working with you going forward. And if I could just say in conclusion, who needs Bill Gates or President Obama when you have the knowledgeable and charismatic speakers representing the European nuclear industry? Thank you very much. Maria, back to you.
Helen, and everybody involved, obviously, thank you very much for that segment. Uplifting news as always. And I'm very interested in having you point out the speed of development, because I don't know if you're aware, but Estonians can put up with a lot, but are ultimately an impatient nation, and somehow we're always in a hurry someplace. So I think this is a pretty good segue to our next speaker, who will try to explain to us, well, how quickly could we build an SMR in Estonia? Let's see what he has to say. Claes Andersson from Vattenfall. I hope that you're on the line with us.
Yes, I think so.
Welcome, Claes. We can see you,
Yes.
and we can hear you.
You can see me and hear me, I
Yes.
understand. Yes, thank you for the introduction, Maria. I will also thank you for the opportunity to participate in this conference. My presentation will summarize a study on constructability. The study was carried out last year, and it's based on open sources and information provided by GE Hitachi. A working session with experts from GE Hitachi has also been an important part of the study. The study has also been reviewed by experts from Vattenfall. And the presentation will cover the following topics. First, a description of why SMRs have the potential to contribute to a nuclear new build, and how well a deployable SMR will live up to these expectations has been investigated by reviewing GE Hitachi's BWR X300. The results from the design assessment will be presented, and a likely project in Estonia has also been assessed, and an estimated timeline will be presented. The conclusions will be summed up in the end of the presentation. So, start with some basics. As you all know, new nuclear is expensive and needs to be cheaper in order to attract investors. Assessments of poor and expensive nuclear projects show that the investment cost is determined by indirect costs and interest. So a predictable and fast construction is therefore crucial to make new nuclear affordable. This can be reached by implementing identified key drivers and lessons learned. It is common sense that the low-cost project can be reached by simplification and standardization of the design. In addition, project risks must also be managed in an efficient way. Building light water SMRs is the response from the nuclear industry and might reach even lower cost levels. The smaller size and the use of passive safety system has the potential to make them very simple. And the smaller size will also reduce the project risks. Also, pushing standardization to the next level, as we heard this morning, will definitely mitigate both licensing and construction risks. One central idea is to build the smaller nuclear units in a modular manner, and this will lead to a shift from on-site construction to off-site manufacturing. An important assumption is that modular construction of SMRs will be cheaper than larger plants. So, in other words, the economy of scale will be handed over from the size of each unit to the number of units. So, how well does a deployable SMR live up to the expectations on a short construction time? How fast can it be built? This slide shows some basic facts about GE Hitachi's design, the X300. And this is the design we have used as a basis for our assessment. The design is in many respects a small boiling water reactor. And the design leverages GE Hitachi's earlier reactors. The technology is proven and has a simple process. The plant volume has been limited. The reactor has natural circulation, and the heat removal after an event is passive. It is demonstrated to be cheap when compared with other designs. The current status is that there are ongoing licensing activities in the US, in Canada, and in the UK. Licensing discussions have also started in Poland. And the first unit is planned to be in operation in 2028. So this slide then presents how well the X300 meets the expectations on a simple and standardized plant design. To start with, the X300 uses very simple process systems and natural circulation. The design also shows a drastic reduction in plant layout compared with a large nuclear power plant design. The X300 shows a high degree of standardization, both on plant and equipment level. The reactor is in many respects a small BWR that uses standard BWR fuel. The reactor and its safety-related items will be manufactured and integrated in accordance with proven nuclear standards. Also, the manufacturing and integration will be made by an established global supply chain. The smaller size enables that many off-the-shelf components can be used for the non-nuclear safety applications. Finally, the turbine island is standardized and will be integrated by a proven supplier. So when it comes to modularization, the BWR technology is modular in its fundamental design. I think that's important to reflect. It integrates the major components of the reactor coolant system. The previous GE Hitachi designs will set up the basis for the modularization of the X300. And that strategy is that modularity will be introduced to an extent that is economically viable. And this includes the construction of the reactor building using steel bricks, as you can see in the figure. The first-of-a-kind unit and some numbers after that unit are likely to be stick-built on the site to a greater extent than the later and more mature units. And there will not be any dedicated module factories unless a large number of X300s are on simultaneous order in a region. And design completion. A completed design is key to avoid delays in a construction project. GE Hitachi claims that drawings and specifications will be completed before a likely project in Estonia. The safety assessment report prepared for the first-of-a-kind unit will also give a good basis for the licensing in Estonia. Then we assessed the project implementation. So this slide will show the main components of an SMR project. The actual project in Estonia can start when the government has decided to launch a nuclear program. The activities to enable a fast construction and to mitigate risks for delays are made during the project development. First of all, the project-specific design will be finalized, and this means that GE Hitachi will adopt the reference design with regards to seismic conditions, to the cooling capabilities, to the power grid, and to the industrial environment. The business case will be developed based on more and more detailed cost estimations from the design process. And last but not least, the contract will be developed. And site work, early investments in the site infrastructure will gain time savings for the construction work. When a site is selected, it will be prepared for the construction project and take into account transportations, temporary offices, and excavations for the reactor building. The actual construction can start when the construction license is obtained and the final investment decision is made. It is also anticipated that a smaller construction project will be better prepared to deal with risks for delays, since it's simple. It's simply not so sensitive to project issues as a huge nuclear power plant construction. A few long lead items will need to be procured before the start of construction. And the licensing activities are running in parallel and will consist of applications and regulatory reviews in 3 phases. So this slide gives a hint of the timeline for project implementation in Estonia. The development of the project will take 4 years. After that, the final investment decision can be taken and a contract can be signed. The site investigations will start early. The procurement of long lead items needs to start 3 years prior to construction. The reason for this is the time-consuming manufacturing of reactor pressure vessel. The construction work at site can start when the construction license is obtained. The actual construction work will take 3 years for the first unit, and the unit following after the first unit will take 2 years to build. So, and the pre-construction work for these following units will be limited by procurement of long lead items and take 3 years. So the total project schedule will be 7 years for the first unit and 5 years for the following units. I will summarize this presentation and start to say that the X300 will be constructed at site, not manufactured in factories. This might not be in line with the common view of an SMR, but the simplified and standardized design will lead to shorter and more predictable construction. So it might still be said that the deployment of multiple units will be made in a modular manner. GE Hitachi claims a 3-year construction time for the first unit and a 2 years construction time for the following units. The pre-construction activities are very important and mostly associated with the first unit of a project. The planning and preparations are estimated to take 4 years. The total project time for the first unit will therefore be 7 years, and the total project time for the following units at the same site will be 5 years. So in summary, light water SMRs can be deployed in the near future, and Vattenfall's overall assessment is that the X300 definitely enables a way to build an SMR in Estonia quickly. The X300 design represents a balance between innovation and tradition. The licensing process will be in favor of the proven technology, and the construction will be in favor of GE Hitachi's know-how and experience. And this is an art impression of how an X300 site could look like. Yeah, thank you. This was my 15 minutes of fame. I will now hand over to you, Maria.
Thank you very much, Klaus. A very well spent 15 minutes of fame, if I may say so. Yeah. So a lot of people are skeptical when it comes to the fast construction times, and what they want to see is evidence. So how would you comment on that? Is there any evidence that these prototypes really can be built as fast?
Yeah, it's a good question since no SMRs have been built yet. But I think the best evidence is that it took Hitachi 44 months to build their much bigger first of a kind ABWR in Japan. So to build a much smaller and much simpler plant in 36 months should definitely be possible. I think that's the strongest evidence, except for the design simplifications.
Well, that's good to know. I also wonder, does the previous experience in a country have an impact on the construction schedule?
The previous experience in yeah, of course it will. I heard a lot of echo when you asked the question in my headphones.
Would you like me to repeat that?
Yeah, that would be great.
Sure. The question is, would the previous experience of a nation impact the construction schedule of an SMR?
Yes, of course, because this light water SMR is just a scale model of previous designs. So implementing all the lessons learned from a big project with all the risks that you're exposed to, it's definitely a good lessons learned. And I think also a way to front load this risk and to take it into consideration is to let workers, for example, be trained in actual projects before you implement the project in your own country. So you have a trained workforce.
It's interesting that you mention lessons learned, which we know is a politically correct way of saying mistakes made. And obviously we want to learn from the mistakes made by others, and we want to learn from their lessons. So what would you say are the most critical factors for Estonia that would support a fast construction?
Yeah, okay. I think the first big factor is, of course, the project planning, the pre-construction work. And then also, I think GE Hitachi's strong simplification of the design is a winning concept to reach quick construction. But if you look at the bigger picture, I think the most impacting factor is this standardization of codes and standards and the regulatory requirements that we discussed this morning. I think a global standardization will reduce the risks or that will support the construction time the most.
Thank you very much, Klaus.
Yeah.
Let's hope that we do get there at one point, or let's work towards getting there when it comes to standardized regulations, which would be internationally acceptable. But before we're there, I think what we can do is definitely look into the questions that we can try and solve in a more immediate timescale. Ehk siis ei ole mõtet karta, et Eestis ei ole olemas pädevust, et Eestis ei ole olemas kompetentsi, et tegeleda väikeste moodulreaktorite hindamisega. Ja selle tõestuseks tookski hea meelega lavale kaks kodumaist talenti, kes vaataksid lähemalt, milline on väikeste moodulreaktorite ohutus. Ehk siis ma annan sõna üle Martti Jeltsovile ja Rainer Kelgile keemilise ja bioloogilise füüsika instituudi esindajatena. Palun.
Nii, tere kõigepealt kõigile minu poolt. Minu nimi on Martti Eltsov. Ma olen üks Fermi kaasasutajatest, kuid ma olen ka KBFi tuumateaduse ja tehnoloogia töörühma looja ja eestvedaja ja taganttõukaja. Ja minuga koos siin selles ettekandes on uue põlvkonna tõusev tuumaenergeetik Rainer Kelk. Me anname ülevaate väikereaktorite passiivsest ohutusest ja keskendume võib-olla ühiskonna vaatest ühele olulisemale küsimusele, et kas ja kui suuri hädaolukorra planeerimistsoone väikereaktorid vajavad. Nii, Rainer, sõna on sinu. Slaidid tulevad siit.
Tere ka minu poolt. Ja võib järgmise slaidi panna. Nii. Mina räägin siis väikeste moodulreaktorite ja nende ohutuse alguses põhitõdedest ja siis lähen natukene ka detailidesse, et kuidas see aitaks siis kaasa ka ohutusraadiuste vähendamisele ja mis on maailma trendid selles. Esiteks väikeste moodulreaktorite puhul üks kõige suuremaid asju, mis suurendab nende ohutust, on nende väiksus, nagu ka nimest selgub. Kuna nende võimsus on madalam, siis on ka nende kütuse kogus oluliselt väiksem ja see tähendab ka, et selles reaktori tuumas olev radioaktiivse materjali hulk on palju väiksem. Teiseks, modulaarsusega saavutatakse see, et kõik komponendid on standardiseeritud ja need valmistatakse tehastes. Ja kuna moodulreaktoritel on ette nähtud, et on mitu siis võrdse suurusega. Nii, aitäh. Et on mitmed moodulid, siis radioaktiivse materjali hulk on jaotunud nende moodulite vahel ära. Kolmandaks, need reaktorid on hästi kaitstud, kuna pea kõik moodulreaktori disainid näevad ette, et surveanum asub kas veebasseinis või maa all. Ja neljandaks, pea kõik väikesed moodulreaktorid on passiivsete süsteemidega, nii tavakäidu kui ka siis õnnetusolukorras. Ja see tähendab, et nende reaktorite kaitsemehhanism tugineb loodusjõududele. Ma räägin natuke lähemalt, mis on siis passiivne ohutus ja kuidas see toob kaasa väiksema riski. Et kui aktiivse ohutuse all ja ohutuselementide all me tunneme või peame silmas, et selle elemendi käivitamiseks on vaja välist toitallikat, jõudu, näiteks elektrit, kuid siin alla kuulub ka näiteks inimfaktor. Passiivne ohutus seest tugineb aga loodusseadustele ja mis toimivad tingimusteta. Eraldi mõistame veel olemuslikku ohutust, mis tähendab seda, et disaini silmas pidades on, või nagu jaam ongi disainitud nii, et on ette nähtud, et mingid õnnetused on lihtsalt võimatud juhtuma. Kuna õnnetuse risk on siis funktsioon tagajärjest ja tõenäosusest, siis näeme, et kui me suurendame passiivsete elementide hulka süsteemis, siis väheneb oluliselt õnnetuse juhtumise tõenäosus. Lisaks väheneb tagajärg tänu sellele, et väikesed moodulreaktorid lihtsalt kätkevad endas vähem radioaktiivset materjali. Ja kokkuvõttes me saamegi tulemuseks, et väikeste moodulreaktorite siis risk on väiksem. Ja see toob omakorda kaasa võimaluse muuta paradigmat ohutuskultuuris. Me võiksime näiteks vähendada hädaolukorra planeerimistsoonide suuruseid. Mis on hädaolukorra planeerimistsoon? Eesti keeles siis lühend HPT, kirjanduses võite ka kohata palju lühendit ingliskeelset EPZ. See on siis ala tuumajaama ümber, milles on valmisolek reageerida hädaolukorrale. See koosneb kitsamast pilvekiiritusrajast ja ka laiemast toidu- ja veevaru kiiritusrajast. Pilvekiiritusraja siis põhieesmärk on vähendada sissehingatava radioaktsiooni mõju.
Toidu- ja veevaru kiiritusraja planeerimistsoonis on aga ette nähtud siis tegevused, millega monitoorida toitu ja vett, et vähendada sissesöödava ja sissejoodava radioaktiivsuse mõju elanikkonnale. Ja nende suurusi mõjutavad laiemas pildis reaktori tehnoloogia ja asukoht, kuid piiritseb ette kohalik kiirguskaitseregulatsioon ja kohalikud kaalutlused. Kiirguskaitsenõuded maailmas, ülemaailmsed kiirgusnormid seab ette rahvusvahelise kiirguskaitsekomisjon ehk ICRP. Kõrgema taseme organisatsioonidel nagu IAEA ja Euratom on selles suunav roll. Lõplik otsuse teeb igas riigis regulaator ise. Eestis on selleks otsustajaks praegu Keskkonnaministeerium. Näiteks Kanada regulaator ja Eesti Keskkonnaministeerium jälgivadki üks ühele IAEA soovitusi ja ICRP soovitusi seal hulgas. Ja need sätestavad, et tavaelanik võib mittelooduslikest allikatest saada kuni 1 millisiiverti suuruse efektiivdoosi aastas. Kiirgustöötaja eest võib saada kuni 50 millisiiverti suuruse efektiivdoosi aastas, kuid mitte siis üle 100 millisiiverti 5 aasta peale. Kui vaatad seda parempoolset graafikut, siis sealt on näha tegelikult, mis on nii-öelda võrdluses erinevad doosid. Lisaks sellele 1 millisiivertile, mis on lubatud tavaelanikule, peab arvestama kindlasti ka loodusliku kiirgustasemega, mis võib maailmas siis sõltuva asukohast väga palju erineda. Eestis on see maailma keskmisest natukene kõrgem, kuna meil on põlevkivitööstus, oma sorti geoloogia ning natukene ka Tšernobõli jääke. Samas on maailmas ka oluliselt ekstreemsemaid näiteid. IAEA soovitused kaitsevööndite, IAEA metodoloogia järgi jagunevad kaitsevööndid siis 8 hädaolukorra planeerimistsooniks ja 8 planeerimise kauguseks. IAEA lähtub sealjuures tehnoloogiapõhisest regulatsioonist, kus ühest küljest arvestatakse jaama disainiga ja teisalt asukoha spetsiifiliste andmetega. Võtmaks arvesse arenguid väikeste moodulreaktorite tehnoloogias on kokku kutsutud väikeste moodulreaktorite regulaatorite foorum ja nemad leidsid, et senine metodoloogia, mis on kehtinud, sobib ka arvestamaks moodulreaktorite kõrgendatud ohutust. Aga kuna lõplikud reeglid seab riiklik regulaator, siis on lühikene tutvustus ka trendidest maailmas. Ameerika regulaator NRC erineb praegu paljudest teistest oma ettekirjutava regulatsiooniga. NRC määrab siis standardsed distantsid, mis on ette nähtud hädaolukorra planeerimistsoonidele ja need on omal ajal kujunenud arvestades siis suuri ja traditsioonilise vesiohutusega reaktoreid. On defineeritud 2 tsooni, 10-miilise raadiusega pilve leviku kiiritusrada ja 50-miilise raadiusega toidu- ja veekiiritusrada. Peab märkima, et Ameerikas on uus regulatsioon kujundamisel, mis siis võtaks arvesse väikeste moodulreaktorite arenguid ja muudaks selle regulatsiooni tehnoloogia põhisemaks. Sealjuures selle tulemusel võib siis sõltuvalt riskianalüüsist selguda, et hädaolukorra planeerimistsoon võibki piirduda ainult jaamaalaga. Erinevalt Ameerika regulaatorist on näiteks Kanadas ja Ühendkuningriigis regulatsioon juba praegu tehnoloogiapõhine. Kanadas eristatakse planeerimistsoonidena keelutsooni, mis on operaatori kontrolli all täielikult, ning hädaolukorra planeerimistsooni, kus siis seal ette nähtud tegevused toimivad õnnetuse korral nii regulaatori, Tervishoiuameti, kohalike omavalitsuste ja loa taotleja koostöös. Ühendkuningriigis eristatakse detailselt hädaolukorra planeerimistsooni ning välisplaneerimistsooni ja sealt all oleval pildilt on näha, kuidas välise planeerimistsooni defineerimisel ei võeta siis ainult arvesse distantsjaamast, vaid ka geograafilisi ning demograafilisi aspekte. Nüüd järgmisena räägib Martti Jeltsov natukene ka erinevast disainist täpsemalt. Nii, Vaatame siis veidi lähemalt, mida väikeste moodulreaktorite arendajad tänase seisuga selles vallas teinud on. Kõigepealt me vaatasime 5 reaktorit, mis meile huvi pakuvad. Esimene on NuScale'i reaktor, see on esimene sertifitseeritud väike reaktor, ta sai loa või disaini sertifikaadi Ameerika Ühendriikis eelmine aasta. Tegemist on nii-öelda kokku pakitud väikese surveveereaktoriga, kõik komponendid ühes koos ja ühe mooduli võimsus on 50–77 megavatti sõltuvalt lõpuks siis kliendi soovist. Ühes jaamas on 4–12 moodulit ja nad kõik asuvad ühes veebasseinis, on teineteisest sõltumatult ja igal moodulil on siis täiesti eraldi seisvad täies mahus kaitse ja käidusüsteemid, mis põhinevad passiivsetel mehhanismidel. Esimest jaama ehitatakse praegu USA-s Utah osariiki koostöös kohalike omavalitsuste, ettevõtete ja USA riigiga. Ja tulenevalt sellest integraalsest tehnoloogiast, väikestest moodulitest ja mitmetest kaitsekihtidest, mis NuScale'i reaktoril on NuScale'i hädaolukorra planeerimistsooni suuruseks hinnatud 0,5 kilomeetrit, mis sisuliselt vastab jaama kinnistule. Teiseks me vaatasime keevaveereaktorit, mida arendab GE Hitachi. Tegemist on 10. põlvkonna keevaveereaktoriga. See X300 on siis 300 megavatine väike reaktor, mis tugineb arendaja väga pikaaegsel keevaveereaktorite kogemusel ning hästi oluliselt ka juba Ameerikas litsentsi saanud ESBVR keevaveereaktoril. See on siis suur reaktor, mis on litsentsi saanud ja nüüd selle alusel väikeseid muudatusi ja parandusi läbi rääkides siis litsenseeritakse Ameerikas praegu väiksemat versiooni sellest. Tegemist on samuti passiivselt töötava reaktoriga ning arendaja hinnangul on hädaolukorra planeerimistsooni suurus sarnane, ma siin mainin TVA väikereaktori asukoha analüüsi käigus leituga, ehk suurusjärgus paar kilomeetrit. Ja sellest TVA-st ma räägin mõne slaidi pärast. Järgmiseks me vaatasime sulasoola reaktorit, 200 megavatine IMSR reaktor siis. Selle reaktori ohutusse eelkõige panustabki suurel määral nii jahutiks kui ka reaktori kütuseks olev sulasool, mis on väga head soojuskandja omadustega, ehk ta jahutab hästi reaktorit ja samas ka väga head radioaktiivsete ainete kinnihoidmise omadustega. Ehk ta keemiliselt seob enamus radioaktiivsed elemendid sellesse jahutusvedelikkütussegusse. Ja esialgsed arvutused on näidanud, et juba 200 meetri kaugusel reaktorist jääb kiirgusdoos alla kehtestatud piirnormidega kõige halvima postuleeritud õnnetuse korral. Ja see reaktor on siis eellitsenseerimises hetkel USA-s ja Kanadas. Ultrasafe Nuclear Company poolt arendatav MMR ehk Micromodular Reactor on, nagu nimigi viitab, väga madala võimsusega 5–10 megavatti gaasjahutusega tõeliselt väike reaktor. Selle reaktori ohutus põhineb väiksusel ning ka kasutataval trisokütusel. Ehk need on väikesed keraamilised nii-öelda pallikesed, mis on erinevates testides näidanud vastupidavust temperatuuridele 2000 kraadi ja enamgi. Ja just sellest väiksusest ja jällegi kütuse kasutusest tulenevast ohutusest on arendaja hinnanud hädaolukorra planeerimistsooni suuruseks vähem kui 100 meetrit. Seda, kas jaama aia taga siis tõepoolest ei ole tarvis spetsiaalset planeerimist, seda peavad näitama veel detailsemad ohuanalüüsid, mis siis reaktori arendamise ja litsenseerimise ja loa menetlusprotsessides läbi viiakse. Need on hetkel käimas. Ja MMR-reaktori puhul, selle gaasjahutusega reaktori puhul tasub märkida, et just selle reaktori rajamise on ette võtnud üks Kanada ja Põhja-Ameerika suuremaid energiaettevõtteid Ontario Power Generation, OPG siis. Ja ainuke Euroopa reaktori tehnoloogia, mida me antud uuringus vaatasime, pärineb Inglismaalt. Tegemist on Rolls-Royce'i ja tema partnerite poolt arenduses oleva väikese survevee reaktoriga võimsusega 450–470 megavatti ja selle litsenseerimisega alustatakse käesoleval aastal. Et minnakse üle siis kontseptifaasist litsenseerimisfaasi, kus on selguvad juba oluliselt täpsemad detailid. Selle reaktori näol on tegemist teada-tuntud tehnoloogiaga, survevee reaktori tehnoloogia, mis on maailmas kõige populaarsem, aga lihtsalt selle vähendatud ja optimeeritud versiooniga. Ja kuna reaktor, nagu ma mainisin, on alles kontseptifaasis, siis ohutustsoone, hädaolukorra planeerimistsoone ei ole veel määratud. Selleks tuleb ära oodata siis litsenseerimisprotsessi tulemused ja tulevikuloa, ehitusloa ja käiduloa menetluse tulemused. Küll aga on sellel reaktoril samamoodi olemas kõik väikemoodulreaktoreid kirjeldavad või nende omadused, mis võimaldavad siis minimeerida hädaolukorra planeerimistsoonide suurusi. Ja nüüd sellest ainsast praktilisest näitest väikereaktorite, ma ei saa öelda veel ehitamisel, aga asukoha valimisel. Ehk siis Ameerika Ühendriikides Tennessee Valley Authority soovis või analüüsis Clinch River Nuclear Site'i väikereaktori projekti jaoks ja vaid keskkonnamõju hinnanguid ja arvutas välja hädaolukorra planeerimistsoonide suurusi. Nad võtsid oma arvutustes arvesse sellise tehnoloogia ümbriku, kuhu kuulus 4 reaktorit, kõik kergvee tehnoloogial põhinevad, mida võiks sinna potentsiaalselt ehitada, määrati ääretingimused, mis vastavad kõigile nendele reaktoritele ja nende põhjal määrati ka siis nagu me eesti keeles kutsume allikatunnus, inglise keeles source term, ehk siis radioaktiivse aine hulk ja muud parameetrid reaktoris. Lisati sinna veel konservatiivseid marginaale, eeldusi, et analüüs oleks tõepoolest konservatiivne selles faasis ja arvutati hädaolukorra planeerimissuurusi. Ja kõigi reaktorite kohta oli see nad jäid maksimaalselt 2 miili raadiuseks ühe reaktori puhul, mis oli võimsuselt siis oluliselt väiksem isegi. Tema hädaolukorra planeerimistsoon jäi jaama piiresse. Aga loomulikult seal ei ole veel jaama aeda kuskil, siis on raske öelda, et kas ta on jaama aias sees või väljas, aga igal juhul mõne miili raadiuses. Ehk siis kokkuvõtteks võime öelda, et tänased regulatsioonid on arenenud optimaalseteks suurte jaamade litsenseerimiseks ja analüüsimiseks, aga nad ei arvesta piisavalt väikemoodulreaktorite eelistega, mis on siis nende väikemoodulreaktorite väiksus iseenesest, väiksed tuumad, väiksed jaamad, passiivsed süsteemid nii käidus kui kaitsefaasis ja tehases ehitamises tulenev kvaliteet. Siiski maailm on jõudsalt liikumas tehnoloogia-spetsiifiliste ja detailsetel riskianalüüsidel põhinevate ohutusraadiuste määramise suunas, mis siis sobib ka väikereaktoritele või kõigile reaktoritele, mis siis ei vasta sinna standardsete suurte reaktorite tingimustele. Ja meile kättesaadavate andmete põhjal on alust väita, et oluliselt väiksemad, sealhulgas ka jaama alaga, kinnistu aiaga piirnevad hädaolukorra planeerimistsoonid on realistlik eesmärk, kuid lõplikud vastused tekivad siis, kui reaalsed konkreetsed projektid kuskil ellu viiakse, mille osas siis tegevused Ameerikas ja USA-s ja Kanadas eeskätt hetkel toimuvad. Ja see on meie poolt praegu kõik. Aitäh!
Suur tänu teile mõlemale ja aega meil küll teab, mis palju ei ole, aga sellegipoolest esitaksin teile vähemalt ühe küsimuse. Et kui suurte jaamade puhul räägitakse planeerimistsoonidest, mis mõõdetakse kilomeetrites, nüüd räägime sadades meetrites. Et mina, kes ma elaksin teisel pool seda aeda, kas mul on igati õigus tunda ennast ohutult?
jah, no ma vastan sellele, siis nii nagu suurte jaamade puhul, väikeste jaamade puhul viiakse ka läbi detailsed ohutusanalüüsid ja kui suurte jaamade puhul on need analüüside tulemused olnud sellised, et on tarvis või on mõistlik kehtestada 5, 10, 20, 50 kilomeetriseid tsoone, siis kui samasugused analüüsid, mis tehakse väikereaktoritele nende enda tehnoloogia põhiselt, võttes arvesse kõiki eeliseid, mis väikereaktoritesse on nii-öelda sisse kodeeritud, siis ma usun, et lähedal või aia taga elavad inimesed ei peaks kartma, kui analüüsi tulemused näitavad, et sealt midagi välja ei tule.
Ja kuidas vastata nende kriitikute kommentaarile, et tõeline vastus tuleb alles peale esimest õnnetust?
Ma võin vastata sellele, et just lähtudes siis passiivsusest, kui madalale on viidud õnnetusjuhtumise tõenäosus, siis ma võiks öelda, et me võimegi jääda ootama neid tihtipeale neid õnnetusi. Et see tõenäosus on lihtsalt viidud nii madalale, et tänapäevaste metoodikatega on see ohutus, mina ütleks küll, et tagatud.
Selge. Aitäh teile mõlemale. In reality, it's not enough to build a nuclear power plant and to produce electricity by running it, but we also have to, from the beginning, consider the question of waste, which is in many ways a driving concern for people both involved in the industry and the general public. So our next speaker, Chris Parker from Deep Isolation, will try to give us a fairly fresh perspective on how to potentially manage spent nuclear fuel and nuclear waste. Chris, are you on the line?
Yes, I am. Can you hear me, Reja?
We can see you and we can hear you. You're very welcome.
Okay, excellent. Well, thank you very much for inviting me to participate in this conference. And I'm only sorry that I can't be there with you in person in Tallinn. I had been very much looking to come and join in the conference, but COVID-19 still being out there, that's not proved possible. So yes, I'm going to talk about the issue you've just described, which is sort of management of the waste, and in particular, I'm going to look at the potential for borehole disposal of spent nuclear fuel in Estonia. So by way of background and introduction, I am Managing Director of the European business of Deep Isolation. And what I'm going to do this afternoon is really talk through 4 issues. So firstly, the challenge that you've highlighted. So if Estonia does choose nuclear to be part of its low carbon future, how will it dispose of the resulting spent fuel? And that is a challenge that the world as a whole is still grappling with. Secondly, I want to describe a potential solution, which is deep borehole disposal, and in particular, a new form of borehole disposal, which Deep Isolation is pioneering, enabled by innovation in directional drilling technology. So I'll talk a little bit about that approach. Then I want to spend most of my time on point 3 on this slide. So sharing some results of a initial study we have undertaken in partnership with Fermi Energia, looking at the feasibility of implementing this technology, specifically within Estonia and Estonia's crystalline basement geology. And then finally, I'll end with some thoughts about next steps and how Estonia might look at integrating this issue into their into its future sort of policy and regulatory work. So the challenge that we're talking about is a significant one. So if you look on a global level, we've now been producing commercial nuclear power for 7 decades. And in all of that time, we have disposed of 1 gram of the spent fuel that we produced as a result of that power production. So we now have as a world community, we have a global stockpile of well over 400,000 tons of spent fuel, all of which is kept effectively in temporary storage facilities whilst disposal solutions are being developed. And we're adding to that at around 3% a year. Linked to that, we have, I think, a significant problem that the current model for geological disposal is simply not scalable. A lot of excellent work has been done in some countries on how this waste can be disposed of in depth through large mined repositories. That's, looking just at Europe, for example, that's a relatively small number of countries which have got very advanced plans on that in terms of, identifying sites and having clear budgets and license plans for disposal. I've highlighted a number of them here. Some of them sort of neighbours of Estonia's in Scandinavia. My point about scalability is that these are all massive decade-long civil engineering projects that take decades to plan and deliver, and they cost billions. The data here on costs is being developed by the ERDO working group, looking at costs across a number of European nations. So question, does Estonia want to invest in that sort of disposal facility alongside its SMR, or is there scope for innovation to open up another approach? So that's where I'm going to talk a little bit about our company, Deep Isolation, because we were very much founded on the idea of bringing to market a solution to precisely that challenge, to offer safe, equitable, but much more affordable disposal of nuclear waste. So the company is relatively young. We were founded in the United States in 2016. The organization that I manage was launched about 12 months ago. We're based in London, but with a responsibility across Europe and the Middle East. So what we do is use state-of-the-art drilling technology, directional drilling technology, which can get to and find suitable host rock formations in a much greater number of areas more quickly and more rapidly than is possible when creating one of these big mined repositories. We do that in host rocks that have been isolated from the environment for millions of years. We take corrosion-resistant canisters containing the spent fuel. We put them in borehole repositories deep underground, so a kilometre, a mile and a kilometre and a half, 2 kilometres underground, much deeper than for example, the Swedish and Finnish examples that we looked at on the previous slide. And then we seal the access hole. And we do that using technologies that are widely used across the oil and gas sectors and the nuclear handling sectors, which we have integrated and enhanced with our own innovations. So this is bringing together tried and tested approaches that have been shown to work. Before looking at the results of our study in Estonia, I will just try and bring that to life by showing a very short video of how the system works. So let me talk you through this. In this example, I'm showing here a disposal canister that's about 32 centimeters across, about 4 meters long, and that's a BWR fuel assembly. So it slips inside the disposal canister. We seal the edges. If you look at it end on, you can see that's a very snug fit. And the canister has been made of highly corrosion resistant alloys, so material which should last thousands of years. We put that canister into deep rock. That rock can be sedimentary rock, as shown on this diagram. It could be granitic rock, it could be crystalline basement rock, as we have in Estonia. It could be salt. So we begin by drilling a hole in the top. And you can see here at the very top, there's a bluish area. That's the aquifer. We drill below the aquifer, put down a metal tube called a casing, and then put cement down the middle of that tube. So that cement then flows up the outside of the tube and gives us even greater protection against anything reaching the aquifer. Now that's a standard procedure done on a daily basis in the oil and gas sector. So once we've done that, we drill down further. Here we're going deep into the layers of rock to what's called the kickoff point. And then we start to bend very slowly, so slowly that if you were down there, you wouldn't notice it as you looked at it, until we reach the horizontal. Then we go horizontally for 1 kilometer, 2 kilometers, and that's the region where we're going to store the nuclear waste. We put cement down, we put casing down, just as we did at the upper level, and now we're ready to emplace the waste. So this is the canister. We attach several devices to the end of it. This one is what's called the tractor, and we'll see that working in a moment. We put this in shielding when it's above the ground to protect workers, and then lower it slowly into the hole using a cable until it gets down past the horizontal section. And when we're in past the vertical section, and when we're in the horizontal section, that's when the tractor comes into play. So you'll see the wheels expanding, and then we use that, we drive the disposal canister to the end of the disposal section. Once that's done, we release the canister, we remove the tractor, pull it back up to the surface, and then place another canister. So that process is then repeated until all the spent fuel is in place. Once the canisters are all in place, we can then seal the vertical access hole with a range of sealing options depending on the local geology and regulation. And within a few years, the enormous weight of the rock above compresses those materials and provides an excellent seal to that narrow access hole. So now we've put the waste deep, much deeper than in a conventional mined repository, and that isolated depth turns out to be very important. And I'll say a little more about that as I go through the Estonia for the presentation for Estonia. But hopefully that gives you an overview of what we're talking about. Let me talk now about the work we've done looking at the feasibility of this technology within Estonia specifically. So this is a project that we've worked on with a group of industry partners. Fermi Energia has sponsored the work, and we've also worked closely with Steiger Engineering, who brought to bear real depth of experience on Estonian geology and drilling experience within Estonia to us. So that's been an excellent partnership in the project. I should stress that this has just been a preliminary study. So we've been analysing existing data. We've not undertaken any site-specific search at this stage. And so really this is just the first step in what would be a longer journey to look at geological suitability within Estonia. But within that context, we've been looking at really two key research questions. Is this safe, and is it deliverable? Is it a practical proposition from a drilling perspective? So does Estonian geology provide suitable host rocks in which a borehole repository could be safely sited, and where we could build a safety case for that, stretching out over a million years and more? And can we construct the repository in Estonian rocks on a cost-effective basis? So those are the two things we've been looking at, and our report sets out our analysis. I'm going to go through some of the headline conclusions. Firstly, just to drill down on the safety side of it. more. We've done an Estonia-wide screening. We've looked at all 15 counties of Estonia from a safety perspective, looking at 4 major criteria, which are mapped really to the requirements that the IEA safety standards set out for geologic disposal facilities of radioactive waste. So seismicity, is the deep geosphere in Estonia historically stable from disruptive seismic events? Secondly, are there risks of a deep repository being disturbed by volcanic activity, by heat flows and volcanism? Looking at climate change impacts, so looking at into the past, what past glaciation and so on has done to the Estonian geology, and what are expected future trends, and what do they suggest? We've also looked at the hydrological environment at depth. So what evidence is there that there are sites which have been entirely isolated from Estonia's biosphere, from the surface environment, and for millions of years. What I'm going to show really is a summary of our findings, and we've summarized it against these 4 levels here. Really clearly, that's, I mean, although we've numbered them 0, 1, 2, and 3, this is a qualitative assessment on a county by county basis, looking at are there any areas of the country which are entirely unsuitable, where there are such significant risks at a broad scale in the area that we should just rule that out, to are there at level 3 areas where we see no significant risks at all. Key findings from this, really 3 things. So the first key conclusion is that we believe the evidence suggests that a deep borehole repository would be both a safe and affordable option for Estonia to consider for its waste. So looking at the safety issues on the left there, we've looked at some preliminary modelling, quantitative modelling of what would happen in a repository based in crystalline basement. So this is not specific to a specific site in geology, but it's a generic model in crystalline basement geology with fracture networks and so on, very similar to Estonia's. And that shows that this would provide robust levels of safety. So the modeling suggests that the peak dose of radionuclides arriving at the surface wouldn't occur until well after 1 million years, 1.3 million years. And that level, that peak dose level, would be 3 orders of magnitude, 1,000 times below the regulatory requirements for safety. So this is a robust solution which is using that great depth of rock to keep radionuclides isolated from the surface. Looking at the data on the right there, again, this is an early indication where the specific type of reactor that's for Estonia is not being factored into this. Costs are clearly site specific, but nevertheless, looking at existing research, it does suggest that this would be a significantly less expensive option than a borehole repository. The data here comes from very recent research by the Electric Power Research Institute, EPRI, looking at a number of borehole scenarios and comparing with the typical costs of a mined repository. And as you can see there, the borehole scenarios represent sort of between 24% and 31% of the cost of disposal in a traditional mined facility. Second key conclusion is that we see no fundamental geological limitations to siting of nuclear waste in deep horizontal boreholes in Estonia. We see a wide range of siting options are available. The chart here is illustrative. We've simply represented those qualitative judgments on the 0 to 3 scales, which themselves clearly bring together a lot of different data points, and map the 15 counties against them. really just to illustrate two key points, that there are no parts of the country where the evidence suggests you would just rule out from any full siting exercise, because we think in all parts of the country are likely to find to offer sites which could be demonstrated as providing a safe environment on a million-year safety case. But the second key point is that there is a cluster of counties, so Lena-Viru County, Ida-Viru County, Harju, which on both the safety thing aspect and viewed from a cost-effective delivery perspective, scored highest on our metrics, and those really are on the northern coastal region and the islands. So from both a safety perspective and an operational perspective, that's where we see as the areas with the greatest likelihood of providing a number of host rock formations which would work. So they combine a number of optimal conditions. So the depths we're talking about would be particularly isolated from aquifers, which in the south of Estonia tend to be at different depths. To the north, the coastal site would facilitate seismic surveys, so making it easier for us to do site characterization. So where does that leave us? As I said, this has been a preliminary study only. We're sharing that with stakeholders in Estonia. We published a summary version of it. Clearly, extensive further work would be needed to identify the right sites and to characterize them as safe, to engage with potential host communities and ensure that they were consenting and embracing the idea of this. And we've set out recommendations on how those issues might be best taken forward in Estonia in 5 domains, really, as illustrated. So policy and regulatory issues, social and community issues, geological issues, demonstrating this within Estonian geology and building the more detailed business case for this. But one overarching recommendation, I think, and this is the key message I would leave today, is that as Estonia, as the government, and in conjunction with citizens, considers nuclear power and considers the SMR option, please think about developing the strategy for managing the resulting spent fuel in practice. Our initial assessment is that basing that strategy on deep borehole disposal is a viable and attractive way forward. So look at establishing a clear implementation plan which addresses all of these issues that we've highlighted on a parallel track, so that the disposal route can be in place at or before grant of the operating license for the nuclear power plant. And final point, there is no question that if Estonia were to do that, it would establish Estonia as a world leader, the only country in the world to have put in place a clear disposal route for nuclear waste before it starts to produce that waste. We believe that's the right and responsible thing to do, and we very much urge Estonia to consider that as it takes this agenda forward. On that note, thank you very much, and happy to take questions if we have time.
Presentation. If you don't mind, I would like to ask you just a couple of questions. The first one being, well, Estonia likes innovation, but not to be left alone with a solution. So would we be the first and the only to use this type of waste management solution?
So would you be the first? No, I don't think so. So to be clear, this is a technology which has not yet in full implementation anywhere. Deep isolation has demonstrated significant aspects of the technology in operation. So at our test site in Cameron in Texas, in conjunction with our global drilling advisors Schlumberger, we have demonstrated the emplacement of canisters, shown how they can be retrieved and brought back to the surface. So there is significant demonstration. There is also significant interest in this from governments around the world. We're engaging with national waste management organizations across Europe, the Middle East, the Far East. There is a lot of interest. In terms of, when will this be implemented and on a license basis, that's clearly not entirely in our hands. I was asked the same question in November when I was on a panel bringing together a range of deep borehole experts from government, from the IAEA, from universities, from research institutes, under the aegis of IFNEC. So IFNEC is, as some of your participants may know, is a government-to-government network of leaders in nuclear waste management. And this IFNEC panel was focused on deep borehole disposal, and they were asked the same question. So when do we think this will be operational? The consensus of opinion on the panel was that this technology is increasingly mature, and it's reasonable to assume that there will be licensed operational delivery of disposal within deep boreholes by 2030. Our view as a company, based on the engagements we're having with a number of governments, is that it should be possible to get to implementation significantly before that, and we're investing to help make that happen. But either way, certainly from an Estonia perspective, that would be well before the country needed to dispose of any waste from a new build SMR in Estonia. So I think the potential for you to innovate is around the policy and regulatory process and being the first to having the solution in place. In terms of the actual implementation, Estonia would be able to draw on practical operational and regulatory experience from other countries.
Thank you very much, Chris, for that thorough answer to that question as well. We will have to move forward now and take the last speaker that we have before the somewhat longer break. Ja mul on hea meel teatada, et meie järgmine kõneleja on täiesti kodumaine ja eestikeelne. Me oleme tänase päeva jooksul juba kuulnud üht-teist IAEA kohta ehk siis rahvusvahelisest aatomienergia agentuurist, kuid meie järgmine kõneleja oskab sellest agentuurist rääkida oluliselt täpsemalt, kuna ta on Eesti esindaja selles organisatsioonis. Reelika, ma loodan, et sa oled meiega.
Tere päevast!
Tere! Ja
tervitused Viinist! Nii, ma proovin kohe tööle saada ka oma video. Nii. Mina olen Reelika Runnel, olen Keskkonnaministeeriumi atašee Viinis ja kiirgusküsimuste nõunik Eesti Viini saatkonnas, mis on ühtlasi ka Eesti alaliseks esinduseks rahvusvahelise aatomienergia agentuuri ehk siis IAEA juures. Ja minu ettekanne on eelnevatega võrreldes natukene teises võtmes. Nimelt teen ma oma ettekandes teile ülevaate sellisest organisatsioonist nagu IAEA, selle rollist maailmas ja tähtsusest Eesti jaoks. IAEA asutati 1957. aastal ÜRO organisatsioonina selleks, et rakendada tuumatehnoloogiat inimkonna hüvanguks. IAEA peakorter asub Austrias, Viinis, kuid neil on ka esindused Genfis, New Yorgis, Torontos ja Tokyos. IAEA-sse kuulub hetkeseisuga 172 liikmesriiki ja Eesti on IAEA liige alates 1992. aastast. IAEA peadirektor, kes täna hommikul meile ka videotervitusega esines, on Rafael Mariano Grossi. IAEA kõrgemateks organiteks on kõikide liikmesriikide osalusel kord aastas kogunev peakonverents ja 35 riigist koosnev nõukogu. Ja meie IAEA liikmelisuse ajaloos esimest korda kuulub Eesti praegu kuni selle aasta septembrini IAEA nõukokku, ehk siis on ühest 35 riigist, kes siis otsustavad IAEA prioriteetide ja tegevuse üle. Ja nõukogu liikmena on meie fookus innovaatilistel tuumatehnoloogia lahendustel, seda siis just kliimaeesmärkide saavutamise võtmes ja radioaktiivsete jäätmete käitlemisel, mille osas me soovime IAEA-ga teha aktiivsemat koostööd. IAEA eesmärk on edendada tuumaenergia rahumeelset rakendamist ning ära hoida selle kasutamine sõjalisel otstarbel. Nagu IAEA peadirektor Grossi oma avakõnes ütles, siis on IAEA põhirolliks pakkuda oma liikmesriikidele igakülgset tuge, kui nad on otsustanud kasutusele võtta tuumaenergia. Ja IAEA-l on pikaajaline kogemus ja teadmised kõigist tuumatehnoloogia valdkondadest, alates siis õigusaktide väljatöötamisest kuni tuumajaamade ohutu käitamiseni. IAEA tegevusvaldkondadeks on muuhulgas siis tuuma- ja kiirgusohutusalase teabe vahendamine, tuumaohutusalaste koolituste ja väljaõppe korraldamine, tuumaenergiaprogrammide järelevalve, siis kiirgusohutuse, tuumaohutuse ja tuumajulgeoleku standardite ja juhendmaterjalide koostamine ja samuti tuumaohutuse rahvusvahelise õigusraamistiku ehk siis konventsioonide haldamine. Oma tegevusega panustab IAEA ka ÜRO säästva arengu eesmärkide täitmisesse, tegeledes siis tuumatehnoloogia abil kliimamuutuste vastu võitlemisega, vähiravi ja diagnostikaga, puhta joogivee tagamise, põllumajanduses saagikuse suurendamisega ja merekeskkonna uuringute ja muuhulgas ka pandeemiate vastu võitlemisega. Näiteks eelmise aasta kevadel asus IAEA oma liikmesriike kiiresti abistama COVID-19 diagnoosimiseks vajaliku laboritehnikaga. Eesti tol hetkel küll IAEA-lt täiendavalt varustust ei vajanud, küll aga said IAEA abisaadetise meie lõunanaabrid lätlased. Ja sellest kiirreageerimisena loodud algatusest on tänaseks välja kasvanud projekt Zodiac, mille eesmärgiks on siis koostöös WHO ja FAO-ga ehk siis ÜRO Toidu- ja Põllumajandusorganisatsiooniga riikides siis pandeemiatega toimetuleku võimekuse loomine. Ja käesoleval aastal on IAEA üheks fookusteemaks ka ookeanid ja mereressurss ja projektiga Nutek Plastik otsitakse võimalusi, kuidas tuumatehnoloogia abil plastikureostust vähendada. IAEA üheks tähtsamaks rolliks on olla ka niinimetatud tuumavalvekoeraks, et ära hoida tuumarelvade levik. Tuumatehnoloogia abil saab maailmas teha väga palju head, aga valedes kätes võib sellega teha ka palju kurja. IAEA-le on 1968. aastal sõlmitud tuumarelva leviku tõkestamise lepingu ehk NPT-ga tehtud ülesandeks kontrollida, et riigid kasutaksid tuumatehnoloogiat ainult rahumeelseks otstarbeks. Ja selle tõestamiseks peavad riigid vastavalt IAEA-ga sõlmitavale kaitsemeetmete kokkuleppele esitama IAEA-le regulaarseid tuumamaterjali ja tehnoloogia deklaratsioone ja lubama oma riiki ka siis IAEA inspektoreid seda kontrollima. Ja kaitsemeetmete kokkuleppele tuginedes kontrollib IAEA ka näiteks Iraani poolset JCPOA ehk siis niinimetatud Iraani tuumaleppe täitmise tingimusi. Kuna tuumaelektrijaamad on maailmas hetkel vaid 31 riigis ja 30 riiki on kaalumas tuumaenergia kasutuselevõttu, siis puutub suurem osa riikidest IAEA-ga kokku muudes valdkondades. 142 liikmesriigi, sealhulgas ka Eesti jaoks, on IAEA-ga koostöö tegemisel kõige olulisemaks IAEA tehnilise koostöö programm. See on IAEA üks peamine mehhanism liikmesriikide arengu toetamiseks sellistes valdkondades nagu tervishoid, põllumajandus, keskkonnakaitse, tööstusrakendused ja ka tuumaalaste teadmiste arendamine. Ja tehnilise koostööprogrammi raames siis sõlmitakse riigi ja IAEA vahel 5-aastane raamprogrammi kokkulepe, milles siis määratletakse ära riigi jaoks olulised valdkonnad, milles abi saada soovitakse. Ja raamprogramm annab riikidele õiguse esitada IAEA-le nendes valdkondades projektitaotluseid IAEA-st rahastuse saamiseks ja osaleda IAEA enda vastavates projektides. Tehnilise koostööprogramm hõlmab nii regionaalseid, interregionaalseid kui ka riiklikke projekte ja Eesti prioriteetideks IAEA tehnilise koostööprogrammis on seni olnud vähiravi võimekuse arendamine, radioaktiivsete jäätmete käitlemine ja riikliku kiirgusohutuse süsteemi toimepidevuse tagamine. Järgmise aasta alguses sõlmib Eesti IAEA-ga ka uue raamkokkuleppe, kuhu siis lisame seekord ka tuumaalaste teadmiste arendamise soovi. Nüüd jõuamegi minu ettekandes selleni, millist abi siis Eesti IAEA-lt nende liikmeks oldud 29 aasta jooksul saanud on. Eesti kiirguskaitsesüsteemi ülesehitamisel on IAEA-l olnud põhiroll õigusloome toetamisel. Ja Eesti esimene kiirgusseadus koostati aastatel 1996-1997 vastavalt IAEA juhistele ja rahvusvaheliste ekspertide toele. IAEA on läbi oma auditite aidanud ka hinnata meie kiirguskaitsesüsteemi toimimist ja vastavust rahvusvahelistele standarditele ja andnud siis ka soovitusi, kuidas Eesti kiirguskaitsesüsteemi parendada. Näiteks 2011. aastal hindasid IAEA eksperdid meie valmisolekut kiirgushädaolukordadeks. Et juhuks, kui siis meil peaks riigis toimuma mõni õnnetus kiirgusallikaga või juhtuma avarii naaberriigi tuumajaamas. 2016 ja 2019 hinnati IRRS nimelise auditi käigus meie kiirguskaitsesüsteemi terviklikku toimimist. Ja 2019 toimus ka radioaktiivsete jäätmete käitlemise audit. Täiesti asendamatuks ja suurima väärtusega abiks on Eesti jaoks kahtlemata olnud IAEA koolitused meie kiirguskaitse, hädaolukordade, radioaktiivsete jäätmete käitlemise ja meditsiinivaldkonna spetsialistidele. IAEA tehnilise koostööprojektide abil on soetatud meditsiiniseadmeid, laboritehnikat ja panustatud koostöös ülikoolidega ka meie teadustegevusse. Eesti meditsiinisüsteem võlgneb IAEA-le väga suure tänu vähiravi võimekuse arendamise eest. IAEA on alates 1997. aastast toetanud kiiritusravi väljaõpet ja panustanud tehnilise koostööprojektide kaudu meie meditsiinivaldkonna arengusse. Arendatud on tuumameditsiini protseduuride kvaliteedi ja diagnoosimise võimekust ja diagnostilises radioloogias kiirguskaitsete kvaliteedi kontrolli ja samuti on koolitatud IAEA abil meie meditsiinipersonali. IAEA-l on tähtis roll ka kiirgushädaolukordadeks valmisoleku tagamisel. Eesti juhindub selles valdkonnas IAEA standarditest ja soovitustest ja vahetab infot IAEA intsidentide ja hädaolukordade keskusega, mis siis tegeleb kriisijuhtimisega maailmas kiirgusallikate ja tuumarajatistega toimunud õnnetuste osas. Ja IAEA koostab siis sündmuste raporteid, korraldab hädaolukordade õppuseid ja teeb sündmuste siis järelmid. Ja sellest, kui kuskil maailmas on kiirgusallikadega mingi õnnetus toimunud, saame meie siin Eestis tänu IAEA-le väga kiiresti teada. Ja Eesti kuulub ka IAEA RANET võrgustikku, mille kaudu on võimalik vajadusel IAEA kaudu paluda teiste liikmesriikide abi ja siis kiirgushädaolukordadega toimetulekuks. Nüüd, kuna rahvusvaheliste konventsioonide ja Euroopa Liidu direktiivide nõuete kohaselt vastutab iga riik oma territooriumil tekkivate radioaktiivsete jäätmete käitlemise eest ise, siis on alates 1995. aastast kõik Eesti radioaktiivsed jäätmed kogutud Paldiskisse, endise tuumaobjekti territooriumile rajatud vahehoidlasse. Ja seda hoidlat haldab siis Majandus- ja Kommunikatsiooniministeeriumile kuuluv aktsiaselts Alara. Paldiski vahehoidlasse on viidud ka kunagises Tammiku radioaktiivsete jäätmete hoidlas asunud jäätmed ja selle objekti puhastus- ja lammutustööd on tänaseks juba praktiliselt lõppenud. Eesti koostöö IAEA-ga algaski tegelikult aktiivselt seoses just Tammiku jäätmehoidlaga. Nimelt 1994. aastal murti hoidlasse metallivarguse eesmärgil sisse ja ühe isiku jaoks lõppes see sündmus surmaga, mitmed inimesed said väga suuri kiirgusdoose. Ja IAEA on juhtumi kohta koostanud põhjaliku raporti ja siis toetanud Eestit siis radioaktiivsete jäätmete käitlemise valdkonna korrastamisel. Ja oleme oma radioaktiivsete jäätmete käitlemise poliitika kujundamisel kasutanud ka IAEA eksperthinnanguid ja loomulikult sõltume oma spetsialistide väljaõpetamisel IAEA poolt pakutavatest koolitustest. Ja Paldiskis siis nõukogude ajal asunud tuumaallveelaevade meeskondade väljaõppekeskuse 2 tuumareaktori kütus viidi küll õnneks Eestist ära Venemaale, aga Eesti ülesandeks jäi nende reaktori sektsioonide lammutamine ja objekti puhastamine. Et reaktori sektsioonide lammutamiseks on vajalik eelnevalt Eestisse rajada nende pikaajaliseks ohutuks hoiustamiseks mõeldud lõppladustuspaik. Ja selle ehitamiseks on ettevalmistusi Eestis juba praegu alustatud ja lõppladustuspaik peaks valmima 2040. aastaks. Ja selle rajamisel loodame samuti väga palju ka IAEA ekspertteadmistele ja abile. Ma ütlen ka kohe ära, et Paldiski reaktorite ohutustamiseks rajatav lõppladustuspaik ei ole mõeldud ega ei ole sobilik kasutatud tuumakütuse ehk siis niinimetatud tuumajäätmete ladustamiseks. Ja kui Eesti otsustab kasutusele võtta tuumaenergia, siis tuleb tuumakütuse ladustamiseks leida mingi teine lahendus, mille ühest võimalikust variandist kuulsime ka äsja Chris Parkeri ettekandes. Minu ettekande lõpetuseks jõuamegi IAEA rollini Eestis tuumaenergia kasutuselevõtu võimaluste uurimisel. Nagu minister Tõnis Mölder oma avakõnes kinnitas, siis on Keskkonnaministeerium saanud Vabariigi Valitsuselt ülesande moodustada tuumaenergia töörühm. Ja riikide abistamine tuumaenergia kasutusele võtmisel ja selle otsuseni jõudmisel ongi üheks IAEA põhitegevuseks. Ja Eestis tuumaenergia kasutusele võtmise võimaluse uurimisel on meil siis võimalik kasutada IAEA juhendmaterjale, standardeid ja lisaks pakub IAEA abi ka riikliku seisukoha kujundamisel, õigusaktide väljatöötamisel ja spetsialistide koolitamisel. IAEA pakub riikidele ka erinevaid tuumaohutusega seotud auditeid, näiteks INIR audit, mis on mõeldud riikliku tuumaohutuse taristu valmisoleku hindamiseks. Ja kõiki neid IAEA poolt pakutavaid võimalusi plaanime tuumaenergia töörühmas ka kasutada. Ja me võime öelda, et IAEA hoiab Eesti tuumaenergia kasutusele võtmise analüüsimisel teravalt silma peal. Ja et see protsess oleks läbipaistev, järgitaks standardeid, kõik vajalikud huvirühmad oleks kaasatud ja vajalikud analüüsid tehtud. Ja seda siis selleks, et Eesti jõuaks tuumaenergia kasutusele võtmise osas ratsionaalse ja kaalutletud otsuseni, hoolimata sellest, et kas lõpptulemuseks on meie poolt siis tuumaenergiale jah või ei. Aitäh!
Reelika, suur tänu selle väga hea ülevaate eest. Ma arvan, et paljud inimesed ei tea, kui tihe on tegelikult Eesti ja Rahvusvahelise Aatomienergia Agentuuri omavahelised suhted. Võib-olla üks kiire küsimus enne, kui me läheme pausile. Ja sa mainisid seda lõpust, et IAEA hoiab Eesti arengutel teravalt silma peal. Võid sa meile öelda, mida agentuur asjade arengust arvab?
Agentuur on võtnud nii nagu IAEA põhirolliks on, et ta väga toetava hoiaku ja väga positiivse. Et me oleme juba saanud väga palju häid soovitusi ja materjale, et millele tugineda ja on loodud ka kontakt meil tuumaenergia töörühma ja IAEA vahel. Et kindlasti hakkab töörühma liikmete ja IAEA vahel toimuma siis tihe koordinatsioon. Et saame sealt poolt siis häid näpunäiteid ja nõuandeid, et kuidas jätkata ja milliseid analüüse tellida ja neid analüüse pakub ka IAEA. Et seni on IAEA olnud Eesti arengute suhtes väga soosival ja positiivsel seisukohal.
Rõõm kuulda ja jõudu ja jaksu töörühma töös.
Aitäh!
Meie omalt poolt aga läheksime nüüd pausile ja kuigi paus on jäänud mõnevõrra lühemaks, siis loodetavasti saame kõik hakkama ja ootame teid tagasi kell 14.20.
It's like half the people that were out there, saying, no nukes and shut down the power plants. They're now realizing that some would say, nuclear is the best way to go for energy for the future. So I think it's natural to re-examine your beliefs as you age up.
Senator Booker, I wanted to ask you about nuclear energy. You are a proud proponent of nuclear energy, have argued it's necessary to wean us off the fossil fuel economy. But you have a lot of environmental activists who are scratching their heads at your support for nuclear energy, particularly around the issue of nuclear waste. Here in South Carolina, for example, there are 35 million gallons of nuclear waste being held at a nuclear reserve south of Aiken. Environmental activists have been fighting it for years. You've got Savannah River. And of course, we're talking about communities, primarily low-income communities of color, who are dealing with nuclear waste in their own backyards, from New Mexico to Yucca Mountain to right here. What is your answer to the fact that there is no solution in dealing with nuclear waste?
Well, first of all, you're a little bit mischaracterizing my views. I'm a realist that tells you right now the biggest existential threat to humanity is climate change. 50% of our non-carbon producing power right now is nuclear. And so as some of my other opponents want to do is just get rid of it, it's going to push us back to being more reliant on fossil fuels and make this, our ability to reach our climate goals, impossible. We saw what happened in Vermont when they cut down the Yankee plant there. Their carbon footprint expanded pretty significantly. So I look forward to phasing out nuclear waste and nuclear energy. But to do it right now, when we are in a race and have a 12-year race to meet our climate goals, The damage done to poor and vulnerable communities is significantly worse coming from climate change than it is the crisis of nuclear energy. If you want to weigh your poisons right now, the one that's coming towards us like a barreling freight truck of climate change, the one that my community in Newark is feeling right now because temperature rises, asthma rates that are off the charts. And let me tell you something about asthma. As a guy that knows what it's like in emergency rooms with black children dying at 10 times the rate than white children of asthma complications. So for me, nuclear energy, it's just common sense to me right now.
To build new power plants?
No, well, let's be clear. The nuclear energy of the plants we have now, designed in the 60s and the 70s and the 80s, is very different than the new modular nuclear energy plants that are being proposed. Now, those actually have a much different, they can actually take spent fuel rods and re-engage them for usage. The frontiers of nuclear science is not something we should just shut down. We should continue to investigate. Is there going to be eventually a safe way to do this? So I don't mind exploring the future. I'm one of these people that considers myself a futurist. Why? Because you have two choices in life: to let the future happen to you, or to shape the future and make sure it happens in a way that's just. So this to me is a very, very simple equation. I've got a 12-year problem to solve. And if anybody wants to get rid of nuclear energy, tell me how you are going to replace 50% of the non-carbon producing power that we would have right now. Because what you're going to do, you're going to send us back to coal and oil. And I refuse to go backwards in the cause of environmental justice.
The first thing we must do is to say goodbye to fossil fuels. In Finland, we will build the world's first fossil-free welfare society. Our long-term energy policy goal is to phase out the use of fossil fuels in the energy sector and move towards an emission-free energy system. In electricity production, we have already taken big steps. In 2018, nearly 80% of Finland's electricity production was based on carbon-free energy sources. 46% of energy was produced by renewables and 32% with nuclear power. However, as a country with cold winters, heating is a big issue that we have to focus on. In the same year, 2018, 53% of district heat was produced with fossil fuels and peat. This is why our government is investing significantly in policy measures to decarbonize our heat production.
Hey guys, so a lot of you have been asking about my makeup routine. The most important thing is to make sure you wash your face really well because we want those pores as clean as we want our electricity. And the best way to get that is to use this cleanser called Stop Shutting Down Nuclear Plants for Christ's Sake. It's carbon-free, emission-free, pollution-free electricity. Then I use this plant-based serum called When a Nuclear Plant is Shut Down, it is replaced by fossil fuels. That's bad. And I just rub this on my face because we all need some goddamn moisture in this quarantine. Then I put some foundation and conceal, like Germany trying to conceal the fact that they still have one of the dirtiest electricities in Europe, probably because they focus on shutting down nuclear instead of coal plants. Now let's do some blush, or we can just naturally blush by thinking of all the countries who already have pretty clean electricity, including France, Sweden, and Finland. They must be doing something right, but God, what could that be? So I have a crazy idea. How about instead of shutting down perfectly fine nuclear plants, we focus on shutting down coal or gas plants, which actually cause climate change. Oh, and don't forget the mascara, because it's not a look without the mascara. Mwah!
I know it's been long assumed that those who champion the environment are opposed to nuclear power. But the fact is, even though we've not broken ground on a new nuclear power plant in 30 years, nuclear energy remains our largest source of fuel that produces no carbon emissions. To meet our growing energy needs and prevent the worst consequences of climate change, we'll need to increase our supply of nuclear power. It's that simple.
Énergétique et écologique passe par le nucléaire. Pourvu que l'on progresse sur la gestion des déchets, sur la sûreté, et je vous sais là aussi pleinement mobilisé, l'énergie nucléaire est une énergie décarbonée, une énergie sûre.
The weather is already very uncertain. It just gets worse
in a negative way.
Do you think politically nuclear power will ever be something that will be a completely viable solution? Because it solves a lot of the problems.
If people were rational, yes, which means there's like a 30% chance. Nuclear, the current reactors actually have a better safety record than any other source of electricity. They are not the best.
Except that when there is a problem, there's a problem.
Chernobyl is the only case where you have radiation release killing people. Coal kills a lot of people, natural gas pipelines blow up and kill people. Per kilowatt hour, it's the safest. But I don't care about that. Those reactors can blow up. You can design a reactor that is not capable. That is, there's no high pressure in the reactor anywhere. These existing reactors have lots of high pressure, and they need humans sitting there pushing buttons. You can design a reactor that by multiple physics principles, that the radioactive material never leaves the reactor. You have, the heat pool and the low pressure anyway. And so people at least should be open-minded that a next generation reactor can have far better economics, far better safety, no proliferation, no waste problem. But we need lots of innovations to solve climate change. If we have certain other breakthroughs like in energy storage, you can actually create a zero-emission grid without nuclear. But it's way more straightforward. It's way less expensive. It's way quicker if a meaningful part of it is this breakthrough new generation reactor.
It's like half the people that were out there, saying, no nukes and shut down the power plants, they're now realizing that some would say, nuclear is the best way to go for energy for the future. So I think it's natural to re-examine your beliefs as you age up.
Senator Booker, I wanted to ask you about nuclear energy. You are a proud proponent of nuclear energy, have argued it's necessary to wean us off the fossil fuel economy. But you have a lot of environmental activists who are scratching their heads at your support for nuclear energy, particularly around the issue of nuclear waste. Here in South Carolina, for example, there are 35 million gallons of nuclear waste being held at a nuclear reserve south of Aiken. Environmental activists have been fighting it for years. You've got Savannah River. And of course, we're talking about communities, primarily low-income communities of color, who are dealing with nuclear waste in their own backyards, from New Mexico to Yucca Mountain to right here. What is your answer to the fact that there is no solution in dealing with nuclear waste?
Well, first of all, you're a little bit mischaracterizing my views. I'm a realist that tells you right now the biggest existential threat to humanity is climate change. 50% of our non-carbon producing power right now is nuclear. And so as some of my other opponents want to do is just get rid of it, it's going to push us back to being more reliant on fossil fuels and make this, our ability to reach our climate goals, impossible. We saw what happened in Vermont when they cut down the Yankee plant there. Their carbon footprint expanded pretty significantly. So I look forward to phasing out nuclear waste and nuclear energy. But to do it right now, when we are in a race and have a 12-year race to meet our climate goals, the damage done to poor and vulnerable communities is significantly worse coming from climate change than it is the crisis of nuclear energy. If you want to weigh your poisons right now, the one that's coming towards us like a barreling freight truck of climate change, the one that my community in Newark is feeling right now because temperature rises, asthma rates that are off the charts. And let me tell you something about asthma. As a guy that knows what it's like in emergency rooms with black children dying at 10 times the rate than white children of asthma complications. So for me, nuclear energy, it's just common sense to me right now.
To build new power plants?
No, well, let's be clear. The nuclear energy of the plants we have now, designed in the 60s and the 70s and the 80s, is very different than the new modular nuclear energy plants that are being proposed. Now, those actually have a much different, they can actually take spent fuel rods and re-engage them for usage. The frontiers of nuclear science is not something we should just shut down. We should continue to investigate. Is there going to be eventually a safe way to do this? So I don't mind exploring the future. I'm one of these people that considers myself a futurist. Why? Because you have two choices in life: to let the future happen to you, or to shape the future and make sure it happens in a way that's just. So this to me is a very, very simple equation. I've got a 12-year problem to solve. And if anybody wants to get rid of nuclear energy, tell me how you are going to replace 50% of the non-carbon producing power that we would have right now. Because what you're going to do, you're going to send us back to coal and oil, and I refuse to go backwards in the cause of environmental justice.
The first thing we must do is to say goodbye to fossil fuels. In Finland, we will build the world's first fossil-free welfare society. Our long-term energy policy goal is to phase out the use of fossil fuels in the energy sector and move towards an emission-free energy system. In electricity production, we have already taken big steps. In 2018, nearly 80% of Finland's electricity production was based on carbon-free energy sources. 46% of energy was produced by renewables and 32% with nuclear power. However, as a country with cold winters, heating is a big issue that we have to focus on. In the same year, 2018, 53% of district heat was produced with fossil fuels and peat. This is why our government is investing significantly in policy measures to decarbonize our heat production.
Hey guys, so a lot of you have been asking about my makeup routine. The most important thing is to make sure you wash your face really well because we want those pores as clean as we want our electricity. And the best way to get that is to use this cleanser called Stop Shutting Down Nuclear Plants for Christ's Sake. It's carbon-free, emission-free, pollution-free electricity. Then I use this plant-based serum called When a Nuclear Plant is Shut Down, it is replaced by fossil fuels. That's bad. And I just rub this on my face because we all need some goddamn moisture in this quarantine. Then I put some foundation and conceal, like Germany trying to conceal the fact that they still have one of the dirtiest electricities in Europe, probably because they focus on shutting down nuclear instead of coal plants. Now let's do some blush, or we can just naturally blush by thinking of all the countries who already have pretty clean electricity, including France, Sweden, and Finland. They must be doing something right, but God, what could that be? So I have a crazy idea. How about instead of shutting down perfectly fine nuclear plants, we focus on shutting down coal or gas plants, which actually cause climate change. Oh, and don't forget the mascara, because it's not a look without the mascara. Mwah!
I know it's been long assumed that those who champion the environment are opposed to nuclear power. But the fact is, even though we've not broken ground on a new nuclear power plant in 30 years, nuclear energy remains our largest source of fuel that produces no carbon emissions. To meet our growing energy needs and prevent the worst consequences of climate change, we'll need to increase our supply of nuclear power. It's that simple.
Énergétique et écologique passe par le nucléaire. Pourvu que l'on progresse sur la gestion des déchets, sur la sûreté, et je vous sais là aussi pleinement mobilisé, l'énergie nucléaire est une énergie décarbonée, une énergie sûre.
The weather is already very uncertain. It just gets worse in a negative way.
Do you think politically nuclear power will ever be something that will be a completely viable solution? Because it solves a lot of the problems.
If people were rational, yes, which means there's like a 30% chance. The current reactors actually have a better safety record than any other source of electricity. They are not the best.
Except that when there is a problem, there's a problem.
Chernobyl is the only case where you have radiation release killing people. Coal kills a lot of people. Natural gas pipelines blow up and kill people. Per kilowatt hour, it's the safest. But I don't care about that. Those reactors can blow up. You can design a reactor that is not capable. That is, there's no high pressure in the reactor anywhere. These existing reactors have lots of high pressure, and they need humans sitting there pushing buttons. You can design a reactor that by multiple physics principles, that the radioactive material never leaves the reactor. You have the heat pool and the low pressure anyway. And so people at least should be open-minded that a next generation reactor can have far better economics, far better safety, no proliferation, no waste problem. But we need lots of innovations to solve climate change. If we have certain other breakthroughs like in energy storage, you can actually create a zero emission grid without nuclear. But it's way more straightforward. It's way less expensive. It's way quicker if a meaningful part of it is this breakthrough new generation reactor.
It's like half the people that were out there, saying,
Tere tulemast tagasi. Loodan, et teie paus oli sama viljakandev kui meie oma. Ja sarnaselt ettekandele, mis eelnes pausile, jätkame ka nüüd täiesti kodumaises eesti keeles ning vaatame edasi, milliseid uuringuid on jällegi tehtud eelmise aasta jooksul. Ehk siis jätkame kodumaise teadusega ja vaatame täpsemalt, mis tolku on moodulreaktoritest ka peale elektrienergia tootmise. Ehk siis annan hea meelega sõna üle kahele järgmisele kõnelejale, Allan Vraager ning Rainer Küngas, kes mõlemad esindavad Fermi energiat. Palun.
Tere, minu poolt. Minu nimi on Allan Vraager ja töötan Fermi energias soojusenergeetika insenerina. Ja mina räägin teile, kas on võimalik kaugkütet ja tööstusauru saada moodulreaktoritest. Et uuring, mis sai läbi viidud firmasiseselt, ongi see, et leida vastus sellele, kas on võimalik, mõttekas ja tasuv kaugkütte soojust ja tööstusauru toota väikesest reaktorist. Ja kas meil on tarbijaid, kes oleks nõus seda tarbima ja kes need siis oleksid? Kaugküttest üldiselt, et maailmas on tuumajaamades kaugkütet kasutatud mitte just väga suurel määral, kõige rohkem Venemaal, aga Ukraina, Tšehhi, Slovakkia, Ungari, Bulgaaria ja Šveitsi on ka kasutajad ja eelmisel sügisel liitus ka Hiina. Haiyangi tuumaelektrijaamas hakati kaugkütte soojust kõrval asuvale asulale tootma. Eestis on kütmist vaja, nagu te kõik kohalikud teate, siis meil väljas on praegu väga krõbe talveilm, -2-kohalised numbrid enamus Eestist. Ja Eestis on 230 kaugkütte piirkonda ja 70% kütmiseks tarvitavast soojusest tarvitati kaugküttes ja kokku on see 4400 gigavatt-tundi 2018. aastal. Ehk see on päris suur number. Ja enamus sellest või ligi üle poole on biomassist, siis on maagaas ja ülejäänud on siis kas siis põlevkivi või siis kütteõli. Ja Konkurentsiameti kooskõlatud soojuse piirhinnad jäävad vahemikku 35 kuni 87 eurot megavatt-tunni eest. Nii, uuringu lähtekohad olid see, et me võtsime ühe asukoha, milleks siis oli, kui aasta tagasi me hakkasime seda tegema, oli Kunda ligidal asuv Lontova, sellepärast see tundus siis kõige potentsiaalsema asukohana. Reaktori tüübiks sai valitud uuringu jaoks General Electric Hitachi PBRX 300. See põhjus oli lihtsalt selles, et selle reaktori tüübi kohta oli kõige rohkem andmeid ja ka valmistajaga koostöö laabus. Toodetava elektri omahind uuringutes sai võetud $35 megavatt-tund ehk siis 32 eurot megavatt-tund, millel lubab garanteerida reaktori valmistaja General Electric Hitachi. Nii. Tarbimine, tarbijad ja torustik. Ehk siis, kui hakata vaadata Kunda ümbrust, siis kõigepealt muidugi on Kunda päris suur tarbija, 14,8 gigavatt-tundi tipuvõimsusega 7 megavatti. Aga kui hakata kaugkütet tegema, et siis võiks nagu veidi suuremat soojushulka toota. Ja siis ainuke selline piisavalt lähedal asuv suur tarbija oleks siis Rakvere linn, mis siis koos plaanis olevate võrkude liitumistega, seepärast Rakveres on väga palju väikseid võrkusi, tuleb siis soojuslikuks aastaseks võimsuseks kuskil 51 gigavatt-tundi ja tipuvõimsus 22,6 megavatti. Sai uuritud ka läheduses olevaid tööstusi ja kohalike ärimeestega ühendust võetud, et kas mingeid arendusi ka seal on ja on ka tööstusest potentsiaalseid liitujaid 130 gigavatt-tunni ulatuses ja 31 megavatti ulatuses. Kas need kõik teoks saavad, seda muidugi nii varases staadiumis ei saa öelda. Torustiku pikkus Rakverre Kundast on kuskil ligikaudu tuleks 24 kilomeetrit ja läbimõõduks oleks 0,5 meetrit selliste tarbimiste juures, mis on praeguse uuringu tulemustel leitud. Toru läheb Lontova juurest Klindi peale, möödub lõuna poolt tselluloositehast ja tsemenditehast ja siis paralleelselt raudteega kuni Rakvereni välja ja Rakvere linnas siis mööda tänavaid. Et see marsruut ei ole täpselt paigas, aga see oleks selline kõige perspektiivikam. Rakvere asub suht kõrgel, et kui tuumajaama juures on tulevase reaktori juures oleks maapinna kõrgus kuskil minimaalselt 3,5 meetrit, siis Rakvere linnas, kus on küttevõrgustik, on maapinna kõrgus üle merepinna juba 80 meetrit, ehk siis tõus on päris suur ja see võib mõningaid tehnilisi erilahendusi nõuda. Nii, küttesoojuse tootmine siis. Kuidas seda siis saadakse? Et aur võetakse mitte otse tuumareaktorist, vaid turbiini vaheltvõtust ja seoses sellega, et keevaveereaktorist tulev aur on kelgelt radioaktiivne, on turvalisuse kaalutlusel, siis ohutuse kaalutlusel vahele pandud vahekontuur, et see aur ei ole samas soojusvahetise veega, mis läheb kaugküttevõrku. Ehk vahepeal on veel üks veekontuur, et vähendada avarii olukorras ohtu, et radioaktiivsus lekib väljapoole jaama. Küttevõrgu ehituse maksumuse hindas Merko ehitus Eesti ja tema leidis, et kõige kallimaks osaks saab olema torustiku enda ehitus, sellepärast et torustik tuleb rajada paega sisse, paeklindi sisse ja see võib päris kalliks minna. Soojusvahetite ja tuumajaama siseste sõlmede ehituse maksumuse hindas Estank aktsiaselts ja meie arvutuste ja nende panuse järgi kokkuvõttes saab öelda, et täiesti tasub ära kütusesooju tootmine väikese moodulreaktoritega. Ja majanduslikult on see tasuv nii meile kui ka tarbija saab soodsama küttehinna. Teine asi, mis me vaatasime, oli tööstusaur. PBRX 300 reaktorist saab kõige kõrgemat tööstusauru, mida tarbijale anda, on 200 kraadi Celsius. See on siis turbiini esimesest vaheltvõtust. Kaasaegsete torudega, mis on siis toru torus, vahepeal vaakum ja isolatsioon, saab tööstusauru edukalt transportida mitmete kilomeetrite kaugusele. Samamoodi lisandub tuumajaama väikese moodulreaktori juurde vahekontuur, nagu oli kaugkütte korral. Soojusvahetite maksumuse hindas järjekordselt ära Estank, aurutorustiku hinna pakkumine sai küsitud Saksa ühelt juhtivalt aurutorude valmistajalt ja üldehituse maksumuse hinnangu tegi aktsiaselts Merko ehitus Eesti. Ja sarnaselt kaugküttega on järelduseks jälle, et tööstusauru saab toota, on võimalik toota ja see on majanduslikult tasuv nii meile kui ka potentsiaalsetele tarbijatele. Kui tööstusauru tarbimine aastas jääb üle mõnesaja gigavatt-tunni. Nii. Ja tulevikus, kui kasutada juba 4. põlvkonna reaktoreid, siis saab soojust kätte 600 kraadi ja osade tüüpide juures rohkemgi, mis avardab veelgi võimalusi kasutada seda soojust tööstuses erinevate produktide tootmiseks, millest üks on vesinik ja millest räägib järgmine esineja. Aga tänud kuulamast!
Austatud kuulajad, minu ettekande teemaks on vesinik, täpsemalt vesiniku tootmine tuumaenergia abil. Ja ma tahtsin oma ettekannet alustada siis slaidiga, mis näitab, et missugused on need kõige raskemini dekarboniseeritavad sektorid, kus tulevikus vesinikku võiks kõige rohkem vaja olla. Üheks selliseks majandusharuks on tsemendi tootmine, mille CO2 emissioonid moodustavad täna umbes 7% maailma CO2 emissioonidest. Samuti juba Vattenfalli asepresidendi poolt mainitud terase tootmine, mille CO2 emissioonid on umbes 6% maailma CO2 emissioonidest, keemiatööstus 5% ja siis veondus 8%. Et nagu öeldud, siis neid majandussektoreid seob tõsiasi, et neid on väga raske dekarboniseerida. Tsementi, terast ja kemikaale on väga raske toota, ilma et selle käigus eralduks siis CO2, sest et CO2 tekkimine on juba nende vastavate reaktsioonivõrranditega paika pandud. Näiteks kui terase tootmine, siis rauamaak pluss süsinik võrdub raud pluss CO2. Ja samuti veonduses, kui sõiduautosid on võrdlemisi lihtne akude peal tööle panna, siis mida raskemaks muutuvad need sõidukid, laevad, lennukid, rongid, siis seda keerulisemaks muutub nende dekarboniseerimine. Ja siin võiks siis madala CO2 jalajäljega vesinik olla üheks huvitavaks lahenduseks. Vesinikku saab toota elektrolüüsi teel. Näiteks siis 100 megavatti elektri abil saab elektrolüüsidel toota umbes 1,7 tonni vesinikku tunnis. Ja sellisel viisil toodetud vesiniku kliimasõbralikkuse määrab siis ära see, et missugune on selleks elektrolüüsis kasutatava elektri CO2 jalajälg. Kui elekter pärineb põlevkivijaamast, siis ei ole kliima seisukohalt selline vesiniku tootmine mõttekas. Kui aga vesinik pärineb või kui elekter pärineb siis madala CO2 jalajäljega jaamast, siis on see kliimasõbralik. Selliseks jaamaks võiks olla näiteks kas tuumajaam või siis taastuvad energiaallikad. Kui sellisel teel saadud vesinik panna reageerima õhulämmastikuga, on võimalik toota ammoniaaki ja 100 megavatti abil on võimalik toota 9 tonni ammoniaaki tunnis, mis vastab siis umbes 4 raudteevagunile ööpäevas. Ja ammoniaak on siis selline väga perspektiivikas kütus tuleviku merendussektoris. Ning kolmandaks siis on võimalik toota elektrolüüsidel toodetud vesinikust, kui see kombineerida CO2-ga katalüsaatori juuresolekul vedelkütuseid. Ja siis umbes suuruses 4 tonni vedelkütust tunnis. Sellise koguse vedelkütuse abil on võimalik siis hoida pidevalt töös kas 14 reisilennukit või siis umbes 3000 veoautot. Ja tuumaenergia eeliseks teiste taastuvate energiaallikate ees vesiniku tootmisel on see, et tootmismahud on ette ennustatavad ja et on tagatud varustuskindlus. See vesiniku maht, mis toodetakse, see ei sõltu sellest, kas päike paistab või tuul puhub, vaid see on kindel, et sa saad selle vesiniku siis, kui sul seda vaja on. Ja tänu sellele sobib siis tuumaenergia peal toodetud vesinik väga hästi kokku tööstusprotsessidega, kus on vajalik siis toorme pidev juurdevool. Ning võrreldes siis teiste tehnoloogiatega on tuumajaama lahendus ka väga kompaktne. Okei, mis on siis sellisel viisil toodetud vesiniku omahind? Et sellele küsimusele vastata tuleb teha kõigepealt terve rida eeldusi. Olen siin eeldanud, et kasutame siis vesiniku tootmiseks leelisellist elektrolüüsi, et jaam valmib aastal 2028, et vesiniku tootmises kasutatakse elektrit hinnaga 35 eurot megavatt-tunni kohta, et jaama esialgne kasutegur on 57%, et see töötab 8000 tundi aastas ning et investeering makstakse tagasi 15 aasta jooksul. Sellisel juhul on vesiniku omahinnaks umbes 3,2 eurot kilo kohta, millest siis suurima osa moodustavad tootmiskulud ja umbes 0,3 eurot hoolduskulud ja 0,4 eurot kapitalikulud. Kapitalikuludest omakorda moodustab suure osa elektrolüüseri omahind. Tootmiskulud on suures osas seotud siis elektrikuluga, vähesemal määral ka panustab veepuhastuse maksumus ja siis hoolduskulud jaotuvad umbes võrdselt siis jooksvate hoolduskulude, tööjõukulude ja siis elektrolüüseri vahetuse vahel. Ja mis on siis vesiniku hinda kõige enam mõjutavad parameetrid, seda olen proovinud näidata sellel joonisel, sellisel tornado graafikul, nagu seda kutsutakse. Nagu jooniselt näha, siis kõige rohkem mõjutab vesiniku hinda elektri hind. Kui elektri hind langeb 35 eurolt megavatt-tunnilt 5 euro võrra 30 euroni megavatt-tunni kohta, siis väheneb vesiniku hind 31 sendi võrra. Ja samamoodi, kui elektri hind tõuseb 5 euro võrra megavatt-tunni kohta, siis tõuseb vesiniku hind 31 sendi võrra. Et elektri hind mõjutab vesiniku hinda väga palju. Teine oluline faktor on siis kasutegur, elektrolüüseri kasutegur. Kui kasutegur suureneb 57%-lt 60%-le, siis see alandab vesiniku hinda 12 sendi võrra ja siis samaväärne 3% võrra kasuteguri alanemine suurendab siis vesiniku hinda 13 sendi võrra. Aga on ka huvitav näiteks vaadata, et tarne aasta, see tähendab, et mis aastal see vesiniku elektrolüüser ehitatakse, see mõjutab vesiniku hinda võrdlemisi vähe, kuigi see vesiniku tehnoloogia muutub iga aastaga järjest odavamaks. Aga selle analüüsi järgi ei ole mõtet oodata vesiniku või elektrolüüseri ehitamisega ainult seetõttu, et hind alaneb. Nii et kokkuvõtvalt siis vesinik on vajalik raskesti dekarboniseeritavate majandusharude CO2 jalajälje vähendamiseks. Rohelise vesiniku abil saab toota kliimasõbralikke kütuseid nagu ammoniaak ja vedelkütuseid. Tuumaenergia abil toodetud vesinik sobib hästi kasutamiseks tööstusprotsessides. Antud eelduste puhul on vesiniku omahinnaks umbes 3,2 eurot kilogrammi kohta, millest siis 80% on elektri hind. Ja lõpetuseks, elektrodüüsiteel toodetud vesinik ei ole ilma CO2 maksude või siis kohustuslike tootmiskvootideta täna turul konkurentsivõimeline. Et siin võib-olla võrdluseks on huvitav öelda, et tavalisel fossiilkütustest toodetud vesiniku hind on täna Euroopa Liidus umbes 2 eurot kilogrammi kohta. Ja selleks, et siis ainuüksi CO2 maksudeta need hinnad võrdsustuksid, peaks CO2 kvootide hind olema umbes 135 eurot tonni kohta. Aitäh!
Nii Allen kohapeal kui Rainer digitaalselt, suur tänu teile mõlemale selle ettekande eest. Üks selline küsimus, me räägime siiski tavaliselt tuumajaamadest selles võtmes, et toota elektrienergiat. Nüüd räägime me kõikidest teistest võimalikest rakendustest samamoodi. Eesti tingimustes, kas nende teiste rakenduste peale mõtlemine mõjutab kuidagi potentsiaalselt tuumajaama konkurentsivõimet või tema mõistlikkust?
Ma arvan, et eriti ta ei muuda, et kui näiteks soojust toota, et siis kõik sõltub sellest, et kuidas elektri hinnal on. Kas tasub toota või ei tasu toota, aga kui sa juba oled kuhugi toru ära vedanud, siis sa teed lepingut pikaajaliselt, siis sa pead tootma. Ja kas ta nüüd oleks kasumlikum selle asemel elektrit toota, seepärast osa sellest elektrist jääb tootmata ja võrku andmata, kui me soojust toodame. Et see on selline ennustamise küsimus, et kas keegi oskab ette näha, mis see elekter hakkab maksma 5, 10, 20, 30 aasta pärast?
Kui ma keeraksin selle küsimuse pea peale ja küsiksin hoopis niipidi, et kas oleks mõistlik ehitada tuumajaamu ainult nende teistsuguste rakenduste jaoks ja täielikult elektri tootmine lõpetada?
Kui võtta, et mingi väike asula ja mingi väike reaktor püsti panna ja seda on vaja, asulat on vaja kütta, et siis see kogu see turbiininduse ja elektritootmise asi on lisainvesteering, et võib juhtuda küll, et tuleb odavam lihtsalt soojust toota, kui veel elektrit toota.
Selge. Aitäh teile mõlemale uuesti. I believe it makes more sense for me to continue in English and to introduce our next speaker. Now, our next speaker will not be presenting the results of a scientific study, but it doesn't mean that he is a stranger to science. He is an independent, award-winning science and non-fiction writer and an energy analyst. So I would be very intrigued to find out whether Rauli Partanen is on the line with us.
Yes, here I am, just sharing the screen. Does it look about right? Can you hear me? Can you hear me? You should be able to hear me, right? Okay. I'm assuming that's a yes. So I'm going to talk a little bit on nuclear from a different perspective, that of an environmental activist. And without further ado, let's get started. It's so nice to be here, and thanks for the invite, and I hope everybody is having a good day so far. I know I am. So let's start with a small introduction. You did notice that I'm representing the Eco-Modernist Society of Finland. So what's eco-modernism? We are a politically and economically independent science and evidence-based environmental organization. So founded in 2015 and basically by people who got a little bit frustrated with the ideological baggage that many of the traditional environmental organizations have with them. So we are very sharply science and evidence focused. About me, as mentioned, I'm a science writer, mainly on energy and climate, and recently quite a lot about nuclear. And the latest book, The Dark Horse, is also coming out in Estonian soon, so stay tuned for that. And as a day job, activism is right now not my day job, but I lead Think Atom, which is an independent non-profit think tank, and we think a lot about how to decarbonize our society and energy systems with nuclear reactors, small, advanced, big, whatever. And here's some publications that I have recently done, and you can check them out from the website as well. They are free to download. Okay, well, so Stand Up for Nuclear. It's an event that have been held twice. So last September and the one before that. And last year it went truly global. 28 countries, 67 cities, 10 virtual events. You can see that there's Tallinn, Tartu, Helsinki, a lot of places around the Baltic Sea, about 1,000 participants and up to 15,000 attendees. So it's growing quite fast, and you can find it in very surprising locations as well. Regarding how we were received in sort of mass media or mainstream media, it was quite positive. Some of the local events went to national TV news, and some newspapers covered them. This, of course, depends a lot on the local environment, how these things are replaced. I'm especially glad that Germany covered the events as much as they did, because the German situation is quite problematic, as we learned, for example, from Staffan Quist's presentation earlier today. So it's getting the attention, and then we just need to keep on pushing. But why would somebody want to stand up for nuclear? Can't nuclear stand up for itself? I mean, well, the problem here is that it hasn't been standing up for itself. So activists around the world who realize that actually nuclear is the technology that can lift all humans out of poverty while also protecting the natural environment. And it's basically the best option to do that. And somebody should stand for it. Because in spite of these kind of characteristics that nuclear has, it's heavily under attack in European countries, as well as on the EU, European Commission and Parliament levels, in Asia, in North America. There's a lot of opposition. And I'm not sure if it's in spite of this, the good qualities that nuclear has, or if it's because of those. Depends on the day and how you look at it, I guess. And for politicians, it's been way easier to kind of please or agree with the anti-nuclear sentiment for a long time, because nobody has been challenging that for like the last 40 years, almost nobody, that is. So it's become the norm to kind of agree, yeah, we shouldn't have nuclear, and we don't need it, and so forth. But and we're kind of stuck in that mindset. And even if right now we have these reports and studies coming out that we need a lot of new nuclear, much more actually than the nuclear industry is prepared to deliver so far, to mitigate climate change effectively. So the point of standing up for nuclear as civil society, publicly and visibly, is that it gives politicians and policymakers kind of license, social license, to support it as well. So it's not controversial anymore. It's actually what my personal aim is, to have it controversial not to support nuclear, because that's what it actually is. So we need to shift that debate on its head. Right. What's European Union policy going towards? I mean, there's a lot of talk of fossil-free EU, but in reality, you have Belgium and other countries, Germany, phasing out their nuclear fleets and then subsidizing new gas plants and subsidizing gas pipelines and building more fossil fuel infrastructure. So we are not going in the direction that we should be going at. Belgium, as a result of this, in a recent study by Ember, Belgium will be the only European country that will increase its emissions from electricity due to this policy of phasing out nuclear and subsidizing new gas plants. That's in the 2030 timeframe. So that gives you something to think. While actually the need for new clean energy is quite a bit higher than we many times think. So we already know that nuclear supplies about half of the clean electricity in Europe, and about 2/3 of European electricity is clean. But if we want to decarbonize, for example, our chemical industry, just this one industry, including petrochemicals, we will have, on the left side, you have clean power today. That's the whole little bit under 2,000 terawatt hours of clean power supplied in Europe. So if you want to have 85% emissions reductions from the processes of chemical industry, you need to build about as much again. And then if you want to actually decarbonize the fuels, like the raw material for the fuel, you maybe need to make hydrogen and synthetic fuels from that instead of using crude oil as the feedstock. Then you can multiply that by 5 times easily to get really carbon neutral chemical industry. And that's just one industry. So I think it's a horrible position to kind of be in when many countries are phasing out the biggest source of clean electricity, while we are facing this tremendous need for actually increasing clean electricity many times over in the next 30 years. So there's this kind of problem between the discussion and the reality. In Finland, we've been doing Stand Up for Nuclear as well. And as maybe many of you know, Finland is in a quite good situation, at least compared to many others. So nuclear has not been under attack for some years. It's generally quite accepted, even though it's doesn't receive much in the way of support. We have new project. We have the Olkiluoto 3, which hopefully will start up soon, but I've been saying that for a while. And then we have the Hanhikivi, hopefully getting construction license soon and starting the first concrete. So mainly in Finland, we stood for nuclear in solidarity with the European and other nations that are in a much worse situation. And then we also looked for some kind of way that we could push the envelopes of lead us forward, take the next steps, because right now, I mean, projects like Olkiluoto 3, that's not going to be enough. We need better projects. We need more projects, faster and more cost-effective projects. So we need to think how to do that. And that was our kind of team. We did this calculation, back of the envelope style, how much new electricity production capacity Finland will need by 2050. So we started with this roadmaps that all the major industries came up in Finland last year. So everybody published a roadmap, how they will decarbonize and how much clean energy they will need for that decarbonization so they would be in line with the government's targets of being carbon neutral by 2035 and way carbon negative by 2050. So we can start with the metal industry. That's about 10 terawatt hours, so one big reactor. The petrochemical industry, depending if you want to calculate the scope 3 emissions as well. So that's the crude oil. Replacing that instead of just all the processes, you could need something between 40 to 80 terawatt hours of clean electricity. And so that's almost as much as we have demand today. And in addition to that, we would like to replace about 20 terawatt hours of imports that we currently have. Then we have fossil fuel combined heat and power capacity that also does district heat, 15 terawatt hours, maybe 10 terawatt hours of retiring wind. So all the wind power that we have built and will build by 2025 will need to be retired and rebuilt somehow as well by 2050. The current fleet of nuclear reactors are getting old, so maybe we need to replace those around 2050 as well. If not, then that's good, but probably. And then we're going to electrify our transportation, which will take something between 5 and 10 terawatt hours. So, and we have about 20 terawatt hours now under construction. So we need about 10 big reactors worth of new reliable production capacity by 2050. And like I said, we don't want those to be Olkiluoto 3 type projects. We need them to be very good projects. And there's an opportunity here that we wanted to bring up in our kind of stand up for nuclear, is that if you have need for 10 big reactors or 30 small reactors or whatever, then you can plan serial production and you can plan the projects to make sense and then learn by doing, and instead of building one reactor here and another type of reactor there and always kind of paying the first expenses and first of a kind fees you have. So yeah, that's my presentation. Thanks for listening, and I'm happy to answer questions. Just stop sharing here.
Rauli, thank you very much for that balanced presentation. I would like to ask you just a couple of questions which are related to the good balance. And you work with non-fiction, you work with facts, and yet it would seem that those who are pro-nuclear and those who are against use a different set of facts to justify and to form their opinions. So if we assume that there is one set of facts, scientific facts, that is accurate, then how come there are so many Greens who are against nuclear, whereas those who are pro-nuclear see that renewable energy is a part of the solution? Where does this discrepancy come from?
Well, to start, in Finland, we actually have quite a bit of Greens who are for nuclear, and that's exciting. That Atte Harjanne that I interviewed in the study is a Green parliament member, and he ran for the parliament on an openly pro-nuclear platform. So it's developing, and we are hoping to get the rest of the Europe on board of this as well. But regarding the facts, they are not always same facts. But even if they are same facts, we need to realize that people come from different places. So somebody has some values and somebody else has some other values, and each of us has this kind of 20, 30, 40, 50 years of context in their life that they look at the facts through. So the same facts can be looked in many ways and interpreted in many ways. And that's something that has been very challenging as a communicator, is to how I account for this, and it's been a problem with the nuclear industry in particular, is that they just like to throw numbers at people as much as and fast as possible, and then they just assume that everybody will come from the same mindset and believe the numbers, but that never happens, almost never happens. So it's a small subset of the population that's this kind of engineering background that wants to have their information with numbers. So you have to have the values there, and you have to share those values and find a way not to convince people, but to make them able to convince themselves and change their mind about this. And so it's a very complex question. Could have done a presentation on that only.
All right, and I understand that you would like to talk more and more about this, but unfortunately we do have to finish here with this particular presentation. So thank you very much.
Thank you for the opportunity. Have a nice day.
Tänases päevas on järgi veel 2 väga huvitavat sessiooni, aga õnneks on minul võimalus nüüd jalgu puhata ja jälgida ülejäänud konverentsi kaamera tagant. Ehk siis ma annan jutujärje üle enda kolleegile, kes on teie jutujuht ülejäänud konverentsi vältel. Ehk siis Henri Ormus.
Tänud. So, good afternoon, good morning and good evening everyone, depending on which place of the world are you watching us. My name is Henri Ormus. I'm Vice President of European Nuclear Society, currently working in Fennovoima in Hanhikivi 1 nuclear power plant project where we build a large-scale nuclear power plant in Finland. And also I'm a co-founder of Fermi Energia. And I will be leading this discussion. I'm very glad to have here online with us Alan Woods, Director Strategy and Business Development at Rolls-Royce, Brett Kungelmas, Managing Director at Energy Impact Center, David Slegic, Senior Vice President Sales at GE Hitachi Nuclear Energy, and Mark Mitchell, President at USNC Power, and Scott Rasmussen, Director of Sales at NewScale SMRs. Welcome everyone. First of all, we will have a short introduction and overview of their respective designs and developments, and then we will head to the questions. So, Alan Woods, please, could you give us a little overview?
Sure, yeah, let me just see if I can share a single screen as well. Please let me know if this is showing. Can you see my screen?
Yes, wait.
Yes, okay, great. So, quick overview of our technology, and then I'll talk about where we are with our program. So first of all, our technology really encompasses exactly what we're trying to do here and why we embarked on this program 5 years ago. For us, our technology, our SMR program, is about delivering nuclear at low cost at a competitive market cost. So yes, we're using proven technology where we can. We don't want to introduce technologies which we know are going to be challenges to regulators or to operators. It's about simplification, standardization, and producing a factory fabricated product which is repeatable. That gives us a certainty in deliverability and a repeatable deliverable solution which we know we can meet our timeframes and costs with certainty. And all of that in the round makes our product investable to any form of customer, whether it be a utility seeking to attach this to a grid, or whether it be an industrial customer wishing to use our SMR for desalination, for hydrogen generation, for synthetic fuel production, for data centers, or for other heavy industrial electricity uses. So our approach to modularization is, as I mentioned, all about standardization. We have to address the whole power station. This isn't a reactor design project. This is a power station development program. It's about moving from very large one-off mega infrastructure projects to a factory repeatable product. So 90% of our power station is factory fabricated. That includes the civil structures, includes all the balance of plant systems, and of course the nuclear reactor part as well. It sits on an aseismic bearing to insulate it from the particular site conditions, and that's very important for repeatability. It means all of our modules are the same no matter where we build the plant, and that means we properly get that factory learner curve for those road transporter modules. They come to the site and we make use of our small footprint to assemble under what we call a site canopy, or our fourth factory. That is assembled and disassembled after the commissioning period. It's reusable, so it does have a cost, but we can use it 3 times. And that means that we assemble all the modules in a controlled environment. It takes us 4 years to build the plant on site, take down the site canopy, we finish commissioning it, and then it goes into operation. So that's our power station. Where we are at the moment, we're just completing the current phase of activities we're in, which has been a joint investment with UK government and our consortium partners. The UK Prime Minister announced in November the 10-point net zero plan, which included £250 million funding for the next phase of our programme. That will be matched by industry and some of our partners, and we will in turn set up a special purpose vehicle company. So the next phase of our programme will be to move all of the activity into a joint venture company. We will then enter genetic design assessment in the UK around Q3, Q4 this year. And of course, we will continue to support our customers in their ambitions and programs, both in the UK and internationally. So that's my brief intro. I hope I stuck to the few minutes. I shall stop sharing.
So let's continue with Brett, who will give an overview about the Open 100 SMR status and developments. Brett, please.
Great. Thank you, everybody, for having me. My name is Brett Kugelmass, and I'm the managing director of a Washington, D.C. based research institute called the Energy Impact Center. So we spent years, 3 years now, meeting with experts across the nuclear industry, trying to figure out, we've got this magical technology, why isn't it more prevalent? Why is it remain stagnated at 10% of global energy production? It's emissions free. Countries have shown that they can scale up and totally decarbonize their entire grid. It's abundant. Like, why? Why not more? And what we found is the primary reason that we don't build more nuclear around the globe today is because it is too expensive. And the reason that it's too expensive, and this is important, is because we, the nuclear industry, makes it more complicated than it needs to be. So we asked ourselves, what is the simplest possible nuclear power plant that can be built based on historical evidence? And so we assembled a team of fossil engineers that have built hundreds of power plants over their career. And we had them design a 100 megawatt biomass plant and just replace the boiler with the simplest possible nuclear reactor, which is a PWR, the same technology that operates in 300 power plants around the world today. And then we published all of our engineering work for public consumption, and I'll show you that right now. So anyone can go here. If you just go to www-open-100.com, I should say, www.open-100.com. And you can see here the engineering all laid out. You can go into systems and pull up different systems diagrams, download all of the engineering work that you would need. You can pull up equipment and download CAD files, or even reach out to vendors that we've pre-categorized for you. You can pull up an economic workbook where you can see the power plant costs down to the line item. And you can even pull up a construction schedule where you can see line by line exactly the time and work that needs to be done to bring one of these small 100 baby normal standard PWR plants together in under 24 months. So our basic concept here is that the nuclear technology does not need to be proprietary. We do not need a bunch of vendors leading the way, trying to sell complicated and expensive reactor systems, and then trying to figure out how to build a power plant around it. We just need the most simple, straightforward approach possible. And so we've published all of this work totally free, so hundreds of utilities and developers can just start building this all on their own And then we would just help from a financing and management perspective. So that's a brief overview, and I look forward to hearing more questions. Thank you.
Thank you, Brett. That's pretty amazing job that you have been doing. Thank you. So let's move on with David Sledzik, who will present the status about the BVR X300. David, please.
On where you are in the world. My name is Dave Sledzik. I'm the Senior Vice President of Sales for GE Hitachi's new plant business. At last year's conference, I was able to share some information on our SMR. Lots happened in the last year, and I'm going to give you a quick refresher on the technology before I get into what we've accomplished in the last year. The BWRX 300 is a 300 megawatt SMR and is the most cost competitive SMR design out there in the marketplace. It's a great option for not just electricity production, but district heating, hydrogen generation, and other industrial applications. We've taken an innovative approach to take cost out of the reactor, but also maintain plant systems and components from our existing licensed fleet. And that reduces your major licensing hurdles. In addition to that, a lot of these materials like the fuel and some of the components do not require further testing for licensing because they are operating in our fleet today. So moving on to developments in the last year, along with our arrangement with Fermi, we're continuing to strengthen that relationship. We look forward to working with them further in this year into their endeavors. In the Canadian market, we were one of 3 technologies chosen to move into the competition. This was announced last October. Since then, we've set up an office in Canada, hired a director of our Canadian operations, and are working with OPG in the final stages of their selection process. In Poland, we've further developed our partnership with Synthos Green Energy and are working with them in the deployment and understanding of our reactor and how it fits into the Polish energy system. We also signed an MOU with ČEZ about the same time last year as we are right here today. And we know that this year they're going to move forward in working on SMRs and how that fits into their licensing regime. So we're excited to move forward with that. In regard to licensing, as you'll see on the screen, we started to submit licensing topical reports or LTRs to the US NRC. The first one was approved in 9 months, which is a pretty good record for the NRC to approve one. And that is really our secret sauce in driving the cost out of this reactor. It's an integrated isolation valve into the reactor pressure vessel. This eliminates all the safety systems, backup systems, concrete rebar. It really takes about 50% of the construction costs out of that reactor. Okay. We've also submitted 2 other LTRs. One was approved by the NRC, the other one last week. We just got unanimous ACRS approval for that. We've submitted another 2 that will be approved before the end of the year. In Canada, we've submitted the first 2 packages of our combined phase 1 and 2 VDR. We're answering RFIs right now, and the 3rd package will be submitted in May. In Poland, we've started to work with Synthos and Exelon, and first discussions with the regulator there to discuss the steps in regulating the BWRX 300 in the Polish market. We're excited to move forward with that. If you think about our technology and GE and Hitachi, we have centuries of delivering energy solutions to the world, to modernize the world. We've got 60 plus years of experience designing, deploying, fueling, servicing reactors across the globe. We've licensed reactors in 10 different countries. So that type of experience and depth really is the genesis behind our 10th generation boiling water reactor. It builds on those decades of real world deployment and how we operate reactors today. Thank you.
Thank you very much, David, for your good update. So let's move on. Mark Mitchell, please present us the USNC micro modular reactor. Mark, we don't hear you. Still don't hear you. Could you try to unmute?
Henry,
yes,
USNC
Please, now
is
we
a
hear.
leader in the microreactor field with proprietary technology in microreactors, advanced fuel, and space reactors. My name is Mark Mitchell, and I am responsible for, as president of USNC Power, for our commercial reactor programs. I thought, as an introduction, I would share just 2 points with you. So the first is a bit on our progress, and the second is a little bit on our product. Since 2014, USNC has been progressing steadily towards deploying the first commercial Gen 4 reactor. This is really shown by our MMR at Chalk River Laboratory in Canada, which we're executing in partnership with Ontario Power Generation. We call this the Global First Power Project, and it's making progress towards securing all the necessary licenses and preparing for production. We expect to have the plant operational in line with the Canadian Nuclear Laboratory target date of 2026. On our product, this is a representation of our launch product, which we call the MMR Energy System. It's a small, it's a microreactor-based solution for off-grid applications. And if anyone's interested, in the bottom corner of the screen here, you can scan the QR code and get access to an AR app, which will enable you to explore the plant a little bit more. Some interesting facts about its features. It's a 5 megawatt electric equivalent design. It runs 20 years of life on a single fuel load. It uses proven high temperature gas cooled reactor technology, combined with our proprietary fully ceramic microencapsulated or FCM fuel and molten salt energy storage. It's set up, it's designed to provide power to remote communities and industry, either as part of an islanded microgrid or an industrial integrated energy system. And to give you an idea of the scale, this is really quite small. Everything you see in this picture will come to site on the back of trucks and be assembled. We're targeting initial deployment in Northern Canada and also looking forward to later deployments, offsetting carbon emissions in industry and perhaps even moving towards other applications like hydrogen generation, as was discussed in the last session. So thank you very much for the invitation to join the panel. I look forward to the discussion.
Not least, Scott, could you give us, please, an overview of NuScale developments?
Sure, I certainly can, and thank you. And so I'm so happy to be here. I couldn't be here last year, so I'm glad to be here this year. And appreciate the comments from my colleagues. It's exciting to see multiple SMRs kind of technologies be discussed and kind of come together here. And NuScale is at the forefront of the SMR industry, and it's good to hear there's so many similarities and we're all progressing well. That's very exciting. So I'm glad to be here. I want to give a little bit about NuScale and trying to go forward and talk about us just a little bit. Our total mission was to focus on bringing improved nuclear technology to the world, with the 4 pillars of our design being a smarter, cleaner, safer, and cost-effective design. Oh, and I just want to warn you, I have like 100 slides, but I'll only go through a few. One of the first things I get asked, and I was asked before this conference, was, so what's new with NuScale prior to, before we come to the conference? Well, NuScale has been very busy over the last, few years, since like 2007, developing our technology and moving forward with getting it licensed. Our technology design, the NuScale power module, and the base design of the NuScale power plant, which includes 12 power modules, was approved by the US NRC in August of 2020. The important part of that is not just getting a license for SMRs, it's working through that whole regulatory process and bringing a tried and true methodology forward so that it can address SMRs and understand how to really manage the differences between the large plants and the small plants and set up the entire industry for success. It takes an awful lot of due diligence and an awful lot of work to progress the design to be at that point, and we've done that. I love showing these statistics, but I really don't like talking about them. It gets old. On the smarter side, just like we've talked about, I think I heard Brett talk about the PWR technology, which is an excellent technology, and they all are, that we've leveraged that and we basically said, how can we take this existing technology and really kind of bring it down into a similar format like Alan was talking about that can be factory produced, shipped to site and installed in a short period of time. We've done that. We're going through manufacturing trials and working through with multiple manufacturers to produce the NuScale power modules. Here's a cutaway view of showing how the modules fit into a plant. I did mention our basic design was approved for 12 modules, and we've been working on plant designs that include a 4-module plant and a 6-module plant to really meet the market needs. And I think that's the overall importance of SMRs, is figuring out what the market requirements are, not just regulatory requirements, but the commercial requirements, and trying to bring that forward and go from there. And you can see down below the footprint of our plant is really rather small. For a 924 megawatt plant, the maximum size of our plant is only about 34 acres, 14 hectares, and it really is pretty compact. It allows for a small emergency planning zone, so it can be built close to points of use. I like Brett's image before of showing the plant right in the middle of a city area, and that's what a goal for SMRs is, a very small planning zone so it can be at points of use, so you can really leverage multiple capabilities and multiple off-takers. We have our patented triple crown of safety, and we've talked about that a lot. I'll move on. And that develops a second to none safety class, and I mentioned the emergency planning zone. I put this slide in here in the next slide because I think these are some of the most important factors, important elements of NuScale's design. It's not just the design, its ability to integrate with renewables and existing grid technologies while preparing for meeting the grid requirements of the future. That's an incredibly important factor, I think, for any energy source, including small modular reactors as we move forward. You've heard my colleagues talk about being able to provide energy for diverse platforms. I always like listening to Dave talk because I know Dave, but I like listening to him talk about the ability to meet different market sector needs. And, you know, NuScale took that to heart in developing the overall plant. And the interesting thing about our capability is with having multiple modules, they can operate either in unison or independently. So I love this slide, and I love to be able to talk about being able to provide energy, clean nuclear energy to all of these elements and all of these industries at the same time. One thing we don't have on here, and we've been talking a lot with some Nordic countries, and I've talked quite a bit with folks in Finland, is about being able to provide heat for district heating. And that goes back to the comment I made before about having a small emergency planning zone and having the plant very close to points of use. It's hard to move heat and keep it as hot as you need it to be from long distances. So this lends really well to NuScale's technology, and I'd say in general, SMRs in general. But I feel like some of the critical factors are being able to provide clean energy for mission critical facilities. I think we've seen in times of COVID and with natural disasters, I don't want to use the word critical, but it really is critically important to be able to provide energy to those sources while supplying energy to the grid and trying to bring the grid back up so you can get things back running very effectively. One of the things I wanted to note here was hydrogen production. And with one NuScale power module, you've got enough energy to produce over 2,000 kilograms of hydrogen an hour. That's an awful lot. So we think we've got a winning technology. We have quite a few opportunities in front of us. We're working with multiple customers and trying to move the technology forward globally. Our primary project is the carbon-free power project that is owned by UAMPS, the Utah Associated Municipal Power System. You may have seen the news that that project is moving forward. The agreements are coming into place with Fluor, which is our EPC, and that'll be happening. The target is 2029, but we've built up our capability to be able to deliver in NuScale power modules to go commercial in 2027. So we have that ability, and we're we're moving forward very, very quickly. And hopefully we're bringing all my colleagues along. And that's what I wanted to go through today. Thank you.
Thank you very much, Scott. And thank you everyone for giving these updates. Good to see that you're going fast forward with your designs and developments. But let's go to the questions. So maybe let's start with the question of the panel discussion. Why do we need SMRs if we already have large nuclear power plants? So maybe let's start alphabetically from Alan.
Sure. So why do we need SMRs if we already have large nuclear power plants? I think part of the answer there is, if you look at what's happening in the Western world at the moment, large nuclear plants are struggling, and a lot of that is down to the fact that they've got huge issues with financing. It takes governments to finance large nuclear power plants. SMRs, certainly we're designing our SMR to be financeable with private finance. So that's the first reason. The second reason is the scale of the challenge here is huge if we want to decarbonise. I think all the panelists have touched on it. We often get obsessed with grid electricity, but we've got to decarbonise the rest of the energy system, and grid is only about 20% of global energy. We need more electricity to do that, therefore we need more flexible power plants, and SMRs can be sited in many, many more locations. So you can put a large power plant, they've got more flexibility and they can work in an energy system, Scott just said, whether it be hydrogen generation or desalination or other aspects. And they can be delivered to a greater number of sites that aren't necessarily on the sea or more inaccessible for very large components associated with large plants. So there's many reasons why SMRs can sit in an energy mix alongside large nuclear power plants, and they have some significant benefits as well. But the key one is that much lower capital cost, lower risk, and speed to build.
Mm-hmm. Thank you. Brett, do you have add to that?
Yeah, let's just be honest. Other than Mark's plant, none of these plants are really small. But I think the key is we need to, like Alan was saying, the problem is the cost. And the problem is when you get into this territory of these super large plants being mega construction projects, and then costs spiral out of control. So I think the key here is, not so much small in size, but small in dollar amount. You got to keep it under $1 billion. If it's more than $1 billion, your project is going to fail, period.
David, any thoughts?
Brett, thanks for the lead. Thanks for the lead in on that. So ours is not as small as Mark's, but the 300 megawatt kind of range fits perfectly and replaced for coal. A lot of the Eastern European countries and the demand on coal, that niche fits in there. But you hit it on the head. Cost is the biggest driver. I mean, these mega projects are cost more than lots of countries' GDP. So you have to drive the cost under $1 billion, be competitive with other sources of energy generation that can be financed not by governments, but by private lending institutes. So that's the biggest reason. And the flexibility, as well as what Alan mentioned, I mean, that's key. We need these to replace coal, and coal is used for district heating, coal is used for electricity generation, coal is used for many different things. So we've got to get rid of those plants and replace it with the clean technology.
Thank you. Thank you. So Mark, you definitely have something to say about microreactors.
Yeah, all reactors are too big. Sorry, guys. Yeah, I mean, it's exactly that. I think we always, setting aside the fact that USNC's focus on microreactors is with a very specific application. We kind of believe that the smaller you get, the kind of laws of physics of nuclear power become reversed, and being really small offers a whole lot of opportunities. I think of Estonia, you're talking a country with about an average demand of somewhere around 1,000 megawatts. So a gigawatt scale nuclear plant is just not, out of the question. Microreactors and by extension SMRs probably have the advantages, the three advantages, that they're cheap, they're quick, and they're economically efficient. And I think we've spoken a lot about the first two, and when I come in with economic efficiency, I think you can get a lot closer to building what you need. You don't overbuild, you don't underbuild. The timing means you can plan. You don't sort of have to estimate 5 or 10 years ahead. And again, one of your biggest costs on a traditional nuclear power plant is your interest during construction. And that's not capital working for you. So anything you do to do that gets you much more economically efficient. And I think that's really one of the things that interests people, prospective off-takers, in using SMRs. Thank you.
Thank you. Thank you. So, Scott, do you have anything to add?
Well, I can't disagree with my colleagues at all. They all hit the nail on the head on cost, size, and time for implementing. And Mark was really right. There are two big things when it comes to implementing any kind of large project, but particularly nuclear. It's the cost of capital, and that comes down to labor. So the bigger the plant and the more complex it is, the more difficult it is to be quick and cost effective. So I really think that it comes to driving for SMRs, driving the ability to implement a plant very quickly. I'll disagree with Brett slightly. I don't think every plant is too big. All right. I think the important thing is to be able to be scalable and to be able to meet each need in an individual manner. Our plant looks big at the outset, but it's very scalable in implementation. We've had multiple customers talk to us about, I want to have the plant built for 12 modules, but I don't want to install all 12 to start. How can I cut back that cost of implementation and leave myself the flexibility to increase my clean energy output over time? Don't forget, a plant is really designed for 60 plus years of life. So every 10 plus years, you want to add another module to increase clean energy to meet your overall demand. That's easily done. So I feel that with SMRs, it's about the flexibility and the cost, not just one or the other. I think they have to come together. That's how I see it.
Thank you. Yeah, so I'd like to continue with that. Before today, there was discussion about the construction time of the SMRs. So what is your plant's construction times, and what do you see? What are the, let's say, success factors or limiting factors on building these plants in a timely manner? Maybe let's start with Scott.
Thank you. So we are currently our target for construction cycle, and we're working through that now. Since we've announced the 4-module and 6-module plant, we're reassessing everything, reassessing the cost estimate and the overall construction cycle. For a 12-module plant, our construction cycle is estimated to be about 36 months. Personally, well, this is being filmed. Personally, I feel it's much shorter than that, but that takes into account a lot of different customer aspects and site requirements that we've seen. So we set a target that kind of covers the whole gamut, but I feel it's much less than that. And so what are the biggest challenges with that? Well, it's ensuring the site characteristics can meet the overall need and ensuring there's not a lot of upgraded design or specific design detail. One little caveat I like to put in is we've looked at some of the coal replacement opportunities, and there's some strong opportunity there to really reutilize infrastructure and really cut down the implementation time, like a water intake in that and transmission yard, cut down the implementation time, and which cuts down the labor, the cost, etc. So we think it's about really looking at the overall site characteristics, analyzing that well, and being able to move forward very quickly.
Thank you. So Mark, what about USNC?
Yeah, I think we come from an even more extreme position. And this is really possible because of our really small size We don't even use the word construction. We talk of produce, deploy. We are focusing on building these these reactors like aircraft, minimizing on-site activity, which means the on-site portion of the activities will probably be completed in a matter of months. This is something we plan to demonstrate at the Chalk River plant. And I would say that's cheating. You know, we're on such a small scale that something like this is possible. But I think that provides a great opportunity to really change how people, I would say, consume nuclear power.
Thank you. So David, what about X300 time schedule?
For our first of a kind, we're looking at 30 months. Nth of a kind is 24 months. The big drivers there are how we are doing the initial construction technique of tunneling versus at large excavation. And one of the key LTRs, licensing topical reports, we have submitted to the NRC is to review that technique, how it's licensed, how do you monitor it, and how do you actually license that as you're putting the module in the ground. And that should be approved by the end of this year, and that will get us where we need to be for the 2-year construction schedule.
Okay, thank you. So Brett, tell us about the Open 100.
Yeah, I think we sometimes have to remind ourselves that nuclear isn't special, right? We give ourselves all these exceptions. Oh, things in the nuclear world take so long, but nuclear is not special. It is a power plant, and normal thermal power plants can be built in 18 months. So if your EPC, your engineering, procurement, and construction firm can't promise you 18 months at a fixed cost, fire them.
Okay, good. So, Alan, what about Rolls-Royce?
Sure. So our construction time, we call it 2+2. So the first 2 is for the site remediation, excavation, laying everything up to our aseismic bearing. And then it's 2 years for the module assembly and commissioning on the site. In terms of what's the critical path on that, Brett alluded to this, licensing is the biggest challenge. The fact that a lot of the associated industries who come on board when anybody wants to build a nuclear power plant hear the word nuclear and think, wow, this is a great opportunity for us to make some money. And as such, we see what are relatively straightforward licensing activities in other industries become huge and complex in nuclear. That's something collectively we have to avoid. If you look at some of the experiences the UK has had, the hundreds of millions, billions of pounds have been spent before they've even put a shovel in the ground. That's something we've absolutely got to avoid. There is no reason for it, no excuses for it, and the nuclear industry is as culpable for getting it wrong as some of the other areas as well. We've got to fix it.
Thank you. So another question, we talked here that in Estonia we are planning to maybe start building 1 or 2 SMRs. But what do you think, how big is the market potential in general if you look at the big picture and the global challenge we are facing? So maybe we start with Alan.
Great. So we think there's huge market potential. As I mentioned before, we often talk about grid power, and we've spoken about the role SMRs can play in the grid. But this is about total energy. If we look at the energy required to make synthetic fuels to replace diesel or jet aviation fuel, or to create hydrogen for district heating, it's a huge amount of energy. So the market is enormous. We sit in the 50 hertz market, so our plant is designed for that 50 hertz grid. It's not insignificant to change the design for 60 hertz. So we're targeting those 50 hertz markets primarily, and it's a huge market. The critical thing for us is proving that we can do what we say we'll do. And the biggest headwind we have is the challenge that nuclear has based on history, the perception that nuclear is always late, always over budget. That's our biggest headwind. Once we've demonstrated that we've removed a lot of those risks and we can do what we say we will, then the market is enormous.
Brett, your remarks?
Nuclear should replace all fossil fuels worldwide, period. The market size is 40,000 gigawatts.
Thank you. That's a lot, yes. So, David, your thoughts?
I agree with Brett. The market is massive, and we're not in it for the one or two. We're in it for the large build out, scale production, and how you get these out there in the world. It does, and we do need to replace coal and the other carbon generating technologies. So again, we're in this for the hundreds, if not more, reactors, not just the one or two.
Thank you. So, Mark, what about USNC point of view?
Yeah, this is easy for me to answer because I think at our scale, the market is essentially infinite, in terms of numbers of units. That aside, I think I very much agree with what everyone has said. It's the first time I've been working in an area, and I've worked in many, where every year the market projections grow bigger and bigger. There's the fossil fuel electricity market, and then there's the general process energy market, and there's a potential market expansion for hydrogen. These numbers are just really big, and I think that's not the question. In my mind, for us, it's about proving a way to the market, getting into the market. Because at the moment, I could equally answer that the market is zero. There is no market. No one's building any. No one's buying any. And I think everyone on this call has exactly the same attitude here, that we're working very hard to get a first product in the field, and that will enable this market to actually come into existence.
Thank you. Scott, any remarks?
Yes, so I love what Brett said. Actually, I appreciated everything that my colleague said, and I agree with Brett 100% specifically, and particularly what Alan said, that the goal really here is getting everyone is being able to get the regulatory processes aligned so that they're not so drastically different that nuclear looks very different in every country. This is what Brett said earlier. Nuclear is not that difficult. We understand how to build these plants. We understand how to control the reactivity and everything. And it should be much easier. So, we're going to find out. NuScale has a license. Let's see how attractive that is to other countries in trying to move forward and make the licensing, the construction, and the implementation much easier, leveraging that factory fabrication for repetitive and cost driving down ability. It comes down to manufacture, not building in the field. Manufacture it, ship it, put it in place. And I agree with what Dave and Mark were saying. There's a broad market. Nobody's in it for one plant. That's what some of the big plants used to be for. That's not what SMRs are about, and that's not what the world needs. So we've got to be able to deliver that, but we've also got to work with countries and governments and regulators to move forward and not just look at it from the same old perspective. That perspective has gotten really cloudy over time, and it needs clarity very quickly. Thank you.
Thank you. Thank you very much. Yes, actually, this was a very good lead into my last question to you all. So we know that there are more than 60 different SMR designs in the world, and not many or have been built. If we take maybe exception of the Russian ship nuclear power plant. So what do you think? What are the critical success factors to SMRs really to be the game changer and be the market changer? So maybe let's go from the alphabetical order last time. So Alan, please.
Yeah, so the critical success factors for SMRs, I can't speak for other technologies. For our technology, it's designed to be licensed. So designed for the total life cycle. That means designed to be licensed. It's designed for manufacturing. It's designed for for build, manufacturing the factories, build on the site. It's designed for operation and it's designed for decommissioning. We've designed it for all the phases of the life cycle to meet the cost and schedule challenges that we have. The critical success factor for us is getting on and doing it. We will demonstrate by doing. We have all the empirical evidence that we can build this, and the time we save, the cost we can. Critical success factor, let's get on and do it. And that's why we're working very closely with our own government now to get on and build them in the UK, where we have a very need and pressing demand.
Thank you. Brett?
Standardize supply chain.
Then short. David?
Yeah, I think design to cost for us is really the secret here. Is how do you make this plant financeable and cost effective for a customer? You can design something that is massively safe and huge, but if somebody's not going to buy it, they're not going to buy it. And so it has to be palatable to the customer base. I think Brett hit it on the head. The supply chain is very important. That's why we're using proven supply chain, proven components where it makes sense. Our fuel is licensed. There's no hurdles to getting our fuel into the plants. So that's a big piece of it as well.
Thank you. Mark?
I think my answer is not going to surprise you. It's in line with what I said earlier. We've got to do it. We've got to make sure it's cheap, quick, and economically efficient. And when we've done that, we've basically achieved success. Everything else that we're discussing feeds into those core parts of the SMR promise, if I call it that. Thank you.
Thank you. And Scott, please.
It's really difficult to follow these four colleagues. They hit all the intelligent thoughts I had, and then I have to come up with a new one. But I will say that, and they're all right. They're all correct, that there's aspects here that we've really got to hit on and be able to move forward. The one, I feel that the biggest aspect, though, is that SMRs and the SMR promise is not some future effort. It's now. It's here. And it's time to start really moving things forward. It's time to start building the first few and make sure that we nail it down and we develop that supply chain and we develop the cost models of each and every one of these designs. Like Brett said before, the market opportunity is huge. There's room for every one of these technologies because they bring something different. And every one of the 60 technologies, they bring something different to each market segment. So it's time to move forward. It's here. It's now. There's no future promise. It's now.
Thank you very much. So I want to thank you all for your notes, for your remarks, and I wish you great success with your design developments in the future, and especially the implementation of the first one. So thank you once again, and now we need to go on. Ja nüüd on hakata aeg tänaseks otsi kokku tõmbama. Aga enne seda vaatame tulevikku. Kalev Kallemets, Fermi Energia tegevjuht, palun.
Ja, tere õhtust kõigile. Nüüd on juba õhtu kätte tulnud. Ameerikas on jätkuvalt hommik. Ma alustan oma juttu sellest Enrico Fermist, et 38. aasta talvel, aasta lõpus, jõudis siis Enrico Fermi põgenedes oma naise ja lastega Mussolini Itaaliast, kuna tema abikaasa oli juut. Ta põgenes Ameerika Ühendriikidesse. Ja ta oli loomulikult selleks ajaks juba maailmas väga tunnustatud tuumafüüsik. Ja mõne kuu aega hiljem tõi Niels Bohr siis Ameerikasse, New Yorki jõudes selle informatsiooni, et tõepoolest Otto Hahnil ja Strasemannil õnnestus tuum lõhestada ja siis Liisa Meitner ja tema sugulane arvutasid välja, et tõepoolest tekkis ühe pooltundimise kohta erakordne kogus energiat. Ja siis tekkis hüpotees, et kas on võimalik, et seda energiat praktiliselt toota või seda kuidagi rakendada. Ja Enrico Fermi kutsuti märtsis 1938 pidama ettekannet Ameerika Ühendriikide mereväele, et mis on võimalus, et saada tegelikult ahelreaktsiooni inimese poolt. 38. aasta oli see, kui minu vanaema Linda Kutš oli, siis veel Nigol, oli 16-aastane. Eestis oli siis elektritootmisvõimsus umbes alla 50 megavatti. Vaatasime just numbrid järgi. See oli see arengutase, mis oli selles maailmas, kus veel ei olnud sõda, kus Eesti Vabariik ja Leedu Vabariik ja paljud teised riigid olid veel sõjast purustamata ja läbimata kõiki neid kannatusi, mida selles kohutavas sõjas paljud rahvad läbisid. Enrico Fermi 2 aasta jooksul, kui tekkis see hüpotees, et ahelreaktsioon on võimalik, koostöös ühe teise Euroopast põgenenud füüsikuga, Laszlo Szillardiga ja Edward Telleriga asusid tööle, et tuvastada, kas ahelreaktsioon on võimalik. Ja nad teostasid 28 grafiidikuhja vähem kui 2 aasta jooksul. Ja Fermi avaldas 41 teadusartiklit sellel perioodil, kuni 42 aasta detsembrini, kui saavutati Chicago ülikooli juures siis järjepidev ahelreaktsioon. See, mille põhjal meie kõik siin räägime, David, Brett, kõik head sõbrad, Alan, nende enda teadmised ja töö põhineb tegelikult paljude tuhandete inimeste tööl. Järjepidevalt, nii Hitachi's kui Suurbritannias, et mõista, saada aru sellest energialiigist ja kuidas seda inimkonna hüveks rakendada. Ja mul on tohutu tänu kõikide nende inimeste eest, kes selle aasta jooksul, eelmise aasta jooksul tegelikult meiega koostööd on teinud. Ma tänan teid südamest. Ja ma tänan teid kõiki Eesti inimesi ja Fermi asutajaid ja tõepoolest räägin nüüd lähemalt Fermi Energiast. 2018. aasta keskpaigas me arutasime tänaste Fermi Energia asutajatega, kuidas oleks võimalik Eestis tõsiselt võetavalt kaaluda väikereaktori rajamise võimalust. Kes, millal, milliste teadmiste põhjal, milliste vahenditega oleks võimalik isegi tõsiselt kaaluda. Loogiline mõte oli rääkida Eesti Energiaga, kust vastus oli huvitav mõte, kuid see ei ole meie strateegias. 2019. aasta sügisel oli juba aktiivne valimiskampaania ja just sel ajal ei ole poliitikutel aega rääkida 2 aastakümnete kaugustest teemadest. Tajusime samuti, et väljavaade, et Eestisse tuleb väikereaktorit tegelikult arendama välisettevõte, meie sõbrad Fortum või Vattenfall, on sama ebareaalne kui idee, et soomlased teeksid endale tuumajaama selleks, et varustuskindlust Eestile tarnida. Vastutuse peab võtma oma tuleviku eest iga rahvas ise. Teadsime enda kogemusest, et mõttest, et Eestis võiks olla väikereaktor, on vähe. Kohe tekivad küsimused, kes, kus, millal, kuidas, mis rahaga. Kui usud, pead tõestama oma töö pühendumise ja pädevusega, et see mõte on teostatav. Samuti lasus meie hariduse ja meie elukogemuse põhjal vastutus. Teadmisest, et keegi teine Eestis selleks tööks ei ole suuteline. Samuti näis 2018. aasta lõpp, 19. aasta algus, õige ajastus ja see oli õige ajastus. Seega langetasime jaanuaris 2019 koos otsuse moodustada ettevõtte, asuda tööle ja kaasata kapitali. Estvori kogemuse põhjal otsustasime, et peame suutma avalikult ja tuginedes kvaliteetsetele uuringutele vastata võimalikult paljudele tehnilistele ja sisulistele küsimustele enne planeeringu juurde asumist. 2 aasta jooksul oleme oma partneritega, maailma parimatega, seda tööd teinud ja teeme käesoleval aastal edasi. See töö ei oleks võimalik ilma rahata. Oleme südamest tänulik kõikidele meie senistele investoritele ja loomulikult tulevastele, kes on tuumaenergia vajalikkuses veendunud, meid usaldanud ja Eestisse uskunud. Ükski neist investoritest ei ole olnud naiivne tuumaenergia, ega Eesti poliitika, ega avalikkuse hirmude, ega erakordselt pika aja horisondi osas. Kuid nemad, nagu ka meie asutajatena, oleme kindlad, et tuleb teha endast absoluutselt parim, et tuvastada, kas väikereaktori rajamine Eesti elektrienergia taskukohase varustuskindluse, kliimaeesmärkide täitmise ja teadmiste mahuka majanduse arengu saavutamiseks on võimalik või mitte. Kerge on rehmata käega, võimatu, liiga kallis, me ei saa hakkama, mitte kunagi, mitte Eestis. Kerge on halvustada, kerge on õelutseda. Palju raskem on aru saada, kuidas on võimalik, kuidas on tegelikult ohutu, millised on praktilised valikud ja sellest ka aktiivselt avalikkust teavitada, saamata süüdistust müügitööst. Räägin kõigi asutajate eest. Meid kannab sügav vastutustunne Eesti ees ja missioonitunne saavutada tegelik süsinikneutraalsus iga ilmaga. John F. Kennedy ütles Ameerika Ühendriikidele kuulemineku eesmärki seades. Me ei tee seda sellepärast, et see on lihtne, vaid sellepärast, et see on raske. Ka Eesti ja Euroopa tegeliku süsinikneutraalsuse saavutamine, saades aru, kui kolossaalne see tegelikult on üks ülikeeruline maraton, mis nõuab trenni, higi, valu ja eneseületamist. Ka emotsionaalset eneseületamist. Teistmoodi ei saa. Uus Eesti valitsus on otsustanud põlevkivist elektritootmise lõpetamise 2035. aastaks. Stopper on käima pandud, kuid viimase 7 aastaga on rajatud vist ainult need tuulikud, mis Aidus ootavad ettekirjutus alusel lammutamist. Päikesepaneelid on toredad, vajalikud, kuid käesoleva aasta jaanuaris oli ainult 16 päiksepaistelist tundi. Ja enamus eestlasi näevad metsa pigem kui elukeskkonnana, kui kütusena. Samas 5 küsitlust viimase 2 aasta jooksul näitab, et 54–58% Eesti inimestest ütleb jah, pigem jah, küsimusele, kas kaaluda väikereaktorite sobivust Eesti elektrivarustuse tagamiseks põlevkivienergeetika vähenedes. See on napp enamus, aga naiivne oleks arvata, et see toetus võiks olla kõrgem kui Euroopa Liiduga liitumisele, mis, kui ma ei eksi, vist oli 66%. Soovidel tõsiselt võetavust, põhjalikult ja teostatavalt kaaluda väikereaktori võimalust varustuskindluse tagamiseks ei ole 2035. aastaks ei ole võimalik venitada. Lubage, ma selgitan täpsemalt, mida ma mõtlen. Arvestades reaalsusi ja olles konservatiivne, peab tõdema, et soovides 35. aastaks elektritootmist, mis tähendab, et enne testide, enne elektrijaama sünkroniseerimist on suurusjärk 100-200 testi, tuleb saada opereerimisluba, loomulikult vaja enne seda jaam valmis ehitada. Mis meie arvates tähendab seda, et ehitusleping peaks olema sõlmitud hiljemalt 2030. aastaks. Mis omakorda see eeldus on see, et on olemas ehitusluba. Ehitusloa menetlus, me ei ole võimalik välja mõelda protseduuri, mis tõsiselt võetavalt oleks alla 12 kuu pikkune. See on see menetlus, mis põhjalikult regulaator peab veenduma, valitud tehnoloogia, esitatud tehnoloogia, asukoha ja ka taotleja võimekuses tagada nõuetele vastav ohutus. Sisuliselt välistada igasugune kiirgusohtliku materjali osakeste pihkumine keskkonda, ükskõik millises avariissituatsioonis. Ja ma usun, et need samad tehnoloogiad, mida praegu tutvustati, kui nad läbivad loamenetlusprotseduuri, nende tehnoloogiate puhul on seda võimalik tagada. Kas aga see selgub siis, kui need on need loamenetlused läbinud ja meil endal on võimalik veenduda kõikides arvutustes ja avariistsenaariumites. Pädevad sõltumatud tuumaenergia regulaatorid samuti ei moodusta mõne kuuga. Selle pädevust ja rajatud ja reguleeritud protseduure peab hindama Rahvusvaheline tuumaenergia agentuur. Seega paar aastat enne loamenetlust tuleks antud uus asutus moodustada ja mehitada tuginedes vastavale põhimõttelise otsusele, võttes eeskuju Soome sarnasest regulatsioonist. Võimalik aeg põhimõttelise loa taotlemiseks ning ministeeriumitel, ametiasutustel ja Riigikogul kaalumiseks ja otsustamiseks meie hinnangul on optimaalselt 2026 aasta. Aga omakorda selle põhimõttelise otsuse tegemiseks peab olema kord, formaat, ilma selleta ei saa menetleda, mille alusel, mida saab määratleda, mida täna Eestis ei ole. Ja seda saab määratleda ainult vastava eriseadusega, milleks võiks olla tuumaenergia seadus, mille omakorda koostamine ja vastuvõtmine võtab vähemalt 12 kuud. Aga milleks vastu võtta seadus, kui puudub usutav menetluse käigus tekkiv informatsioon, ametlik informatsioon, millised on väikereaktori mõjud ja kas üldse ja kuhu oleks võimalik väikereaktorit Eestis rajada. Ja samuti, millise menetluse käigus tekib kindlus ja usutavus, et on arendaja, kes tegelikult on huvitatud vastava regulatsiooni kasutamisest. Meie arusaama järgi kehtivate seaduste alusel ainus menetlusviis, mis võimaldab avaliku menetluse käigus asjakohast informatsiooni saada, on vastavalt planeerimisseadusele riiklik eriplaneering, mille raames koostatakse samuti keskkonnamõju strateegiline hindamine. Me oleme hinnanud partneritega, et selle menetluse kestvus on 3–4 aastat. Seega tagurpidi arvutades, samm-sammult, ei tundu olevat ühtegi ülearustu aastat oodata. Me peame esitama põhjaliku, kõikehõlmava ja praktilise ettepaneku planeeringu algatamiseks Vabariigi Valitsusele käesoleva aasta jooksul, niipea kui valmivad viimased analüüsid. Kuid meil on veel palju tööd teha. Fermi Energia on põhjalikult analüüsinud parimate valdkonna ekspertidega eritehnoloogiad ja langetanud 2 põhimõttelist otsust reaktori tehnoloogia osas. Kaalume vaid tehnoloogiaid, mis on täna ametlikus loamenetluses ja millel on usutav väljavaade valmida, mis tähendab, et jõuda elektritootmisse käesoleval kümnendil. Teeme põhjaliku tehnoloogiavaliku tehnoloogiavaliku alles peale esimeste omatüübiliste reaktorite valmimist. Ehk et see tähendab enne ehitusloa taotlust. Ja see on ka Soome praktika olnud. Tuumaenergia on valdkond, kus tagamaks pikaajalist ohutust, töökindlust ja investeeritavust ei ole võimalik hinnata innovaatilisust kõrgemalt kui pikaajalist käidukogemust. Peame teatava kurvastusega tõdema, et erinevalt Põhja-Ameerikast, see on siis Kanada ja USA, ei ole Euroopas ja seda enam Eestis praktilist võimekust teostada nii loamenetlusprotseduure ja Euroopas üldiselt investeerimisjulgust ja tarneahelat selliste 4. põlvkonna reaktorite osas, mis kasutavad sulasooljahutust või sulametalljahutust. Nagu täna Staffan Quisti esitatud andmed tõendavad, on varustuskindlusega samas kiire Eestis. Samas oleme veendunud ka, et on üks 4. põlvkonna reaktor, mis on usutavalt Euroopas rajatav ja mis nii-öelda läänes demokraatlikes riikides täna ka tegelikult töötab. See on kõrgtemperatuurne gaasireaktor, mida väike mikroreaktori kujul arendab Ultrasafe Nuclear ja eeldatavasti saab rajatud Kanadas. Aga täna kõrgtemperatuurne gaasireaktor töötab Jaapanis. Seetõttu oleme otsustanud Fortumi, Vattenfalli ja Tractebeliga seda tehnoloogiat, arvestades ka, et meie teadmised võrreldes veereaktoritega on tagasihoidlikumad, selle aasta jooksul põhjalikumalt uurida. Koostame ja esitame riigile koostöös Vattenfalliga põhjaliku läbimõeldud inimressursi arengukava, mis hindab tegelikke, praktiliselt vajalikke võimekusi, millal, mis aastal, ja tänast olukorda, arvestades, et meil Eestis tegelikult on teadmised kondenssatsioonisüsteemil, režiimil elektritootmises. Teeme selles koostööd nii TTÜ, Tartu Ülikooli, Keskkonnaameti ja Tarbijakaitse ja Tehnilise Järelevalve Ametiga. Koostöös Tractebeli ja Raidla Ellexiga töötame välja detailsema võimalike otsuste menetlusloogika ning projekti realiseerimise tervikplaani. Tractebeliga analüüsime detailsemalt ka võimalike tehnoloogiate ja asukohtade auruturbiini jahutuslahendusi. Loomulikult loodame teha lähedast koostööd moodustatava tuumaenergia töörühmaga, et kõik küsimused saaks hoolikalt läbimõeldud ja avalikkusele teavitatud. Samuti hoiame väga lähedaselt silma peal Ameerika Ühendriikide, Kanada ja USA regulaatorite tööl. Oleme kontaktis Ontario Power Generationi ning kõigi tehnoloogiaarendajate ning rahvusvahelise tuumaenergia agentuuriga. Planeering ei ole kivisse raiutud lõplik otsus rajada väikereaktor, vaid oluline selleks, et saada usutavat ja avatud menetluse käigus riigile, arendajale ja avalikkusele informatsiooni. Kas Eestis on üldse sobiv asukoht ja millised on tegelikult väikereaktori keskkonnamõjud? Täna tutvustatud Tractebeli uuring ei ütle, mis on sobivaim asukoht ja seda ei tea ka meie. Ainult planeerimine saab anda vastuse, kas ükski eelanalüüsis osutatud asukoht tegelikult sobib. Kuid tundub, et on alust väita, et see on võimalik. Äärmiselt oluline on saavutada ka kohaliku omavalitsuse nõusolek ja seda arvestades on Fermi Energia kirjalikult esitanud 2 omavalitsusele ja elanikele oma nägemuse väärtuspakkumisest, mida saab kujundada igale asukoha eripärasid arvestades. Kindlasti elanikud, kuhu elektritootmine rajatakse, peavad sellest saama pikaajalist kasu ja neil peab olema selles õiguslik kindlus. Fortumi ja Eesti partneritega uurime Soome kogemusi, arvestades uue tuumajaama rajamise sotsiaalmajanduslikke mõjusid, näiteks kas on alust arvamuseks või eelarvamuseks, et kinnisvara väärtus langeb, või on hoopis vastupidine tõsi, et kinnisvara väärtus tõuseb. Ning võrdleme eri asukohtades Eestis sotsiaalmajanduslikku sobivust. Kaalumised ja arutlused, kuigi arvestades nii arvamusi ja eelarvamusi, peavad mingil määral ikkagi ka teadmistele tuginema. Planeeringu algatamine on ainus usutav sõnum Eesti noortele õpilastele ja tudengitele, et riik võtab väikereaktori teemat enam kui retoorikas tõsiselt ning järelikult ka samm, mille alusel noored julgelt enda õpinguid saavad seada. Ülimalt innustav on eelmise aasta neutriino suvekooli korraldades, et registreerus 24 kohale üle 80 õpilase ja tudengi, kes 2 päeva jooksul soovisid tuumaenergia kohta õppida. KBFi reaktorfüüsika töörühmas osalevad juba noored tudengid, kes sooviks minna edasi õppima Soome ja Rootsi. Sel aastal TTÜs meil käivitub esimene õppekava ja võib-olla tekib praktiline põhjendatus paari aasta jooksul käivitada ka bakalaureuse või magistriõppeprogramm. Täna me veel seal ei ole. Aga nagu ka meie kaasasutajate sooritused kuninglikus tehnikakõrgkoolis Stockholmis tõestavad, Eesti noorte nutikuse ja üldhariduse hea kuulsus ei ole aluseta. Meie eesmärk ei ole Eestile, Eesti riigile ja rahvale esitada udujutte või visioone. Meie eesmärk on esitada professionaalsed ja läbimõeldud huvitatud partneritega teostatavad mehitus- ja rakendusplaanidega ja rahastusplaanidega ning avatud teavitustegevusega praktiline ettepanek, kuidas tagada Eesti tarbijatele taskukohane elektrienergia varustuskindlus, kliimaeesmärkide täitmine ja majanduse teadmiste mahukas areng. Päriselt ja mitte ainult retoorikas. Eesti ajaloo see osa, mille üle me eestlastena oleme õigusega uhked, koosneb tarkadest otsustest ja tegudest, mis reeglina tundusid hulljulged. Juba oma riikluse väljakuulutamine ja selle kaitsmine vabadussõjas 2 vaenlase vastu oli julge ja kaugelt mitte konsensuslik. Kõvasti kritiseeriti. Kuid me võitlesime meie Soome, Briti, Rootsi, Ameerika ja teiste sõprade abiga. Balti kett, laulev revolutsioon, taasiseseisvumine, kõik see nõudis meeletult julgust, meelekindlust ja palju tarkust ning koostööd meie partneritega. Lähemast ajaloost. Eesti rahareformi IMF ei kiitnud heaks, kuid oli Eesti majandusliku edu alus. Eesti lihtsalt maksusüsteemi kritiseerisid Euroopas paljud, kuid ka kadestasid. E-riik, ID-kaart, e-valimised ja e-maksuamet tundusid alguses paljudele mõttetud edevusprojektid. Kellel seda vaja on? Kuid täna ei kujuta enamus inimesi ilma selleta oma igapäevaelu ette ja on pannud kindlalt olulise panuse Eesti kujunemiseks edukate IT-ettevõtete ja tehnoloogiaettevõtete keskuseks Euroopas. Ning mitmed nimekatest IT-ettevõtetest on täna investeerimas Fermi energiasse. Kutsun teidki, palun kirjutage info@fermi.ee aadressile. Eesti väiksus on eelis, mida oleme suutnud korduvalt, tuginedes teadmistele ja julgusele pöörata oma eduks. Soome eeskuju tõestab, et tark ja põhjamaine tuumaenergia rakendus, kus peamiseks majandusliku riski kandjaks on ettevõtjad, on üldiseks hüvanguks ja peab aastakümnete vältel vastu ka populismi tormile. Soome eeskuju tõestab, et valdav osa ühiskonnast ja isegi roheline erakond võib toetada tuumaenergiat. Eestis ei ole praktiliselt kõik Soome ja Rootsi lahendused, kuid mõndagi on õppida. Eesti suuruses lähtuses sobivad teised lahendused ja ka Fermi Energia ei kopeeri ühtegi ettevõtet, kuid kindlasti teeme koostööd oma sõprade ja partneritega. Euroopa kliimaneutraalsus 2050. aastaks on kolossaalne ühiskondlik ja majanduslik väljakutse ja võimalus. Me kas teeme sellest eduloo või oleme Eestis mainstreamis kopeerijad, rajame tuulikuid. Kas oleme tarkuse, enesekindluse ja võimekuse eksportijad ja tugevdame enda lääne partnerlusi või oleme saamatu Ida-Euroopa gaasi põletav kehvik, millisena meie idanaaber soovib kujundada. Suures plaanis on need ka Euroopa valikud. Kas süsinikneutraalsus päriselt iga ilmaga või jääme jätkuvalt tegelikult sõltuvusse gaasi põletamisest? Energeetika on alati ajaloos olnud julgeolekupoliitiline valik. Seega on suur valik ka järgmine. Kas rajame veel Nord Streami rahastades rahastame lääne väärtuste õõnestamist, tarnesõltuvust või teeme transatlantilist koostööd, kaitsmaks õigusriiklust, demokraatiat ja rahvaste enesemääramist täna ja igavesti. Sellise kõnega sooviks Fermi Energia selle aasta konverentsi lõpetada. Loodan, et oli huvitav, loodan, et on mille üle mõelda ja kui teil on küsimusi, palun kirjutage, kui te tõesti tunnete huvi meie ja omate julgust ja kuidas siis öelda, veendumust, et süsinikneutraalsus on päriselt saavutatav, siis ka kirjutage info@fermi.ee aadressile, vastame teile kindlasti. Aitäh teile kõigile ja tervitused kõikjale maailma!
Mm-hmm.